Welcome to the 2025 NASA STEM Enhancement in Earth and Space Science High School Internship Programs Science Symposium. SEAS is a collaboration between NASA and the University of Texas at Austin Center for Space Research. Former SEAS interns have gone on to major in STEM in college, interned at NASA centers and space contractors, and been hired by NASA working on missions such as Cassini, Europa, Artemis, and even launches at Kennedy Space Center. In 2025, we received almost 4,000 applications and had over 1,900 completed. We selected 82 students for the on-site internship and 93 virtual students as participants who were assigned to 19 different Earth and space science projects. Research was conducted in Earth and space science, environmental studies, climate research, mission design, and technology. Could you advance the slide? To say these students are amazing is an understatement. Each student conducted 60 to 90 hours of research in Earth and space science modules, Python coding, and project-specific work prior to starting their project. Interns heard from 10 NASA subject matter experts that highlighted NASA missions, opportunities, and careers during the course of this internship as part of the SEAS Speaker Series. You are in for a treat as you hear from these amazing young people, our scientists and engineers of the future. On behalf of Selena Miller, Laura Tomlin, could you advance the slides, please? On behalf of Selena Miller, Laura Tomlin, Angelica Krasinga, and myself, Margaret Baggio, the managers of the program, welcome to NASA SEAS 2025. So today we are welcoming 14 team project video presentations. We will divide into 2 sessions with one 20-minute break. Each team will present their research during the video presentations, followed by a 5-minute question and answer. Please post your questions on the slido.com website or app and use code SEAS 2025. Presentations during session 1 are reflected on this slide, followed by a 20-minute break. Presentations on session 2 will begin at 1:20 and will conclude at 3:05. We do hope you will join us tomorrow for day 2 research presentations. We will have presentations by teams followed by a 5-minute Q&A. We will invite each team presenting to turn on their cameras and their microphones to answer the questions posed by those listening. During the 20-minute break, we invite you to watch the video highlights of the student intern produced products as part of the Earth and Space Science project, and kudos to those students who went above and beyond in completing Python coding projects. Our first presentation is from the Moon to Mars project team. The mentor for this team is Dr. Ernest Lewis, who works in NASA Johnson Space Center's Astromaterials Research and Exploration Science, ARES division, as a research scientist, where his work focuses on developing innovative methods to support astromaterials research, laboratory analysis, and sample return missions for NASA. The project assistants for the Moon to Mars team are Becky Busby and Philip Ashby. Please join me in welcoming the Moon to Mars team with their project, Operation Delta.
Hello, we are the Moon Team, Operation Delta, the Lunar Base and Habitat Initiative, and our mission is to design a lunar base for long-term human habitation. I'm Yunji, and I specialize in sampling in the lunar habitat.
I'm Abby and I specialize in radiation.
I'm Neva and I specialize in the CLPS program.
I'm Vish and I specialize in communication and data transfer.
I'm Miles and I specialize in lunar chemistry and PSRs.
I'm Sophie and I specialize in on-the-surface robotic systems.
For reference, these are some of the acronyms we will be using in our presentation. Feel free to take a photo. Delta is an acronym for Designing and Experimenting for Lunar Technology Advancement, hence our initiative.
Here are a few research methods we used.
Our mission will begin with a flyby of the moon to locate lava tubes near the South Pole. Our probe will look at 3 volatile-rich areas, Faustini Crater, Cabeus, and Degurlash.
We will look for lava tubes that follow Figure 1's stable dimensions to ensure that lava tubes maintain its structural integrity for the whole mission.
Here is our mission timeline. The 2.5 years prior to human arrival will be a precursor mission to explore and set up the lunar terrain, followed by an integrated mission with both humans and robots, then a human exploration phase. Humans will be on the moon for a total of 232 days. For our base design, we decided an initial inflatable module in the middle, with additional modules added on later by astronauts with 3D printed lunar regolith. In the center of the base will be an elevator to transport astronauts to conduct EVAs on the surface. NASA's Commercial Lunar Payload Services Program, or CLPS, collaborates with commercial companies on delivering spacecraft and payloads for lunar missions. Here are key CLPS payloads that we will use. SCALPS and NDL will collect data during touchdown for landing refinement. RFMG will provide propellant gauging for human and robotic survivability. Viper instruments will prospect for volatiles such as water ice, and LULAD will scout lava tubes for our location. NASA's Viper will carry 4 CLPS payloads. It will search for water ice using instruments like Trident, a hammer drill that excavates samples, and NERVIS, which analyzes surface composition using infrared. The NSS will prospect for hydrogen-rich materials, and the LRA will locate nearby spacecraft. CLPS informs everything from chemistry to radiation, subsurface temperatures, and volatiles for our base design. Radiation dosimeters help calculate shielding requirements, thermal probes influence power and insulation, and drills and spectrometers confirm ISRU potential. These shape decisions about crew safety, experiments, and life support. Most importantly, since CLPS is shared between NASA and commercial providers, it makes our mission more affordable and scalable. CLPS missions also serve as a scientific backbone for a safe base design. Here's how we translate CLPS into architectural action. Surface and thermal profiles inform our site selection, water ice detection supports the placement of ISRU systems, and stratigraphy data helps decide where to embed structural elements. This scan timeline shows when our CLPS payloads are utilized. 6 months after the flyby, LULAD will search for an optimal lava tube for a base location near the candidates proposed by the flyby, and Viper will assess the terrain. In the crewed phase, we'll begin oxygen extraction and surface base science. As a part of the human landing system, NASA's Orion will transport the 4 astronaut crew from Earth to lunar orbit, where it will remain docked at the Lunar Gateway. The crew then transfers to Starship, which descends to the surface and serves as both a habitat and emergency return vehicle. As a part of the human-class delivery lander, SLS Block 2 cargo will be used for an infrastructure deployment and can hold up to 46 tons of payloads to deliver high-mass assets such as power systems and life support hardware for base construction. Blue Origin's Mark 1 will support precursor deliveries, while Mark 2 will handle resupply and modular payloads.
Now, one of the main concerns with going to the moon is how to protect astronauts and equipment from the lunar surface's hostile radiation environment. For background, there are 2 main types of radiation on the moon: solar energetic particles and galactic cosmic rays. Solar energetic particles are emitted from SPEs from our sun and happen around 7 times a year. Galactic cosmic rays are a constant form of radiation on the moon that come from high energy events in our universe like supernova. While trying to block radiation, the ALARA principle is utilized. ALARA, or as low as reasonably achievable, essentially states that you should protect against radiation until it becomes inefficient to do so. Now, the best way to block radiation is to put as many barriers between the person or object and the radiation as possible. Hydrogen-rich materials work best as this barrier, and after many consideration factors, we decided that Kevlar would be the best material due to its thermal resistance. According to ALARA, we don't want to go above 20 grams per centimeter squared of Kevlar due to the fact that the shielding becomes less efficient as you cross that point. Our base will be set up in a lunar lava tube for a variety of reasons. Lava tubes provide a stable temperature around 17 degrees Celsius, protects from SPEs and GCRs with roof thickness of 6 meters, and provides protection and shelter from micrometeorites and lunar dust. While astronauts are adequately protected from the radiation when they are on the base, they still need to conduct EVAs for research, which poses the question, how long is it safe for an astronaut to do EVAs? Looking at low Earth orbit limits, we were able to determine that astronauts will be able to conduct around 131 days of EVA in their career before exceeding legal limits. In addition, when astronauts are conducting EVAs, they have a chance to be exposed to SPEs, which could potentially astronauts to lethal amounts of radiation. To prevent this, the WASP protocol will be initiated. WASP, or Warn Astronauts About Solar Particles, is a procedure where mission control will be constantly monitoring data received from satellite SWFOL-1, which will provide them with almost real-time notification when an SPE happens. They will then alert the astronauts on the moon to head back to the base and not do any more EVAs until the radiation levels on the moon go back to normal. This procedure works because it takes hours to days for SPEs to reach the moon once it's released, providing adequate time for astronauts to take shelter. Furthermore, we can protect technology on the lunar surface by implementing Kevlar multilayer coating, radiation-hardened materials, new memory scrubbing technologies, and strategic designs to cover the most radiation-prone parts. Finally, a study shows that foods high in antioxidants might help mitigate the effects of radiation. So on our base, we would like to aim to grow as much of these plants as possible, such as blueberries, spinach, beans, and strawberries.
Permanently shadowed regions are areas of the moon where, because of crater walls and low sun angles, light hasn't reached the ground for billions of years. Because of this lack of sunlight, temperatures can stay extremely low, often below 50 degrees Kelvin. There are around 10,000 square kilometers of PSRs known and could potentially hold 100 billion metric tons of water ice within the first meters of the surface. Missions like LCROSS, LRO, and LP have detected many different volatiles on or right below the surface and deep freeze for eons, which will be essential for the long-term habitation of the moon. Molecules and elements such as water, molecular hydrogen, ammonium, xenon, and carbon dioxide have all been confirmed as available resources. In the South Pole, hydrogen is most abundant in the Faustini crater and CLPS regions. Here, abundances can reach up to 240 micrograms per gram, and ice can be found on the surface. Water ice on much of the rest of the moon can only be found by digging up to 20 centimeters into the regolith. Other volatiles like carbon dioxide and monoxide and hydrogen sulfide also sit at the bottom of the South Pole craters in much higher amounts than anywhere else on the lunar surface. As for metals and other origins of resources, the former are generally more abundant in the Mare regions of the moon compared to the South Pole. Iron, for example, can be found at a 26 weight% abundance in the Mare regions and only 10 weight% at the South Pole. Aluminum is the exception, with up to 20 weight% at the South Pole, but only half of that in the Mare. The rocks and regolith of the moon also contain many useful atoms that could be used. Minerals like plagioclase, olivine, and ilmenite contain both metals and nonmetals that could be used to build and live on the moon. Titanium from ilmenite and aluminum and silicon from albite and northite are readily available resources already on the moon. Regolith in general can be up to 45% oxygen. The volatiles found on the moon will aid in the ability for astronauts to live for extended periods of time off Earth. Breathable oxygen can also be gathered from water ice and regolith, as can hydrogen. Nitrogen can be found in small quantities, which will provide the rest of the base's interior atmospheric composition. The hydrogen and oxygen together give the components of rocket fuel, which will be used to launch back to Earth or beyond. Drinking water is created from the existing ice and reactions between the separated components. Helium-3 is an excellent atom to use in nuclear reactors. To gain the different atoms from ice, electrolysis on the collected material is used. Metals and oxygen from rock are extracted through a carbothermal reactor like NASA's CARD. However, this method releases carbon, and electrolysis can be used to reach the same results with lower emissions.
Now I'll be detailing the on-the-surface robotic systems. There are 4 main phases, starting with the flyby mission to identify 1 to 2 optimal lava tubes. Phase 1 involves sending the Surface Investigation and Terrain Explorer based on LULAD and Viper to map terrain, find sampling locations, and assess lava tubes for habitability, then select the human landing site. In Phase 2, mix and match robots deploy the inflatable habitat, move regolith, and grade the site. The dual-mode unpressurized rover sets up equipment like solar panels, and 3D printers build a communication center and launch pad. In Phase 3, astronauts arrive with the pressurized rover for large sample collection. It works alongside SITE, which identifies high-value samples. In Phase 4, astronauts perform longer EVAs, and mix-and-match robots assist with early cargo replenishment. The objective is a self-sustaining base. Now for key features. SITE uses an RTG and includes Viper payloads and LULAD's LiDAR sensor. The dual-mode unpressurized rover has a hauling tractor extension and a T-shaped Apollo-inspired control stick. Mix and match robots are based on MIT's WORMS frame and use modular attachments listed below. The 3D printers melt regolith and mix it with polymer for construction. The pressurized rover, based on Rover First, has a crew airlock in the back, making EVAs easier without repressurizing. To address lunar risks, I've included a requirements implementation strategy. Dust and fairy castle structures, systems use electrodynamic dust shielding, which creates an electric field to push dust from critical surfaces. Viper's triple layer shielding was effective at blocking dust from joints and will also be used. For extreme temperatures, dual compartment designs keep inner electronics like batteries warm, as shown below. NASA's cold arm technology replaces robotic arms. It works without heaters and could save around 30% of the mission's energy budget. Site also uses an RHU and a radiator to maintain temperature during dormancy. For low light and PSRs, LiDAR creates 3D topographic maps. This is paired with low light image enhancement and SLAM stereo cameras shown in the diagram to improve navigation. For rough terrain, active suspension lets wheels lift individually and stabilizes crew seats. Crab steering enables 360-degree wheel rotation for tight turns. Most systems are either prototyped or being tested in simulated lunar environments with high TRLs. I've also included the constraints, risk assessment, and test and evaluation plan in this diagram to prove mission readiness.
Next, we discuss sampling, a critical theme that complements on-the-surface robotic systems. First, we established a 3-stage mission guideline for sampling to display information in a preliminary design review format, highlighting the new focuses of lunar sampling research, including storing energy with lunar regolith, incorporating LiDAR sensors with ground-penetrating radar, and utilizing double-walled isolators. These guidelines will help us determine the success criteria for mechanisms on the moon and then relate them to a future mission on Mars. The requirements compliance matrix includes objectives, accuracy, mass, reliability, and regulations that guarantee safety across all 3 stages of the mission. Key aspects are co-registering LiDAR and GPR data to detect lava tubes, generating both a topographic and subsurface map, Lunar, a proposed NASA mission for storing thermal energy in regolith, and the NAC backpack LiDAR. We also refer to JSC safety and health requirements as well as the Artemis Accords to fulfill requirements. There are 3 main lunar sampling tools and systems, highlighted by a novel replaceable bit mechanism that can alternate between bits of a drill, a scoop, a hammer, a rake, and more, that is made of tungsten carbide to withstand the abrasive lunar regolith. We use a titanium tube, also designed in CAD, and a double-walled isolator to analyze samples inside the lunar base. One of the highlights of the technology that allows lunar regolith to store energy, powering nighttime EVAs and other tasks, is the Brayton cycle power conversion system that provides an efficient method of power conversion, allowing for the optimization of cycle temperature and pressure ratio. The electrodynamic dust shield that Sophie previously mentioned also helps the LiDAR from external abrasion. Finally, we have outlined the process of the success criteria and test implementation. Figure 1 represents a way of incorporating sampling tubes to grow plants from lunar simulants mixed with fertilizers of different percentages, 50% and 75%. In a greenhouse environment, we had success with 100% lunar simulant, as well as lunar simulant mixed with Hawaiian charcoal, as seen in Figure 4. However, as seen in Figure 2, there has been a lack of Martian soil growth due to the percolates in the soil. Yet these results are promising, as they demonstrate a greenhouse as a viable solution to a future mission on the moon, improving astronauts' physical and mental health and the need for filtering soil on a future mission to Mars.
Communication and data transfer are very important aspects of the lunar base as they allow for raw data to be sent back to Earth for better analysis very quickly. Communication systems are also vital for astronauts to communicate with on-surface robots and other astronauts. To optimize the back and forth process and reduce latency, we plan to use optical communications or lasercom. By using lasers, more data can be sent at one time very quickly. Packages that are over 1 terabyte can easily be sent within a minute. This is previously not possible with regular radio wave communication due to its lower data rates. This also means that live feeds from the moon can be broadcast at much higher resolution with highly reduced lag. To bring out the most of optical communications, we have created the Oculus system, or optical communications used for lunar settlement. Oculus gives a framework for how lasers are sent on the moon's surface and back to Earth. Oculus includes a system of satellites in the lunar communications base to form a network around the moon. Oculus is primarily composed of a satellite relay system which consists of the T-Bird and LCRS. T-Bird, which stands for Terabyte Infrared Delivery, and shown on the left, fits in a 3U CubeSat. However, the entire T-Bird will be in a 6U CubeSat to accommodate an ADCS. The T-Bird payload consists of several parts to allow for a downlink of up to 200 gigabytes per second. These parts are mainly commercial off the shelf and include two 100 gigabytes per second fiber transceivers and terabyte class buffers. To accompany the T-Birds, two LCRS satellites will also be launched. LCRS will act as a relay point between the T-Birds and Earth to relay information to the correct ground stations. The communications base will act as a culminating point for all lunar research data and communications. This will allow astronauts to look at the gathered data and analyze what they can on the moon before sending the rest back to Earth. The base itself will have a singular transceiver that can move to gain a wider range of application. Since the base is located outside of a lava tube, astronauts will need to take the elevator to exit the lava tube and then re-enter the comm base through the designated airlock. The T-Bird and communications base both have specifications that allow for optimal distance and data rates. First, the laser on board the T-Bird system will have lower power since the T-Bird itself is a small package and needs to conserve power. However, the laser itself is still able to cover a lot of distance. Average power consumption for a 10-minute downlink for the T-Bird will be around 100 watts. And the comm center will have a significant increase in power since the laser needs to travel farther. Finally, the Oculus system will function within given communication windows. This applies to most forms of communication and with optical communications as well, since light cannot bend without outer forces. There are certain times when communication with Earth may be easier, and that's why T-Birds are constantly orbiting around the moon and creating more windows for the communication center to send back data to Earth. This is a single point failure chart that we use to identify possible risks and their mitigation tactics.
This chart outlines how technologies from lunar missions, such as ISRU experiments, rover performance, and communication systems can directly inform Mars exploration. While factors like the soil chemistry and radiation differ, lunar testing enables early prototyping for Mars missions, potentially solving issues such as data transfer delay and environmental shielding techniques. If we had to describe our C's experience, it would be out of this world.
From meeting professionals to gaining insights into STEM fields from our mentor, we had the honor to learn and experience all of the components that go into STEM research, providing us with valuable knowledge that we will carry with us for the rest of our lives.
Furthermore, we were able to meet other like-minded and incredibly accomplished people, creating a place of belonging and finding lifelong friends.
The events of the summer were life-changing and further prepared us to excel in the careers we choose to pursue. Not only did we get project experience, we also got to go to places like iFly, Six Flags, Johnson Space Center, and even bat viewing.
Although we experienced some challenges with designing our base and extracting only the important aspects of our research when compiling, we are proud of the project that we have designed.
Each and every one of us are honored to call ourselves part of the Moon Team, and will leave this program more prepared to take on the world than we ever were. Thank you, Cease, for the resources, connections, and experiences you have provided us.
Thank you, Dr. Lewis, Mr. Phillip, and Miss Becky for your mentorship and care.
Thank you to everyone who supported C's and our team's efforts.
If you didn't scan it before, here's a QR code to all the references we used. Thank you for listening.
Congratulations, Moon Team. We invite you to turn on your cameras and your microphones and prepare for your questions. The first question is, given your research into the Artemis program and compared to your own Moon to Mars architecture, what would you change about the Artemis program today?
One thing we would expand upon is subsurface habitation and lava tube investigation to prevent further radiation exposure that Abby will add on to. And then we would also like to expand robotic precursor missions to expand upon site safety before people get there, and regolith-based construction due to our experiments.
Yeah, so adding on to the radiation part, there's not a lot of research based on like effective methods for blocking like technology from space radiation. So if we have more radiation prior to going on the moon and the Artemis program, it would be really beneficial for supporting the longevity of electronics. So it would also be cost beneficial, so you don't have to keep sending more electronics up there.
What on-site research did you complete at CSR, and how did these experiments help progress your role within the team and your overall plans for the lunar base?
I can take that one. So we experimented with growing plants in different levels of regolith and fertilizers, and we found out that plants can grow in 100% lunar regolith simulant. And so this proves that growing plants in a lunar base with the materials available naturally is possible and makes habitation more feasible.
Great. Why did you choose to land specifically 1.5 kilometers away from the lava tube in the robot system?
Yeah, so I can take that one. So the main reason why I chose 1.5 kilometers away was based on the NASA Heritage Site guidelines. So while our base or our landing missions aren't going to be landing near one of those heritage sites, I took the information given and kind of used the assumption that maybe the ejecta would land around 1 to 2 kilometers away, like when the spacecraft lands. And so we want to keep the lava tubes protected. So we are following similar guidelines as implemented in the NASA Heritage Site guidelines to protect the lava tubes when the robotic systems land.
Great. How do you envision the astronauts and building materials getting down into the lava tubes?
Okay, so I can take this one. In the beginning, we'll use, like Sophie said, we'll use mix and match robots that have a crane attachment to get like initial cargo down into the lava tube, like the inflatable part of the base. And then like pieces of the of an elevator will be sent up and then could be constructed by a mix of robots and astronauts to be able to get up and down the lava tube efficiently.
And what type of terrain data did the team analyze to assess surface hazards for lunar landings?
So I can start with this. So one note that we are going to be using for landing specifically is in the beginning, we will be using mix and match robots to clear and grade the site, and then the 3D printing robots before the human landing will be used to create a launch pad. We'll also be sending in our precursor missions LiDAR sensors, which will also be able to map the terrain and create a 3D topographic map. And additionally, we will be using mix and match robots to spray polymer around the launch pad to prevent dust from flying up. And those are the main ways that robotic systems will help keep the landing sites safe for astronauts when they arrive and later cargo missions. But if anyone else has something to add, then.
I would like to add on to Sophie. So this also relates to another question that was posed further down in the Slido, but we're planning on currently using also before even humans get onto the habitat to use LiDAR and GPR data to analyze the slope data to analyze terrain safety for landing and habitation. And then we also analyze some terrain slopes for the missions and EVAs in specific, and we analyzed that slopes under 15% would be considered more towards the safety aspect in the risk management chart that we developed.
Well, your team has done an excellent job. We want to congratulate each of you for your thorough research. So we will continue with our team presentations from the Engineer Beyond Your World team. Their mentor is Stephanie Hanover, a dedicated middle and high school teacher who contracts with NASA to develop curriculum. Her guiding motto is not just what you know in science or engineering, it's what you can do with what you know. So please welcome the Engineer Beyond Your World team presenting their project, Asteroid.
Hi, my name is Beltan, and I'm from the Bay Area, California.
Hi, my name is Gia, and I'm from Metuchen, New Jersey.
Hi, my name is Julio Perez, and I am from Brownsville, Texas.
Hi, my name is Alyssa Hadla, and I'm from Detroit, Michigan.
Hi, my name is Layla Curvilla, and I'm from Missouri City, Texas.
Hello, my name is Danette Lamrani Sarifi, and I am from Sparks, Maryland.
Hi, my name is Maddie Davis, and I'm from Austin, Texas.
My name is Brant Doggett, and I am from Spicewood, Texas.
As a team, we set goals to reach our overall objective Our main objective is to design and make a functional planetary defense system that can successfully change the trajectory of an asteroid away from Earth. We also want to design and construct a sample collector to successfully get a return sample from a metallic asteroid. Secondary objectives include research and learn about different types of asteroids, make a real functioning prototype of our sample collector, design a functional planetary defense system that will be effective to direct asteroids away from Earth.
Before coming on site, our team reviewed resources to familiarize ourselves with the asteroid belt. We learned that the asteroid belt is home to hundreds of thousands of small celestial objects. Asteroids are remnants of the early solar system, and they offer crucial insights into planet formation. Additionally, they are resource-rich and can potentially act as future pit stops for space exploration. Our team also looked into previous missions and past asteroids explored. We concluded that most missions were conducted on C-type asteroids due to their abundance and composition. C-type asteroids are rich in primordial materials, providing information about Earth's formation. For example, Ryugu and Bennu, both C-type asteroids, were targeted for sample collection. Their samples revealed organic materials such as nucleotides and hydrated minerals, suggesting they help deliver building blocks for life. Another key reason for asteroid missions is monitoring near-Earth objects for impact risks. By observing these asteroids, scientists can better predict threats and develop defense plans as needed.
The patch process started with all of us individually brainstorming ideas that we would then take parts of to create one final patch. As you can see at the bottom, there were a lot of ideas with differences like the shape of the patch, the team name, and background details. The final patch design was simple but meaningful. We chose the name Asteroid, which stands for Asteroid Sampling Technology and Recovery Initiating Defense. We chose a diagonal shape rather than octagonal because we wanted to take inspiration from the DART mission patch. The asteroid on the patch was chosen because it looked similar to the asteroid that we picked to land on, and then to improve the flow of the composition, we added the red streaks in the background of the patch to indicate the path of the asteroid that we intended to land on, learn from, and alter.
While appearing to be uncommon, meteors crash into the Earth daily. Although Earth's thick atmosphere allows the meteors to simply burn up, the larger they are, the more likely they will be a danger to life on Earth. A prime example would be during the year 2013, where a relatively large asteroid crashed into Chelyabinsk, Russia. This event caused many fatalities and injuries, proving that NASA should prioritize detecting and deflecting potentially hazardous asteroids that are in close proximity to Earth. Years later, the first mission to an asteroid with the objective to deflect its course from Earth was created and successfully implemented. The Double Asteroid Redirection Test Mission, or DART, was a NASA space mission aimed to testing a method of planetary defense against a near-Earth object. The DART mission paved the way for planetary defense sector of the agency and received immense support from the public. As mentioned by Dr. Abel in my team's recent meeting with him, planetary defense is the people's #1 concern and has been given priority to NASA in recent years. For these reasons, my team has created an innovative yet economically viable defense mechanism to deflect the path of our near-Earth asteroid of interest, 3554 Moon. In order to achieve all of our primary goals, the success of the sampling mechanism was pivotal. While all of us were eager to begin detailed sketches of possible sampling mechanisms at the start of the internship, we knew that some parameters needed to be considered beforehand. The sampling mechanism, which was prototyped and modeled with CAD, needed to collect regolith, pebbles, and debris from the surface of 3554 Moon, and would need to reach a moon's subsurface. Understanding the entire composition of a moon is crucial to our mission, and will not only allow us to gain immense knowledge on the early solar system, but will also allow us to gain support and funding from NASA and private aerospace companies due to a moon's potential of containing precious metals of high value.
The asteroid that best fit our goals was 3554 Moon because of its metallic composition, its extremely close proximity to Earth, and factors of past missions. It's an M-type or metallic type asteroid, meaning it holds more metals than any other asteroid type. These asteroids are thought to be cores of protoplanets or other planetary bodies that never fully formed. This asteroid is also categorized as a near-Earth asteroid and crosses Earth's orbit twice per revolution, meaning it's an Aten asteroid. With this asteroid being an M-type, it is presumed to be solid and house precious metals like nickel, platinum, iron, and cobalt, which adds an extra layer of potential funding. We chose to have our mission on a solid asteroid because of the risks that rubble pile asteroids hold. This is demonstrated through OSIRIS-REx mission, where they tried to land on a rubble pile asteroid, and if they had continued to land, they would have gone straight through the asteroid. Also, defense mechanisms that work on rubble pile asteroids, like the one DART was tested on, are not guaranteed to work on solid, much denser asteroids. So, to better defend our planet from all types of asteroids and to research the founding of our galaxy that we call home, we will sample and move this asteroid from its orbit.
The orbit of a moon is elliptical and crosses both Venus's and Earth's orbits, which makes it easier for us to reach the asteroid. For our probe's approach, we want a time period that's relatively soon, but also gives us time to build and design the other parts of the mission. After analyzing JPL's Horizon Systems data, it was revealed that on May 1st of 2038, a moon will be the closest to Earth in decades, only around 0.3 astronomical units. That would make the trip there, if we used ion propulsion systems like the Dawn probes, only 1.5 to 2 years. By including radar on our probe, we can shorten the orbiting time of our probe around the asteroid to find a safe landing location. By doing this, we shorten the time on the asteroid so that the time on a moon can be exactly a year long, making it so the probe can leave the asteroid during the 1st through 3rd of May 2039, when a moon will be at its shortest distance for the next couple of years, 0.45 astronomical units. The longer time period from now until launch, there's a good chance for a new or better propulsion system to be developed to make the trip even shorter. These dates would allow the mission to take 5 to 6 years currently, wherein Hayabusa 1 took a little over 7, Hayabusa 2 took 6, and OSIRIS-REx took 7.
Due to recent cuts in NASA's budget, our team realized early on that keeping the cost of our mission low was one of our main priorities. In our meeting with Dr. Abel, we learned that most Americans believe that NASA should prioritize planetary defense the most. Due to both this and the fact that longer missions are more expensive, we made the decision to choose to visit a near-Earth object. We also looked at the internal structure of the asteroid. Some asteroids, called rubble piles, are not actually one solid rock. They're a pile of rocks held together by each other's gravities. In the end, our team decided against visiting a rubble pile because their surfaces are extremely unpredictable. The final factor in choosing our asteroid was the type of asteroid. Although P and D type asteroids are thought to be rich in volatiles and organic materials, we ruled them out due to their distance from the Earth. Although they are the most common type and carbon rich, we decided against choosing a C-type asteroid because they've been studied many times before. This is also the same reason why we ruled out S-type asteroids, which are mainly composed of silicates.
Our team met with Dr. Joseph News, a senior scientist at Goddard Space Center. Dr. News is a leading expert in astrobiology and astrochemistry. His research also involves studying near-Earth asteroids contributing to planetary defense. One major challenge in asteroid research is preventing contamination. Dr. News explained that secure sampling processes are crucial, as even slight Earth or space-based material can skew analysis of an asteroid's natural chemistry. Regarding mission planning, Dr. News emphasized that safety must always come first when selecting landing sites. He also explained that having a sun-synchronous orbit would be helpful for long missions and would ensure consistent lighting, helping with surface observation. Dr. News shared some of his research, and he shared his experience of accidental discovery. Through this, he reassured us that different asteroids would offer different insights, and that many missions involve uncertainty and taking risks.
We met with Dr. Paul Abel, NASA's chief scientist for small body exploration at the Johnson Space Center. He specializes in both planetary defense and near-Earth objects, and has worked on many NASA missions involving asteroids, including Hayabusa, OSIRIS-REx, and DART. Our meeting with Dr. Abel resulted in us learning a lot more about near-Earth asteroids and planetary defense. Two of the most vital lessons that he taught us about planetary defense were that finding the potentially hazardous asteroids early is crucial to be able to actually do something to protect our planet in time. The other lesson was that in planetary defense, you do not get to choose the asteroid chooses you. Near the end of the meeting, Dr. Abel also described the major challenges regarding the preservation of ice while it's being held in the spacecraft, especially during the re-entry into Earth. To design our mechanisms, each team member was originally given a large sheet of paper and asked to draw 6 original ideas of mechanisms. We were separated when brainstorming to ensure creativity and originality. Next, we went back to our team's workspace and left comments and constructive criticisms on each mechanism. We then utilized the feedback to sketch and design our final ideas. The next day, we introduced them to each other and integrated our ideas to create the mechanisms we built on our sub-teams.
Team Alpha decided to use a solar sail as our prototype defense mechanism. A solar sail is a propulsion mechanism that uses the momentum of light or the pressure exerted by light to propel a body through space, as said by the Yarkovsky effect. Although it is a relatively small effect on orbiting bodies, with the correct materials like mylar and other highly reflective materials, it can cause immense movement for large bodies, as demonstrated in the light sail projects. I decided on a light sail that was 305 meters by 305 meters because that would generate 40 kilometers per second velocity, which is the escape velocity of the moon asteroid.
After countless days of brainstorming, sketching, and purchasing additional materials, my sub-team and I were finally able to begin creating our sample mechanism prototype. Our final design integrated each team member's individual ideas into one unified and successful sample mechanism for mission Asteroid. We decided that our sample mechanism would be attached to a robotic arm on the space probe, and it would be lowered down to the surface of a moon. The sampling device is encapsulated in a cylindrical metal container composed primarily of aluminum due to its strength, lightweight, and thermal protection properties. The inside of the container is covered in a sticky adhesive that would be able to collect non-magnetic regolith. The vessel is propped up by lander legs for stability purposes in the low-gravity environment of a moon. Within the container, the mechanical press is centered and held up by two gears on either side of the container. The sides of the 3D printed press contain ridges that the gears fit perfectly into in order for the press to be brought down when the spacecraft lands and for the press to move back down when the sample has been collected. The gears are attached to servo motors, which have been programmed using the Arduino IDE to move clockwise and counterclockwise in specific time intervals, allowing the mechanism to move autonomously. The drill component is held by a metal capsule that twists to tighten the drill, and it operates using a brushless motor.
After completing the build, we ran 2 testing trials on a simulated 3554 moon environment with 2 different potential surfaces we might encounter. The first issue we faced was stability. The lander legs we attached didn't give much support, and on the flat test surface, we couldn't achieve the kind of anchoring we originally planned that would have made the entire system much more secure. The second limitation was surface conditions. Our simulated moon environment didn't have nearly as much regolith as the real asteroid would, so the adhesive didn't have enough material to collect. The next limitation was gravity. Testing on Earth meant we couldn't replicate microgravity, so the adhesive hadn't picked up as much material as we'd hoped, since our design was made for conditions where loose material would float and move through the chamber. Even with those challenges, the trials were a success because they proved that the concept works and showed us exactly what to improve next.
Main components of our sampling system, a drill and a magnetic sample collection dish. As the drill works, it will break into the surface of the asteroid and create chunks of magnetic sample material that can then be collected by the dish, along with other loose particles in the microgravity environment churned up with our direct burst of nitrogen gas. With the samples collected, we can withdraw the drill and pull it back into the chamber above the sample collection dish, and then we can close it up and leave the asteroid. This design was chosen for several reasons. One of the main reasons was that we wanted to primarily collect the ferrous material in the asteroid, and we thought that a drill would give us the best chance at breaking into the surface and collecting more subsurface samples. In addition, because it was feasible for us to prototype with the time and materials available to us at CSR, we ended up choosing this design over other options.
The defense mechanism is made up of an ion thruster and an attachment mechanism. The attachment mechanism can be divided into a group of air valves and a metal plate, which is crafted from Damascus forging and made mainly from iron and nickel. This will be orbiting a moon in the opposite direction of its rotation. When a relatively smooth location on a moon is located and chosen as a landing/fusing site, the defense stage will disengage from the rest of the probe and descend to the surface of the asteroid with help of its ion thrusters. At the same time, the air valves will open and let out a burst of nitrogen gas to disperse anything on the asteroid's surface, leaving behind a clean area. The defense stage will then make contact with the area as low as an angle as possible and slide on its surface while thrusting downwards to add pressure. Hopefully, the metal surface of a moon and the metal plate on this defense stage will heat up enough from sliding against one another and friction weld to one another. The ion thrusters will then gradually increase the velocity of the asteroid until its orbit changes.
After our team finished building, wiring, and coding our mechanisms, we tested them continuously. We started by testing individual systems until they were consistent before integrating the full system, focusing on whether the rack could reliably control the vertical joule motion on our simulated asteroid surface. Overall, the mechanism ran smoothly under load, and the drill effectively disrupted the rubble. The magnetic plate performed as intended, attracting the ferrous material, including meteorite samples. During testing, we noted a few areas for improvement. Alignment of the rack and pinion system needed higher precision. Our motors needed proper torque settings to minimize backlash and ensure stability. Finally, the rack and pinion system needed more power to deliver high torque for deeper drilling under asteroid-like conditions. In summary, our iterative tested validated the functionality of our drill mechanism and our magnetic collection system, while highlighting our key refinements: alignment accuracy, structural stability, and drive power, to prepare for our actual environments.
collection mechanism, we decided to keep the drill. We also chose to combine the adhesive and magnetic collection ideas. We chose to add the adhesive at an angle so that the non-magnetic samples kicked up by the drill would be more likely to stick to the adhesive. We made this choice because we had noticed while testing that the samples collected along the lip created by the adhesive sticking to the surface it was on. For the magnetic collection dish, we kept it higher up within the sample collection space. We took inspiration from the housing design in the alpha prototype and the rack and pinion design from the disc prototype in order to create our final mechanism to run the drill.
For our final defense mechanism, we chose to go a different route than what each of the subteams picked. Our defense system uses high-powered CO2 laser ablation to gradually alter the asteroid's trajectory by sublimating surface material and creating thrust via the reaction of ejected vapor and debris. We selected this method for its continuous controllable force output and scalability across asteroid classes. Critically, our design leverages solar concentrated energy to power the laser, eliminating the need for onboard nuclear fuel-based power systems. This allows us to generate and sustain a kilowatt class beam output using nothing more than sunlight focused by a deployable mirror array. Laser ablation was chosen because it offers the highest thrust-to-energy ratio among non-impact methods, and uniquely enables precision vector control without physically contacting or attaching to the asteroid. Using the provided and computer-assisted design, I calculated that the average thrust of the laser is a continual 1.42 newtons when using the laser at its full force on an asteroid. The defense mechanism also houses our LiDAR, radar, spectrophotometers, and our magnometer.
We researched commonly used materials as well as figuring out what kinds of metals would not be found in a moon. We decided to use mylar and aluminum for the solar sail in the defense mechanism because they're commonly used, and for our drill we chose to use tantalum. Dr. Abel mentioned during our call that tantalum isn't found in any asteroids, so we chose to use it in our drill to remove any chance of accidentally cold welding the drill to the surface of a moon or contaminating the sample without realizing.
This slide outlines our spacecraft's power distribution strategy. The largest draw comes from our scientific payload, which is radar, LiDAR, a spectrophotometer, and a magnometer. The CO2 laser pumps are the only electronically driven part of the defense system and are the next major load and operate in burst mode along with the radar system to save energy. We use a lightweight foldable radiator system for passive thermal rejection that deploys post-launch. A surplus buffer maintains science operations during laser cooldown. Since the laser is powered by concentrated sunlight via reflectors, onboard electricity is preserved for critical systems. We've also planned to jettison the sampling system post-use, reclaiming nearly a kilowatt of power and extending operational endurance after surface activities conclude.
We have learned and used processes and designs that could overcome the challenge of drilling and using various planetary defense systems. Some benefits we got from our mission is actually learning how to implement a new way to collect samples on an asteroid surface, furthering technology advancements. What we've also learned is we can implement both planetary defense and sample collection mechanisms at the same time without actually needing two separate missions. We've also learned how everything would react in microgravity and designing the mechanisms to work while in microgravity. Some more great benefits is actually figuring out an easier method to collect samples on the asteroid containing metallic material, and also easier methods for our planetary defense systems.
Our team faced several key challenges in designing our mission. First, we dealt with theoretical constraints. Many of our systems, especially the defense mechanisms, were untested in real-world conditions due to the lack of space simulation capabilities. Material and cost limitations were also a significant challenge. Many materials we needed were too expensive, so we had to optimize available resources to keep the mission feasible. There were also various safety concerns. High-energy systems like ion thrusters posed operational hazards and regulatory restrictions. Selecting the right asteroid was another challenge. We needed a target that would provide valuable scientific data while ensuring there was enough existing information to make it feasible. Lastly, testing on Earth. The lack of microgravity meant that our prototypes were not tested in conditions similar to space, which impacted the performance of our designs. Despite these challenges, our team came together to find innovative solutions and push forward with the mission.
NASA STEAS is a truly impactful internship that has allowed me to become knowledgeable in a variety of scientific disciplines and to gain skills necessary for my future career as an astrophysicist. From learning how to solder and desolder to building a mechanical press, I have grown so much from these past 2 weeks, and I cannot describe how memorable this internship has been for me.
NASA STEAS has helped me grow my love for STEM and has given me valuable skills like programming that I know I'll be able to take with me in the future.
been a wonderful experience. Working on the Engineer Beyond Your World project team was so rewarding, and I really learned to appreciate all the different perspectives people can bring to a project like this. Despite the challenges that we faced, addressing them was a team effort, and being able to delegate tasks and work to my strengths, confident that my teammates would do the same, allowed me to do my best work. I really couldn't have asked for a better experience overall.
Thank you, NASA SEAS, for this opportunity, which really solidified what I want to do in my future, which is become a mechanical engineer one day in the space industry. Thank you again, and go NASA SEAS.
SEAS has really been a wonderful adventure for me. It really helped me explore my passion in aerospace and see how big the industry really is. It was an amazing educational experience, both for soft skills like teamwork and hard skills like engineering.
I cannot stress how grateful I am that I got to participate in SEAS. Not only has it taught me so much about space, it has also let me meet a group of amazing, talented people.
I'm just going to say that SEAS has been an absolutely wonderful time. I've learned so much about myself and so much about the people around me, and it's really cemented that this is what I want to do. I want to change the world through aerospace. Thank you so much, SEAS, for this amazing opportunity.
SEAS really allowed me to dive deeper into my passions for mechanical and aerospace engineering by providing a real-world problem, really allowing me to bridge my knowledge with practical applications.
So we have several questions for the Engineer Beyond Your World team. So if you would turn on your cameras and unmute your mics. Our first question is, how would your defense system adjust if the asteroid had a highly irregular orbit?
I can take with that one. So our defense system is a laser-based system, and it's going around the asteroid. If it had a highly irregular orbit, it wouldn't change much about the laser except for the solar energy that's being pumped into the laser mediums. And in the calculations, we estimated way below the necessary amount of energy for thrust. So it would still have the same amount of thrust that we needed. And with this mechanism, we can choose to push it into a more regular orbit with the constant thrust the laser provides.
How do you plan? Oh, yes, go ahead.
Sorry, expanding on that, sometimes these irregular orbits push them really far from the sun, so we might have to adjust our defense mechanism based on that since it's using the energy of the sun to create the laser. That's all, sorry.
Oh, great. How do you plan to maintain continuous contact on an uneven, rotating, and potentially non-uniform asteroid surface without bouncing off in microgravity?
Sorry, I can take this one. So we plan to, as we lower the drill, we plan to have like ion thrusters on the other side of the space probe so that we would have like a constant force pushing the drill onto the asteroid so that it would not bounce off. So that way it just has a force that's like pushing it rather than it just being like free floating and bouncing off. So yeah.
What materials did the team use to build the prototype, and how do those materials simulate a real space deployable device?
Okay, I can take that one. So we weren't really able to use materials that would help us simulate a real space deployable device because we had a limited amount of time, so we only used available materials in order to build the prototype. But we did do research on what materials we would end up using in our final spacecraft. For example, with our prototypes, we just used like the available drill bits that we had. But in the real device, we decided that we would end up using tantalum because we had researched it, and I did detail those reasons in the presentation. However, we did simulate the environment of the asteroid by using various metals and pieces of ferrous material.
If the asteroid turns out to be porous instead of a solid rock, how would your defense strategy avoid the object creating multiple hazardous fragments?
I can take that one again. So what our defense system is doing is basically vaporizing the rock. As long as you aren't carving off large sections of it and you just continue with one point or specialized points, even if it is porous, the laser mechanism won't affect or break up the asteroid. And specifically because this is an M-type asteroid, they're usually the cores of either protoplanets or larger asteroids, and they are completely solid.
Great. If you had more time or resources, what improvements or additional testing would you add to bring the prototype closer to flight readiness?
I can take this one. So one thing we would do we would perform enhanced simulation and testing. So we would probably try to better replicate the space environment. So this would be like the temperatures, the microgravity, the radiation, to basically test all the components to ensure consistency and high performance. And we would also study more into the material science and cost optimization. So we would test those materials, like they mentioned, tantalum, to test the strength, durability, and just the overall efficiency. And obviously we would do more safety and compliance. So we would analyze the hazards, the different trajectories, and just using better simulations to perform better mission planning for our target asteroid. And by conducting these extensive testing and integrated tests on diverse simulants, we could ensure that our asteroid mission would be the most smooth it could possibly be.
Adding on to that, our lack of like a microgravity simulation here, because we had to test our prototype, was one of our major challenges throughout the whole process. Like we had to build and deliver something that could be tested here on Earth, but could also like possibly work on a microgravity environment like an asteroid. So yeah, that was something that we really had to think about while we were prototyping and building during our process.
Well, congratulations to all your team members. Our next presentations are by interns on the Astronomy Surveying the Universe team, mentored by Dr. Judith Reese. Dr. Reese conducts near-Earth asteroid observations at McDonnell Observatory while continuing to support education and outreach programs at CSR. Please welcome the Astronomy Survey the Universe team with their project, Black Hole, Detecting Black Holes.
Hello everyone, we are the NASA STEM 2025 Astronomy Surveying the Universe team. Our project, Black Hole Hunters, involves detecting black holes through microlensing events. My name is Angelique Kazmierczuk. I am a rising senior and I'm from Yuba City, California. One fun fact about me is I play tennis.
My name is Zoe Kramer. I'm from Eugene, Oregon, and I'm a rising junior. One fun fact about me is that I have a dog.
Hi, I'm Liza Friedman. I'm from Sarasota, Florida. I'm a rising junior, and one fun fact about me is I'm a competitive swimmer.
My name is Olivia Vanacore. I'm from Lafayette, Louisiana. I'm going into the 12th grade, and a fun fact about me is that I skateboard.
Hi, I'm Juan Sanchez. I'm from Brownsville, Texas. I'm a rising senior, and outside of SEAS, I'm a part of the South Texas Astronomical Society.
Hi, I'm Rohan Ravula. I'm going to grade 12. I'm from Cerritos, California, and I like to hike.
Hello, my name is Krishna Srinivas. I'm a rising junior, and I'm from San Jose, California. And one fun fact about me is I like playing the violin.
Hello, my name is Roshan Nada, and I'm a rising senior. I'm from Bellevue, Washington, and one fun fact about me is that I like to snowboard and ski.
This is the outline of the content we are going to be presenting in our presentation.
Black Hole Hunters is a citizen science project started in 2021 as a continuation of SuperWASP, another citizen science project that focuses on identifying variable stars. Black Hole Hunters aims to identify the missing black holes in our galaxy by finding changes in light curves. The 70 black holes that have been discovered were found because of X-ray signatures given off when a black hole becomes close enough to a star to draw in matter and emit light. Black Hole Hunters needs citizen contributions to form a list of candidates and conduct follow-up calculations to confirm possible black hole subjects. But finding a black hole using microlensing is rare, so our goal for our research is to answer the question, can we detect black hole candidates using microlensing and predict their mass?
To observe a microlensing event, we use data collected by TESS, which stands for Transiting Exoplanet Survey Satellite. It uses specialized photometers on board to continuously measure stellar brightness. This graph displays how the brightness of a celestial object, in this case a star, changes over time. Moving on, how to read the graph. The x-axis represents time measured in Julian dates, which is a continuous method astronomers use to measure days, providing a consistent timeline for observing celestial events. The y-axis indicates luminosity or how bright the object appears. The empty white circles are noisy data that later gets averaged out, as shown by the red circles, to make the graph easier to read. Lastly, the symmetrical peaks we observe in the simulated microlensing event indicates that a possible black hole magnified the star, causing an increase in brightness.
Hi, I'm going to be talking about stellar evolution today. It begins with the gravitational collapse of a cloud of gas and dust, forming a protostar. Once nuclear fusion ignites in its core, the star enters the main sequence phase, where it spends most of its life fusing hydrogen to helium. The larger the star, the shorter amount of time it will spend in its main sequence phase. As the hydrogen depletes, the star evolves into a red giant or a super red giant, depending on its mass. Low to medium mass stars eventually shed their outer layers and become white dwarfs, which are the center of a planetary nebula, while massive stars may explode in supernovae, leaving behind neutron stars or black holes, depending on their size. Stellar evolution plays a critical role in enriching the universe with heavier elements and shaping galaxies.
So what is a black hole? A black hole is a celestial object whose gravitational force is so strong that it creates a region of space-time where nothing can escape, not even light, once it passes through the event horizon. As hot gas and dust spiral as a result of the black hole's strong gravitational force, a glowing accretion disk is formed. Also, some black holes launch powerful jets of energy perpendicular to the accretion disk at nearly the speed of light. As a result of their strong gravitational fields, black holes and even other massive objects can cause microlensing.
But what is microlensing? Microlensing occurs when a massive object such as a black hole or a lower mass object like an exoplanet passes momentarily in front of its companion star. Due to the extreme mass of the black hole, the fabric of space-time is warped and acts as a magnifying glass. This causes the star behind the black hole to appear brighter. When the companion star, massive object, and telescope are lined up, photometry sensors simulate a light curve with an extreme peak in brightness and returns to normal.
For our data, we focus on two primary observatories. First, we use data from the Transiting Exoplanet Survey Satellite, which is a satellite-based telescope system equipped with 4 cameras designed to observe regions of the sky with lower star density. This data is available on the citizen science project Black Hole Hunters on Zooniverse. Our second observatory was the Optical Gravitational Lensing Experiment, known as OGLE, located in Chile. OGLE is a ground-based telescope specialized in observing regions with high star density, particularly the galactic bulge.
We used photometric data from the TESS satellite to analyze around 9,000 unique light curves, graphs representing variations in stellar brightness over time. Gravitational microlensing events produce a symmetric and isolated peak in the light curve, as the lens temporarily magnifies the light from the source star. This characteristic peak was the primary feature we were looking for. Because microlensing events are extremely rare, we had to filter through several types of non-microlensing signals, including simulated light curves used for machine learning, light curves with significant data gaps, graphs with instrumental noise or stellar variability, and planetary transits with periodic luminosity dips.
This graph is an example of an unidentified event. The graph presents a linear brightness that peaks and then returns to its normal brightness. A few days later, another peak appears and then once again returns to its normal brightness. When we come across such graphs during classifications, we simply marked the peaks and moved on, allowing for astronomers to easily identify the graphs with peaks and spend more time on classifying the event.
Using the equations governing microlensing, we wrote some code using matplotlib to understand how different variables affect the light curve. Variables like the mass of the lens or the distance between the lens and the star affect the light curve. The first equation, AFT, represents the amplification of light due to the lens. At the peak of the light curve, you can also see when the star and the lens are close to alignment to amplify a lot of light. UFT then represents the angular separation between the star and the lens, and TE, which is the Einstein time, represents the time of the microlensing event. So one of the first variables that are important is the mass of the lens. When we increase the mass of the lens, we can see that the Einstein time, or the time of the microlensing event, increases. But when we decrease the mass of the lens, the time of the microlensing event decreases. And this is because when the mass is larger, it's able to bend more light and increase the time for microlensing. Another important variable is the impact parameter, which is how close the lens passes to the line of sight of the star. When we increase this impact parameter, we increase the separation between the lens and the star, and this decreases the peak of this light curve, which also decreases the maximum amplification. And this is because a lot of the light gets scattered around because of the large distance. But when we do decrease the distance between them, a lot of the light is focused by the lens and gets bent, causing a much higher peak. So now that we understand how the light curves work, we wanted to know how we can actually do more and estimate the mass of the candidate microlensing objects and figure more about the test candidate black holes.
To estimate the mass of the lensing object, we first started with the equation for the angular Einstein radius. The Einstein radius is the radius of the light ring in the sky that is created by gravitational lensing. Then, using algebra and substitution, we derived the equation to find the mass of the lensing object based on some parameters. The parameters are ds, the distance in kiloparsecs from the observer to the star, dl, the distance in kiloparsecs from the observer to the lens, or in this case, the black hole, v, the transverse velocity of the lens relative to the observer, m, the mass of the lens, and te, the Einstein time of the event.
Okay, let me walk you through how our simulation works to estimate the mass of black holes using microlensing. At the core of our simulation is the equation, which you saw in the previous slide. It allows us to calculate the mass of a lensing object with different parameters. But instead of plugging in just one set of values, we wanted to understand the range of possibilities. So we developed a Python-based simulation that essentially maps out a galaxy's worth of scenarios. We start by modeling our line of sight toward the galactic bulge. This is a dense, star-packed region at the center of the Milky Way, where most microlensing events are observed, and where most of the OGLE dataset originates from. Earth is about 8 kiloparsecs from the center of the galaxy, so we assume stars we might observe are between 2 and 6 kiloparsecs away, positioned somewhere along that line of sight. For each of those possible star positions, we simulate black holes located between Earth and the star at distances ranging from 1 kiloparsec up to just under the star's distance. This is because the closest black hole to Earth, Gaia BH1, is no closer than 1 kiloparsec away. This way, we split the galaxy into a grid of physically valid lens source distance combinations. Using Python for each pair, we calculate the lens mass using our equation, holding the Einstein timescale constant and estimating transverse velocity using a simplified galactic rotation model. For example, imagine a star located 6 kiloparsecs away. We try black hole positions at 1, 2, 3, 4, and 5 kiloparsecs, and compute the resulting mass in each case. Then, we repeat this entire process for stars at 5 kiloparsecs, then 4, and so on. The result is a complete matrix of theoretical black hole masses that could have caused the microlensing event we observed. This diagram on our slide helps visualize that idea. Every dot in this grid is a possible lens source combination, and the simulation computes the mass associated with each one. Instead of just solving the equation once, we're creating a mass map of possible configurations.
So from our simulation, we took the max mass value from our mass interval, and using the OGLE data, we got the peak magnification factor for all of the microlensing events. Given our mass interval range from our simulation for the lens, we checked if the max value was greater than 2 solar masses, the minimum theoretical mass of a black hole. We then took those points and saw there were 44 out of 545 microlensing events which were possible black holes. From this, we then plotted the max mass of all the lenses from our simulation against the peak magnification factor, which is the maximum brightness amplification during microlensing. From our simulation, we can now see a 4th-degree relationship between the log of the max mass of the potential lens versus the log of the peak amplification factor. This makes sense because as the lensing object's mass increases, it produces a stronger curvature in space-time, causing more light from the background star to be bent, which leads to a higher magnification during the microlensing event. On the graph, you can also see the line x equals 2.5 solar masses in green. And to the right of that line, those are all the potential black holes that we found. And on the bottom, you can also see the 4th-degree regression between the maximum amplification factor and the potential mass.
Now, let's go over the limitations of the model. One of the limitations of our model is that we use the velocities of the Milky Way rotation curve to calculate the relative transverse velocities of the lensing object and the source star. Another limitation is that we assumed that we were always going to be looking towards the galactic bulge. This was to simplify the model.
From the test data, we found 5 microlensing candidates. Using the simulation, we found that the first candidate had an estimated mass of 4.63 times 10 to the negative 4, which is in the mass range of a gas giant. This graph has a very clear peak, so it is a strong microlensing candidate. The second graph had an estimated mass of 7.41 times 10 to the negative 5, which is in the mass range of a giant planet. In this graph, there is quite a bit of noise before and after the peak. However, the peaks are fairly symmetric and clear. The third candidate was found to have an estimated mass of 5.4 times 10 to the negative 5, also in the mass range of a giant planet. This graph has a straight peak, which makes it a strong candidate, but it does have quite a bit of noise before and after the peak. But since the peak is so clear, we counted it as a microlensing candidate. Finally, our last two graphs were both calculated to have an estimated mass of 1.29 times 10 to the negative 5, which is a mass range that classifies both of them as planets. Both of these peaks were very consistent and symmetrical. However, the fourth candidate does have a tiny dip when it goes back down, so we are not too sure what it is, but the peak still presents as a microlensing event. All of the masses are in the unit of solar mass. It is important to note that these masses were calculated using our simulation, which presented the most favorable case for identifying microlensing events. We used the maximum value in the simulation. If we used the smallest value in the simulation, our largest mass would become a rocky planet, and our smallest mass would still remain as a small planet, so we would still get realistic results. While the double peak from earlier in the presentation had a clear peak, we were only asked to identify peaked graphs with a single peak by the Scientist Citizen Project.
The comparison of microlensing observation efforts between TESS, OGLE, and the Astronomy Team reveals notable differences in the detection efficiency. TESS has a 0.002% chance of observing a microlensing event, whereas OGLE has around a 0.00002% chance of observing a microlensing event. TESS has looked at around 1 million stars, whereas OGLE has looked at over 200 million stars, which is a much larger sample compared to TESS. TESS has found around 2,100 microlensing candidates, whereas OGLE has found 3,718 microlensing candidates. In contrast, the Astronomy Team had a much higher percent probability of observing a microlensing candidate, at a 0.07% chance, whereas TESS had a 0.002% chance. TESS looked at around 1 million stars and found 2,100 microlensing candidates, whereas the Astronomy Team looked at over 13,000 charts and graphs, but due to duplicates, we only looked at 7,164 stars and found 5 possible microlensing candidates. Microlensing events are rare and difficult to confirm without careful analysis and follow-ups by scientists. Although TESS has already identified some microlensing candidates, the mission is still ongoing, and much of its data has yet to be fully examined. This means the current numbers may only represent a fraction of what TESS might eventually uncover as more data is analyzed and verified.
We were met with a plethora of limitations while searching through the TESS data from the Citizen Science Project. One of the limitations we faced was that there were many variable star graphs that presented as microlensing effects, due to the fact that we didn't have enough time to see the full variations. TESS observes in more than one color in the color spectrum, and if we had access to that information, we could decide if it is a true lensing event. This means that a lot of these graphs require follow-up observations from astronomers. Another limitation we encountered was that there are a lot of graphs within the Citizen Science Project that still need to be classified, so there may be a higher average of microlensing events within those subjects that we have yet to see.
By filtering data for potential microlensing signals through mass constraints and light curve analysis, this approach reduces the volume of data requiring manual inspection and allows researchers to focus on verifying high-confidence candidates. Further research includes obtaining more data about the star to reduce the number of assumed parameters, refining the simulation to look at a broader range of lensing configurations, and extending the simulation to lower mass microlensing events to evaluate the range.
So here are our references.
I'd like to take a moment to share some of our biggest highlights and challenges from our time at SEAS. Let's start with the challenges, because as we all know, growth comes from overcoming obstacles. One of our biggest challenges was learning how to effectively work as a team. With so many different perspectives, it took time to figure out how to collaborate efficiently, communicate clearly, and support each other's strengths. Another challenge was navigating code errors, whether it was debugging or trying to understand unfamiliar code. It pushed us to think critically and be persistent. Lastly, we struggled with finding consistent data. It was a real test of patience and research skills, especially when we were trying to verify the accuracy and reliability of our sources. But now let's switch gears and talk about some of the major highlights of our time that made our experience truly unforgettable. One major highlight was getting to meet people from all over the country. It was amazing to connect with such a diverse group of passionate, driven students. Another unforgettable experience was visiting the Johnson Space Center. Seeing the behind the scenes of NASA's work was incredibly inspiring and gave us a glimpse into what our future in space science might look like. And finally, this program gave us valuable experience for our future careers, whether we go into space, science, engineering, or any STEM field. We're walking away with new skills, more confidence, and a better idea of where we want to go next.
So my experience at SEAS was really fun, and I enjoyed meeting a lot of people from across the nation and meeting people from different cities. I especially enjoyed going to Six Flags in Texas.
My SEAS experience was an amazing journey where I explored datasets and worked alongside passionate peers.
My SEAS experience was amazing. I loved going to the Johnson Space Center and opening up new doors and new opportunities and new ideas for me.
My SEAS experience taught me a lot of new things, and I really enjoyed seeing astronauts in the Natural Buoyancy Lab, and that really opened a lot of new doors for me and allowed me to see a lot of new things that I couldn't see.
My SEAS experience was really transformative. I especially liked going to the Neutral Buoyancy Lab at Johnson Space Center.
SEAS has been an incredible opportunity for me. Over the past 2 months, I've learned so much from completing the program modules to visiting the Neutral Buoyancy Laboratory. These experiences have not only deepened my understanding of space exploration and science, but also helped me clarify what I want to pursue in my future.
My experience at SEAS was amazing because it gave me the opportunity to make connections with professionals and work on real research. Going to the Johnson Space Center in Houston and visiting Mission Control was one of my favorite parts of the internship.
My experience at SEAS has been nothing less than extraordinary. Getting to learn from so many students my age from around the country has been amazing, as they are all so intelligent. I have also enjoyed learning about where my peers are from and their lives outside of SEAS. It was also amazing to learn from so many scientists, engineers, and amazing teachers who are some of the best in their fields. I can't explain how grateful I am for this opportunity. Thank you.
I would like to thank our mentor, Dr. Reese, as well as Ms. Baggio, Ms. Miller, Ms. Tomlin, NASA, the Center for Space Research, and the University of Texas, as well as everyone else who has been a part of SEAS this year. Your guidance, resources, and support have been instrumental in making SEAS possible this year. Thank you.
So we have several questions for the astronomy team. The first question is, did the team encounter any false positives or anomalies during catalog filtering, and how were those handled or flagged in your results?
Okay, I'll take this one. So there were many false positive graphs that we did find when looking through the catalog of graphs. We found a lot of graphs that presented as variable stars, which are stars that don't have a regular brightness. They just will dip and heighten just based off of their activity. So there were many stars such as those that we found, and we at first thought were black hole candidates because they were very clear peaks that we saw, which will present in those candidates. But to filter out through those, we just kind of had to look at the regular level of brightness to see if it stayed consistent or if it was kind of noisy in those graphs.
Is the method of finding black holes the strongest method currently available? How do you think it could be improved in the future?
So I can take this question. So from microlensing, this is kind of just one proposed way for finding black holes. And from our simulation, we kind of find this range of a black hole and the possible mass it could have. And if from our range, if the theoretical mass of a black hole, which is approximately around 2 to 3 solar masses, if it is not in that interval, we kind of say, oh yeah, it's not a black hole. But this is kind of one way we think of finding a black holes. And one way we can kind of improve it is by trying to get more data to try to decrease the size of the interval. And again, this is kind of just one way, and there's probably like a lot of other ways to find black holes. So yeah.
So what mechanisms are believed to drive jets of protons perpendicular to the accretion disk, and how do they escape the black hole's immense gravitational pull?
I can take this one too. So the jets are released from the accretion disk, but the reason they can still escape is because they're released outside of the event horizon, and the event horizon is basically the place in the black hole where not even light can escape. So if you look at the escape velocity, the velocity that you need to the velocity that it approaches is around the speed of light, but not even light can really escape this event horizon. And if you see they're launched at the center of the black hole, and there are two of them that are launched, and that's used to conserve the angular momentum of the black hole. And they're also launched around the center axis of the magnetic of the black hole, because that's where the magnetic field of the black hole is the strongest. And it also allows it to accelerate and escape the black hole's gravity because it's launched from the accretion disk and not the event horizon.
How does varying star and black hole positions in the simulation affect the calculated mass range and microlensing detectability?
Yeah, so I can take this one. Varying the positions of the star and the black hole in our simulation is what our simulation actually does, and that's how we get our output of masses. What this does is it changes the geometry of the system, and this will influence both the estimated mass and how likely the event is to be detected by by the telescopes. So when the positions shift in our simulation, the distance between the observer and the lens and the source change, and that affects how much light bends and how long the lensing event will last. And since we're inputting the lensing event time into our simulation, we can get an approximate mass range. Um, and these changes also impact the strength and duration of the observed signal. Uh, Through our simulation, we saw that the most favorable configuration for a microlensing event is when the star is from the farthest from the observer and the black hole is closest to the observer.
Well, congratulations to every member of your team. You've done an excellent job with your research. Our next team presentation is from Astronaut Photography, led by Rosina Miller, a Jacobs contractor, serving as a research scientist in the Science Engagement Office within Astromaterials Research and Exploration Science, the ARES department at NASA Johnson Space Center. Flor Gomez is the project assistant. So please join me in welcoming the Astronaut Photography team.
Hello, and thank you for joining us for the 2025 NASA STEM Symposium. We are NASA STEM's interns from the Astronaut Photography Research Team, and today we'll be sharing our project on evaluating anthropogenic or human-caused changes on Earth over time using astronaut imagery. My name is Chris Petrapke, and I'm from Northfield, New Jersey.
I'm Kale Manning, and I'm from Caldwell, Idaho.
I'm Lloyd Busby from Huntsville, Georgia.
I'm Parina Gupta from Pleasanton, California.
I'm Liz Aaronkranz from Sammamish, Washington.
And I'm Desiree Gonzalez from Westaco, Texas.
What is astronaut photography? Astronaut photography refers to images taken by astronauts aboard spacecraft, most commonly the International Space Station or the ISS. Astronauts use handheld digital cameras to capture these photos in the cupola, which is a 7-window observational module.
Now, why is it important? Well, astronauts can respond more quickly than automated satellite systems. They can take images of specific events like wildfires, floods, storms, often within hours of occurrence, making astronaut photography a powerful tool for monitoring rapid environmental change. While most traditional satellites take images pointing straight down at the Earth, astronauts can take images from a variety of angles and lenses.
So how do we find change over time? Our photos were collected from NASA's Gateway to Astronaut Photography database and supplemented using satellite imagery. Astronauts take millions of pictures, so we filtered using location, date, keywords, and time of day for city lights. We focused on finding images with low cloud coverage and high resolution from the exact same location and with discernible change.
Now, as said before, anthropogenic change refers to human-induced changes in the environment. Our project studies the impacts of anthropogenic activities including urbanization, light pollution, deforestation, wildfires, aquaculture, and waterway engineering.
Now, I looked into the anthropogenic change in Tokyo, Japan. Layers of street and artificial light cover the Kanto Plain, which contains the Tokyo metropolitan area. This illumination characterizes the growing urbanization, exhibiting the population shift and growth. This pair of images shows the nighttime appearance of the Tokyo metropolitan area from the International Space Station from 2003 to 2021. In 2003, the photograph depicts the high light density in the central urban core and main transportation streets. However, in the peripheral areas within the greater metropolitan area, low light density and dark spaces are displayed. By 2021, the previously dim lit areas and the central urban core are visibly packed with light density, suggesting growth in infrastructure, land, and especially population. The Tokyo metropolitan area's population was approximately 35.1 million in 2003 and grew over the years to reach 37.3 million in 2021. The dramatic increase in Japan's urban population, especially post-2000s, demonstrates a national trend of urban concentration. The rapid population growth required an increase in developed areas. Japan contains areas of high light radiance, with Tokyo standing out as a major contributor to regional light pollution, a consequence of dense urbanization. The new patterns of light showcase the continuous expansion of Tokyo's visible urban footprint. From an environmental perspective, the increased light usage is contributing heavily to light pollution. The high pollution concentration and the use of lights has also led to elevated temperatures. Thus, coming up with solutions to combat the challenges becomes necessary, as some urban planners predict there will be continued densification of the metropolitan area through the 21st century. Now from here, I'm going to hand it over to Lloyd.
For my anthropogenic change, I looked at the Panama Canal, also known as one of the two most strategic waterways in the world. This marvel of engineering is an artificial canal approximately 40 miles or 65 kilometers long. Excavated by the United States in 1904 through 1914, the hollowed-out canal going through the Isthmus of Panama connects the Pacific and Atlantic Oceans, allowing water vessels to easily travel from the two, saving thousands of miles in time. In 2007, construction of a third set of locks began with the purpose of allowing larger post-Panamax ships into the canal. The three photos below show the change over time from before, during, and after the construction. Looking at the photos gives an idea of the process and shows how the surrounding areas have been affected. Furthermore, the canal has also boosted the economy and given Panama the new opportunities to grow. Next, I'll be followed by Kel and his anthropogenic change in aquaculture.
Aquaculture, which has recently attracted investment from Egypt, is the farming of aquatic organisms like fish, shellfish, and plants in controlled aquatic environments. It enhances Egypt's domestic supply and gives Egypt a more self-sustaining stockpile of food, reducing the need for imports and strengthening Egypt's source of more affordable protein. As you can see in the images on the right, the prime example of aquaculture development in the country is the Al Fairuz fish farming project. Along 17 kilometers the coast of the Mediterranean Sea, 5,908 fishing farm basins, each with an area of just under 2 acres, continue to produce over 13,000 tons of fish and shrimp annually. Al Fairuz's innumerable basins lie north of our large concrete production and industrial site east of the Suez Canal. Before construction, the region was composed of salt lakes and wetlands. Contributions to food production through large-scale aquaculture like Al Fairuz hold environmental risks, especially when not managed carefully. The conversion of wetlands disrupts their abilities to store floodwaters, protect and improve water quality, and keep water on the surface flowing during dry periods. Wetlands are relied upon by numerous bird and mammal species for resources such as food, water, and shelter. Furthermore, fish farming facilities can potentially harm marine ecosystems through the leakage of excess nutrients and chemicals into nearby waters. Without long-term measures such as salinity and waste management to function sustainably, projects such as the Al Fairuz could undermine the overall landscape. The next portion will be by Purina.
I studied how the Mendocino Complex Fire, one of the largest wildfires in Northern California, impacted the landscape over time. It ignited on July 27, 2018, and burned 459,123 acres of land. It included the ranch and the river fires, along with multiple smaller spot fires. The ranch fire started when a property owner struck a rock with a metal stake while trying to plug a yellow jacket nest underground. The cause of the river fire remains unknown. The image on the left was captured from the ISS and shows an active fire within the complex on August 4, 2018. The fire occurred in the wildland-urban interface, which is a zone where human development meets wildland vegetation. This overlap increases fire risk, especially when dry vegetation and hot summer winds accelerate fire spread. The two Terra satellite images shown were taken by the MODIS instrument and reveal landscape changes between 2011 and 2019 before and after the fire. The earlier image shows a landscape dominated by healthy forest and grassland, while the later image shows burn scars and exposed soil from the fire. The Normalized Difference Vegetation Index, NDVI, which ranges from -1 to +1, measures vegetation health. Higher values indicate healthier vegetation. NDVI maps show a drop in average values from 0.33 pre-fire, indicated by green patches, to 0.09 post-fire, indicated by brown-red patches. This indicates severe vegetation loss. Beyond vegetation, the fire also destroyed 280 structures, including 157 homes, killed 1 firefighter, and injured 4 others. It also burned through forested areas surrounding Clear Lake. While the lake itself was untouched, runoff likely carried ash and debris into the watershed, affecting water quality and aquatic ecosystems, as has been observed in other fires near coastal regions. Now I'm going to hand it over to Liz.
Thanks, Parina. I researched change over time at Kutupalong in southern Bangladesh, which is the world's largest refugee camp. It has nearly 1 million inhabitants, over half children, with 800,000 arriving in August 2017 after a wave of violence against the Rohingya people, a Muslim ethnic minority of nearby Myanmar. The resulting expansion was visible from the ISS, as seen in these stacked images that depict the land before and after expansion. The camps are extremely densely packed, and structures made of bamboo and tarp provide minimal protection from floods, landslides, cyclones, and monsoon rains, which can occur multiple times each year. Now, this rapid development has also highly impacted the surrounding environment. This is a zoomed photo of camp roofs in 2023, and its effects are visible in the ecological condition map of the same area on the right. The camp is also built on the endangered Asian elephant's migratory route, leading to attacks on both sides. A study from a university in Bangladesh found that an 8% increase in settlement area brought an almost 10% decrease in forest area. This leaves the region unprotected and further susceptible to desertification and severe floods, while overused wells deplete groundwater and affect vegetation. Deforestation has also led to a 14.6% decline in biodiversity. The camp population is currently relatively steady, but these environmental and humanitarian challenges persist due to limited aid and no safe place for the Rohingya to return to. Next, Desiree will be sharing her project.
I researched change over time on Florida's unique coastal environment. This territory is shaped by constantly shifting sediments, primarily composed of quartz sand and calcium carbonate, essential for maintaining water quality and supporting marine life. Over the past decade, Florida has experienced a sharp increase in urbanization, particularly in southeastern regions fueled by population growth, tourism, and coastal development. This surge, averaging 1.4% annually between 2010 and 2020, has disrupted natural sediment processes and increased runoff into coastal waters. NASA images of Suwas Point from 2009 and 2017 visually capture this transformation, showing how unchecked development contributes directly to sediment buildup and environmental degradation on the Florida coast. The 2020 U.S. Census map below highlights this growth trend, showing how major metropolitan regions such as Miami-Fort Lauderdale, with over 6 million residents, contribute to increasing pressure on Florida's fragile coastal systems. Additionally, the graph located on the right displays a steady rise in Florida's resident population from 2000 to 2034, with a noticeable spike in growth during the 2010s, when population climbed rapidly from 18.8 million to over 20.4 million residents. This urbanization impacts the environment by disrupting natural sediment movement, smothering seagrass beds, and degrading coastal ecosystems. As development continues, habitats like coastal uplands face the risk of losing nearly half their area by 2070, threatening biodiversity and weakening natural storm barriers. In conclusion, when observing Earth from space, the impacts of human activity are visible on a global scale, from Bangladesh in South Asia to Panama in Central America. Anthropogenic changes affect nearly every community and environment.
While some of these changes may offer short-term benefits, the continued, unchecked expansion of human influence on natural systems has already led and will continue to lead to significant long-term consequences. Earth observation from space provides essential context for us understanding the extent and impact of these transformations on the planet's systems.
When researching information for our project, we found that some of the hardest tasks were finding photos and data sets to match our topics. There are thousands of photos that have been collected and documented over the last few decades on the Gateway to Astronaut Photography of Earth website.
Filtering through the images to find two or more that depict the same exact coordinates over a sizable time period proved to be quite difficult. In addition, some of our topics required very specific related data that took a while to find to help explain what was going on.
Now we've had a lot of memorable experiences throughout these 2 weeks, from touring the Neutral Buoyancy Lab, the Johnson Space Center, and intense high-spirited card games. We've also had the incredible opportunity to meet astronauts, engineers, and professors from all over the country.
Looking back, every single moment has expanded our knowledge in STEM. These 2 weeks have led to an unforgettable and enriching internship experience.
NASA SEAS was truly a life-changing internship. From learning how to write my first scientific article to expanding my social skills by meeting just under 100 interns and mentors these last 2 weeks, NASA SEAS has tested me in every aspect.
The NASA SEAS internship has been a transformative experience. This program has expanded my professional network, deepened my passion for STEM, and opened doors to opportunities that I once thought were out of reach.
Although I've learned a lot about aerospace, this program has also shown me the breadth of intersecting fields and amount of collaboration that goes into any space venture. It's motivating and inspiring to know that no matter what I end up pursuing next, there is a place for my interest in space.
Having the opportunity to be a part of the NASA SEAS internship was a remarkable experience that has positively challenged me in both academic and social aspects.
SEAS was an amazing experience. I've learned so much and I'm so grateful for all the people and knowledge I have gained.
Throughout the 2 weeks of SEAS, I've had an incredible experience, bringing me out of my comfort zone and teaching me so much. I am so thankful for the opportunity and for the amazing people I got to meet.
Thank you to our mentors, Rosina Miller, Florestella Gomez, Margaret Baggio, Selena Miller, and Laura Tomlin. We also want to give a big thanks to SEAS, NASA, Center for Space Research, NASA Johnson Space Center, and the University of Texas at Austin. Finally, thank you to everyone in the audience here that has supported and listened to our presentation today.
Thank you!
So we have several questions for the astronaut photography team. So please unmute your mics and turn on your cameras. The first question is, how does an astronaut plan shots in advance given the rapid speed of orbit and limited visibility window?
Yeah, I can take this one. So the ISS orbits Earth every 90 minutes, so time is essential when taking photographs from the ISS. And the way astronauts plan their shots in advance is by using daily target lists that are prepared by Earth scientists on the ground. And these lists contain detailed information about the exact locations where astronauts will pass over, including the times that they'll pass over that location. And they also include details on which camera settings and camera lenses to use based on the altitude and the lighting.
Great. How did the team quantify visual changes in urban growth, agriculture, and deforestation over time from the photographs? Was any image analysis software used?
Okay, so I can take this one. So from just seeing the astronaut images, you can't really get like quantitative data, but you can like find the scales of certain locations using like outside resources, and you can like apply trends, and you can see graphs, and you can see like specific quantitative data over time using like those charts. But just from those specific astronaut images, it's really hard to just derive quantitative data from them.
And what tools or camera settings are most effective for capturing surface features like storms, volcanoes, or even city lights from space?
I can take this one. So, astronaut photography uses tools such as handheld cameras with various lenses and within the International Space Station through their seven-window cupola. They use like a variety of lenses such as telephoto lenses, wide-angle lenses, and fast lenses, which allow astronauts to capture high-resolution images and data from various angles under different lighting conditions and cloud coverage.
How did the team select which astronaut photos to analyze from the full database, and were any filtering criteria used?
I can take this one. So during the researching process, we already had a general idea of what we wanted to look into. And then so we got to use the NASA's Gateway to Astronaut Photography tool. And through that tool, we were able to search for specific images by looking up the topic. For example, if we wanted to look up a wildfire, we could look up wildfires for astronaut photography. And then we could even break it down, like filtering it more to specific locations. And there was even a map that had multiple location pinpoints to choose from, and that helped a lot for looking for images.
How consistent is astronaut photography in comparison to satellite imagery? For example, through areas captured, angles captured, rate captured, things like that.
Yeah, I can take this one. So in terms of angles, most satellites are like nadir pointing and only can take photos of things right below them. But astronaut photography is more irregular in its angles, which can actually be a useful thing when viewing like the topography or just different features. And then in terms of frequency of photos taken, astronaut photos are less frequent just because it's like an actual person taking it. But that also means that what they're choosing to take photos of is probably going to be more intentional and like specific.
Did the team encounter inconsistencies in lighting, resolution, or image distortion between photographs, and how were those addressed during comparisons?
I can take this question. Speaking for the team, I know that we all encountered many inconsistencies from lighting resolutions, eye-catching pictures, and anything that blocks the surface, like clouds and smokes, was very common, blocking what we were looking at. To address this, we made many like limitations, as in we looked at time frames, size of the pictures, and the different qualities that were available.
Great. Well, you've done an excellent job, and congratulations on your research. Our next team presentation is from the X-59 team led by Rhonda McCarthy, a STEM educator from Iowa who is passionate about involving students in real-world space research. She believes that young learners hold the key to addressing future challenges both in space and on Earth. So please welcome the X-59 team and their project, X-EOS.
Hi, I'm Emma.
I'm James. I'm Kenan.
I'm Charlotte.
I'm Dharma.
I'm Katie.
I'm Ashita.
I'm Chris.
And we are the X-59 team.
And this is X-EOS, an aerodynamic design and analysis of a low-boom supersonic commercial airliner.
To provide context, we'll begin with a brief background on supersonic commercial flights. The Concorde was introduced in the 1970s, turning the idea of planes traveling faster than sound into reality. However, supersonic flight creates a sonic boom, and the Federal Aviation Administration, or the FAA, had already banned it over land due to disturbances it brought to nearby communities. The Concorde was limited to flying supersonically over oceans, but it still created disruptions, and after a fatal crash, it ceased operations in 2003.
The interest in supersonic commercial flight continued in 2016 when NASA and Lockheed Martin began the Quiet Supersonic Technology, or QUEST mission. Here they began the design process for the X-59, a single-seat supersonic aircraft designed to mitigate the sound of a sonic boom into a light sonic thump. This year, they plan to fly the X-59 for the first time and collect data from communities about the perceived sound level of the thump. Meanwhile, a company called Boom Supersonic is creating a similar aircraft. These include the XB-1, which flew out for the first time in January, and the Overture, a supersonic commercial airliner that is expected to take flight in 2029.
The X-59 was designed with many features to minimize the sonic boom. Notably, the long flat nose is crucial in this role because it shapes the way the shockwaves are formed. The plane's needle-like design doesn't leave room for a traditional windshield, so the aircraft uses an external vision system, or XVS, for pilot navigation. This system includes a camera on the nose and a high-resolution monitor in the cockpit. Additionally, the fixed canards prevent the shockwave from coalescing into a single wave, thus reducing the overall sound signature. The X-59's engine, although taken from an FA-18 fighter jet, is uniquely positioned on top of the fuselage in order to redirect the exhaust shockwaves upwards. The narrow wings, similarly to the canards, serve to shape and disperse the sonic boom, and the T-tail is used to minimize the aftershock.
The Quest mission will be carried out over 3 phases. During Phase 1, Quest built and designed the X-59, conducted ground tests, and will fly the plane for the first time. During the second phase, the team will focus on acoustic validation, or how shockwaves form and move through the atmosphere. This testing ensures that the X-59 is ready for the third phase, which is community response testing. During these final tests, it will fly over communities, and then a survey will be shared with residents to collect qualitative data about the perceived noise levels and the general disturbance. The main goal of these tests is to inform future policy on supersonic flight, since the X-59 itself will never be in mass production. Our goal with this research project was to use the technology from the X-59 to develop a prototype of a quiet supersonic airliner. We determined that designing a commercially viable prototype inspired by the X-59 would provide the most valuable contribution to the future of the Quest mission. We chose to name this aircraft the X-EOS, combining the X from the X-59 with ecos, which means sound in Greek. Together, the name means no sound.
We began pursuing our goal by researching the X-59 and analyzing the previously mentioned technologies. Based on our research, we were able to determine how exactly each feature mitigates the sonic boom and how we can employ these into our CAD model. So we designed the X-EOS in Onshape, and we kept most of the main features of the X-59, but we did make a few changes for commercial scaling, namely the widened and elongated fuselage and adding another engine. We estimated that our prototype can hold around 175 to 200 economy seats with an overall length of 60 meters, which is pretty similar to a large passenger jet like the Boeing 767. The model also allows us to conduct CFD and other tests to see how well the X-EOS mitigates the sonic boom. In the future, we're hoping to take these results and then further refine our model to minimize shockwaves.
We decided to validate the X-EOS's aerodynamics and shockwave generation using computational fluid dynamics, otherwise known as CFD. We began with OpenFOAM 11, looking to simulate supersonic compressible flow. We chose to simulate this since the supersonic shockwaves are caused by the buildup and compression of air at the nose of the plane. However, we realized as we continued development that it would take days for any useful qualitative or quantitative data to be generated. So, we decided to switch from OpenFOAM to SimScale. It was a much simpler software to use, but we were limited to simulating subsonic incompressible flow. That's just typical aerodynamics and nothing to do with shockwaves. On top of that, we still wouldn't have time for the mesh generation, let alone running the actual simulation.
We began developing mathematical models derived from 3 equations: the Reynolds number, Berger's equation, and Euler's equation. The Reynolds number is found using a relatively simple algebraic equation and is used to describe airflow around an object. Typically, for an object with a Reynolds number below 2,300, flow is considered laminar or smooth. For any number higher than 3,500, it's considered turbulent. Numbers in between describe transitional flow, or flow that may be both turbulent or laminar. We found the Reynolds numbers of the X-59's wingspan at both supersonic and subsonic speeds and found them to be 2.25 times 10 to the 7th and 4.8 times 10 to the 7th, respectively. This tells us that the flow around the X-59 is very turbulent and that viscosity is less significant than inertia in this scenario.
The insignificance of viscosity within our calculations helped us remove some variability within our mathematical modeling. As such, we proceeded to use the envisaged Berger's equation to measure the sonic boom's shockwave propagation from the aircraft to the ground. We used Python code to run our simulations, including the consideration of atmospheric absorption, and used high-order differentials to model the weakening of the N wave, a type of waveform of the sonic boom characterized by a rapid rise in pressure followed by a gradual decay. We were also able to generate visualizations pertaining to the ground sonic boom signature, as well as its ground frequency, enhancing our understanding of how the shape of the sonic boom can be optimized to minimize community disturbance.
Additionally, we used the exponential decay equation to mimic data you could produce from Euler's equation. We used various measurements such as the plane's length, wingspan, surface area, altitude, free stream Mach number, and atmospheric pressure and density. We use this data to create a MATLAB code to develop a mathematical model displaying sonic boom profiles to compare the X-59 to the X-EOS on MATLAB.
In the graph to the left, we can very clearly see the aggressive changes in pressure from the shockwaves. This is very similar to the N-shaped signature you would see from a supersonic aircraft, with large shocks at the front and tail ends of the plane and very dramatic changes in pressure. For the X-59, however, these changes are much less dramatic. There are still distinct changes in overpressure as position increases, but they're smaller and more frequent. This means that instead of the two large booms of a typical supersonic aircraft, people on the ground would hear many quieter thumps in quick succession. Because we weren't able to fully simulate pressure signatures for the X-EOS, we assumed that having the X-59's features would cause the pressure data to be similar, although it can be inferred that its signature would have a larger amplitude due to its increased size.
Shown here are two plots that detail how the X-59's sonic boom changes as it travels from the aircraft down to the ground. The first graph illustrates the shape of the boomed pressure wave at several stages as it propagates downward. At higher altitudes, the wave is sharper and more pronounced, similar to what you might expect from a classical N wave produced by a supersonic plane. As it nears the ground, the wave clearly becomes smoother and overall jumps in pressure get smaller, showing the thump gets softer as it descends. Similarly, in the next graph, we track how the largest pressure spike or peak overpressure and the average energy, or the RMS overpressure, both steadily drop as the boom gets closer to the ground. This happens because the air absorbs some of the energy and the wave spreads out, so people on the ground hear something much less noticeable than a traditional boom. And finally, we have the last figure, where we can see that most of the energy in the X-59 sonic boom at ground level is concentrated at lower frequencies. This tells us that the boom loses its sharp, high-pitched character, reinforcing our understanding of how the sound from the X-59 travels.
The figure shows the sonic boom profile displaying how the pressure changes as the sound wave travels. Our prototype begins with a higher initial pressure, around 700 pascals, compared to the X-59's 400 pascals, primarily because the prototype is a longer aircraft. However, the X-59's pressure decays more gradually over distance due to its sleeker, more aerodynamic design, while the prototype's decay is steeper and more sudden. As a result, the large size of the prototype creates a stronger initial boom, but the pressure drops off more quickly than in the X-59.
To gauge public interest in flying at supersonic speeds, we conducted a survey. The survey contained general questions about supersonic flight, environmental impacts, and potential acoustic disturbances. We found that respondents in education and business sectors demonstrated higher comfort with supersonic flight and having no windows, if provided with high-quality screens. Within our data, there was a trend between feeling comfortable with radiation exposure and being accepting of minimal windows on a supersonic aircraft. Individuals who responded this way reported higher overall comfort levels with supersonic flight. While many survey participants voiced concerns about key issues, the trend in our data was positive towards flying supersonic. While our survey was not statistically significant or randomly distributed, it supports a public interest in continuing our research, and we'd appreciate it if you could scan the QR code on the screen and provide your opinion.
One major challenge we faced regarded the trade-offs that came with including canards and other protrusions on the aircraft. Drag affects aircraft differently at subsonic and supersonic speeds, so the impact of these protrusions will vary too. During subsonic flight, drag increases parabolically, while at supersonic speeds, drag increases linearly, and wave drag is introduced due to the creation of shockwaves. Drag can be minimized when flying subsonically by smoothing out the body of the plane, while drag in a supersonic flight is minimized by preventing shockwave coalescence with various features like the T-tail or canards mentioned previously. Because of this contrast, it is difficult to create a design that's optimized under both conditions.
We came up with two potential solutions to this. The first is to have retractable canards. A mechanical system would retract them into the fuselage when subsonic to reduce drag and extend when supersonic to break up shock waves. The main drawback is that additional mechanical systems generally require more maintenance and are more prone to malfunction, a result of overall having more moving parts.
Another solution to the drag mitigation contrast is to create morphing wings using shape memory alloys. Shape memory alloys are materials that can assume different shapes at different temperatures. When the plane equipped with these alloys increases altitude, this is required for supersonic flight, the temperature will decrease and the material will change shape and aid in reducing the magnitude of the sonic boom. Shape memory alloys are particularly beneficial because they are often in wider than alternative solutions, and they can allow for similar shape-changing mechanisms. Even so, these materials are more prone to structural fatigue, meaning that with constant bending over time, they will lose some function, even become more prone to breaking and require more maintenance. This would contribute to the already high price tag.
As we continue our research, we've identified several pathways to further our understanding of the X-59 and improve upon the X-EOS. One of those is about radiation. Flying at higher altitudes increases exposure to ionizing radiation, especially for pilots. At 35,000 feet, frequently flying pilots already face up to an 87% increase in some cancers. At 65,000 feet, those numbers are likely to climb, and there is an additional risk of solar flares. For example, in a California to London flight, the X-EOS would complete the trip in about 5 hours compared to 10 hours by a Boeing 737. But the pilot would absorb over 10 times the radiation dose than the one in the Boeing. In future models, we could consider structural composites, embedding with shielding materials like barium sulfate, lead, or other heavy metal alloys to reduce long-term health risks.
Another consideration we have for future efforts is improving upon our design of the X-EOS. When we first designed the aircraft, we only modeled the outer geometry because it opened avenues for CFD and mathematical modeling, and it was much more time efficient. Now that we do have the main body, we can continue to iterate and improve upon our design. We plan to create a higher fidelity model with improvements like landing gear, a rough interior cabin, estimated mass properties, and exploring retractable features. We're also hoping to fine-tune our shock minimizing geometry as we continue our CFD and mathematical models.
As we continue with our research, we will be able to get a variety of numerical data sets from various speeds and altitudes. This additional data will also allow the mathematical modeling to be vastly improved in terms of depth and accuracy. We will be able to simulate the supersonic compressible flow, subsonic incompressible flow, and shockwave generation of the X-EOS. We will also be able to simulate how differing atmospheric conditions would alter shockwave propagation through urban, suburban, and rural settings.
I feel like I learned so much about myself, aerospace engineering, and what it means to do STEM research as a whole. I had an unforgettable experience, and I'm incredibly grateful that I got to be a part of SEAS 2025.
My favorite part about SEAS has been meeting new people and being able to contribute to a project that can have real-world applications in the near future.
The NASA SEAS program has not only allowed me to collaborate with like-minded individuals, but also communicate and learn from aerospace professionals to see real-world applications of engineering, while having fun and developing meaningful relationships along the way.
This internship has been an incredible experience, and I've made lifelong friends. All of the activities that we did together as a team were amazing, and the experts that we talked to were super helpful and inspiring.
My favorite part of SEAS was getting to work on a team of people who are just as passionate about this project as I am. I learned so many things, I gained so many skills and so much knowledge that I will be able to take with me for the rest of my life and through the rest of my career.
Coming to SEAS has allowed me to meet so many incredibly smart people, from other students my age all the way to high-level professors. What I've learned here will not just stay here, it will carry through me in everything I experience from here on out.
I've really enjoyed SEAS because of all the experiences we've been able to have and the just amazing people I've been privileged to speak with. Getting to tour JSC and getting a behind the scenes of prototype rovers from Mars was incredible. And being able to speak and listen to such knowledgeable people like Dr. Crosby and Mr. Christopher Maddie was an amazing privilege.
I'll forever be grateful to SEAS, not just for the breadth of opportunities it's allowed me to pursue, but for allowing me to grow, to not just envision the future, but become it.
We would like to first thank the NASA STEM program and UT Austin for providing us the opportunity to explore for future careers in STEM.
We would also like to thank Dr. Kevin Crosby, Mr. Chris Maddie, and Dave Berker and April Lynette from the Quest team for providing their time and assistance in navigating our doubts and guiding us through our troubles.
At last, we dedicate a special thanks to our mentor, Ms. Rhonda McCarthy, for supporting us each and every step of the way.
Thank you.
So congratulations to the team. We have several questions. The first question is, what criteria or equations were used to estimate sonic boom impact levels in different geographic regions?
Yeah, so I can take that. For the basis of our research, we basically used your typical sound propagation models, like for the Burgers equation to measure shockwave propagation from the aircraft to the ground. We also use Euler's equation for like near field shockwave formation, and then Reynolds number to verify laminar versus turbulence flow. And so at 65,000 feet, atmospheric variables such as temperature, humidity aren't necessarily a factor because just have how little variability there is. So for the geographic thing, that's kind of more like future research in terms of how the sonic boom reaches the ground and how it's absorbed by like rural versus urban areas. But in terms of how it propagates or how it forms at that altitude, it isn't much of a concern.
Would supersonic planes be more or less equipped to face things such as storms or turbulence when flying?
I can take this question. When traveling at subsonic speeds, the plane would be basically the same as any other subsonic plane. However, once we get to supersonic, storms and turbulence aren't as big of an issue because we're traveling subsonic at 65,000 feet. That would be far above any weather, so that wouldn't really be a concern. And with turbulence, once we break the sound barrier, turbulence is really eliminated and it would be a pretty smooth flight just because you're traveling faster than the speed of sound and the air.
What materials and systems were most efficient when building your supersonic airliner, and how would the result you got influence your future research?
So I can take this question. The materials that were mainly built for the X-59 were graphite epoxy laminates, which is essentially just little layers of really thin layers of material stacked on top of each other. They did this so that they can maintain the structure but keep it as light as possible because the nose does need to be very light, especially compared to the back half of the plane where it gets very hot. So they have to use titanium and other alloys that are going to be able to withstand the air and the heat at the altitude. In terms of our actual design, we didn't think too much of materials, but that is going to be definitely a future consideration. Essentially, we're going to look at a lot of alloys, the standard aluminum that is used for commercial planes right now, and then of course the graphite epoxy laminates for the nose specifically, and any other high shockwave producing areas such as the canards and the wings.
What specific aerodynamic principles or models did the team reference when analyzing how the X-59's design reduces shockwave intensity?
Yeah, so I can take this one. So we specifically looked at drag, and we looked at how the different kind of protrusions and stuff on our aircraft could potentially increase drag and how much thrust we would need for that and how that would compare. And we took into account all the factors such as the altitude we were flying at, the speed we were flying at, the temperatures at that altitude and things like that. We also looked at different equations such as Reynolds, Euler's, and Burgers, which I think Sheeta talked about earlier. Yes, those are the specifics.
Great.
I can
Did
add
the
on a little
team-
bit more to that question.
Sure.
So, well, for the shockwave mitigation, mainly it was like the nose that we talked about, the canards and like the little protrusions on the wings. If you look at the wing, it's not completely flat. It's like it has a little bump at the very end. So that also just helps with, minimizing the drag or minimizing the shockwave. We also looked at, as we're kind of early on, we looked at using variable sweep wings. So planes like the F-14 from like decades ago, it'll have wings that look almost like this, like a commercial airliner, where they'll go really wide out, and that helps produce more lift at low speeds and taking off and landing. And then as it flew faster and faster, the wings would come in like this, and it would look almost like an arrow. That's when it went supersonic, or even like, it really could help it go up to Mach 1, Mach 2, really fast, just because it minimizes drag.
Great. Well, your team did an excellent job with their research. We are going to take a short break. We're going to reduce the amount of break time due to our glitch in our system this morning. We will come back at 1:20 for session 2 of the SEAS Science Symposium. Please enjoy highlights from the student accomplishments during the Earth and Space Science course, and thanks to Angelica for scoring and preparing these highlights. So welcome back for session 2 of the SEAS Science Symposium. Our next presentation is from the Texas Atmospheric and Space Research Team led by Melissa Poore, a classroom teacher and also representing NASA SCAN, Twigs Lab, and ISS National Labs, along with Nick Pugh, a telecommunications specialist. The project assistant for the TASR team is Chris Demukes. So please join me in welcoming the TASR team with their presentation on flood prediction using high-altitude balloons.
Hi everyone, we're a part of the Texas Atmospheric and Space Research Team here at NASA SEAS, and today we'll be presenting our project on using high-altitude balloons in Texas to predict floods.
I'm Alejandro Becerra, and I'm from Odessa.
I'm Mike Cavers, and I'm from Houston.
Hi, I'm Meg McMillan, and I'm from Chicago.
My name's Bella Pham, and I'm from Houston, Texas.
Hello, I'm Dishita Singh, and I'm from New Jersey.
Hi, I'm Emma Zareen, and I'm from Northern Virginia. Now for our mentors, we had the absolute privilege of working with Ms. Melissa Poore, Mr. Chris Demukes, and Mr. Nick Pugh. We're incredibly grateful to our mentors for all of the guidance, hard work, and dedication they've committed to this project.
Throughout our project, we aim to answer 2 core questions. To what extent are high-altitude balloons effective for predicting floods and extreme rainfall? And how can these balloons improve early warning systems to keep communities safe? Earlier this month in Hunt, Texas, a flood along the Guadalupe River took the lives of over 100 people across the state of Texas, including 27 girls from Camp Mystic. Furthermore, rescue efforts were delayed by heavy rain and risks were underestimated as a result of normalcy bias, which is a human tendency to underestimate the likelihood or impact of a potential hazard or negative event. In this project, we aim to understand how high-altitude balloons can improve existing warning systems, overcome normalcy bias, and invent new systems for flood detection.
Now, this issue isn't just about technology. It's deeply connected to policy and funding decisions. First, the National Oceanic and Atmospheric Administration, or NOAA, and the Federal Emergency Management Agency, or FEMA, faced severe budget cuts, which reduced the number of daily weather balloon launches in Texas from 11 to 6. Rural communities are left with massive blind spots in monitoring, making them more vulnerable when floods hit. Second, recent disasters show the real impact of underfunding. In the 2021 Texas floods, damages exceeded $1 billion and emergency response was delayed. And most recently in Hunt, Texas, 27 campers were found dead at Camp Mystic due to the recent floods, and 180 people were found dead statewide. Our team saw this as both a technical and policy problem. Expanding high-altitude balloon systems could provide a low-cost, high-coverage network.
High-altitude balloons collect atmospheric data like moisture, which helps predict rainfall intensity and flood-affected areas. But currently, there are only 6 of the 11 balloons that are usually launched twice daily in Texas, leaving rural areas unprotected. There was only 1 balloon in the 200-mile radius of recent floods. Current systems such as radar, satellites, and river gauges are used to predict floods and monitor weather, in addition to weather balloons. But as we can see on the right picture of Texas, that these weather balloons leave a lot of gaps, especially in rural areas. And these gaps can be complemented and aided in forecasting from high-altitude weather balloons.
Before launching our balloon, we followed the preparation procedures on the ground.
So we had several goals in this project. We wanted to improve flood and heavy rainfall forecasting, detection, and warning systems by building cheap and accessible high-altitude balloons, applying satellite data from satellites such as GRACE to identify high-risk flood areas, and partner with agencies like NOAA to make warnings and predictions more accurate. Through all of this, we hope to overcome the normalcy bias that plagues communities so that people are able to take action sooner in the event of emergencies.
To prepare, we practiced soldering electronics, including Bob Twick's invention, the Jiggy, designing and coding Arduino systems, and holding virtual team meetings to learn more about the project and develop skills that would be needed for us to have the most productive 2 weeks possible. These experiences were crucial in sharpening our technical and teamwork skills.
We tested 2 TinkerSats on the ground prior to our launch trials to validate our sensor accuracy. Early on, we faced challenges like signal delays and data discrepancies, but we were thankful to be able to identify these issues and find factors that would cause such challenges. and we were able to improve reliability. It was determined that this relative change on the ground did not affect data collection in the atmosphere.
Throughout this project, we've had the privilege of working with several experts and mentors. Astronaut Dan Tani made us question the decisions we were making in our design and really think through all of our options. Professor Ronald Fevig was able to help us brainstorm ideas for the next phases of our project, which include flood detection and warning. And then finally, Dr. Kevin Crosby really helped us understand the math behind our project.
Our approach to this problem involves initial researching and brainstorming, followed by dividing the project into 3 key phases: prediction testing, deploying detection systems, and developing response mechanisms. We repeated these phases in cycles, using feedback and reflection to continuously improve our design.
Here is a diagram of all the sensors on our SlimSat model hardware that we used as our payload that are used to measure atmospheric conditions. First off, we have the SGP-30, which measures air quality and in particular CO2 levels. Then we have the GPS to measure the balloon's real-time location and altitude. Next, the BMP-180 to measure temperature, pressure, and altitude. BME-680 to measure temperature and humidity. And then finally, a cut-down device. Now, the cut-down device uses a little line of fishing wire attached to a resistor, and when we send from the server that we want the payload to drop, it melts the fishing wire and drops the payload. And we also have the INA219 sensor, which measures the power for the payload.
On the software side, we created a flight path predictor and used Adafruit dashboards to track live data. This lets us monitor the balloon's path and collect measurements in real time. This system diagram shows how data flows from sensors to the ground station. Our goal was seamless communication to avoid losing track of the payload mid-flight.
Our high-altitude balloon, or HAB, system features a payload equipped with a radio that transmits both sensor and GPS location data. This signal is received by a ground radio connected to an antenna. The ground radio interfaces with the phone, which relays data to an Adafruit server for live monitoring. Simultaneously, a connected laptop displays real-time data analytics and sends the cut-down command when needed.
Our lift calculations were pretty simple. We were aiming for at least 3 ounces of net uplift to ensure that our balloons would rise above any winds pushing it around. First, we found our balloon's neutral buoyancy by filling an attached container with water until the balloons neither rose nor sunk. We then weighed the container to determine how much lift the balloons were producing. Then, we weighed the actual payload and subtracted that from our determined neutral buoyancy lift to find our actual net uplift.
Next, we begin our launches.
The goal of our first launch was to test our helium balloon design and practice the skills necessary in a launch. We used a short tether of 100 feet to collect temperature, altitude, and humidity data. Our payload was a Thinkerset. We practiced working in teams to launch, track, and retrieve the balloons.
In our second launch, we tested a cut-down signal to drop our payload. We determined that the actual cut-down had about a 30 to 45 second lag from the sending of the signal. With higher wind speeds than our first tethered test, we really saw the effects of thermals and low-level wind shears on our balloon's flight path.
In our third trial, we used a longer tether of about 200 feet. We were really able to see the effects of thermals and wind shears on our balloon because it was a warmer day and the winds were a little bit higher at around 17 miles per hour. We also realized that as our balloons went over the tops of surface obstacles, wind shears in particular started decreasing.
Our fourth and final flight was untethered and collected the data for our project. It reached a maximum elevation of over 3,000 meters and traveled around 20 miles from our launch site. Due to a loss of communication with the payload, we had some difficulty recovering it, which will be discussed later.
At 3 p.m., we initiated the payload cutdown and confirmed its drop from 3,078 meters, but lost communication shortly after. Our mentors began searching using 2 antennas as air tag tracking was unavailable at the time. Due to time constraints, the search was abandoned that evening. Later, we regained the air tag signal, providing us a new lead. The next day, we set out on our recovery mission using the last known air tag location. By 2:32, our mentors, Miss Melissa and Mr. Chris, arrived at the site and, with the help from some nearby high schoolers, spotted the payload stuck high in a tree on private property. By 2:55, we were happily reunited with the payload.
Once we retrieved the payload, we analyzed the collected data on the temperature, altitude, and relative humidity of the air, 3 quantities that allowed us to calculate the water-vapor mixing ratio. To clarify, the water-vapor mixing ratio is the ratio of the mass of the water vapor in grams to the mass of dry air in kilograms in a specific volume of air. The saturated water-vapor mixing ratio, is the mixing ratio when the humidity of the air reaches 100%, which is the maximum amount of water vapor that can be in the air without condensing. The first step to calculating the water vapor mixing ratio was to calculate the atmospheric pressure at the balloon's altitude using the barometric formula. And in step 2, we utilized the Clausius-Clapeyron relation to calculate the saturation vapor pressure, or in step 3, we calculated the actual water vapor pressure by multiplying the relative humidity measured in our experiment by the saturation vapor pressure calculated in step 2. Finally, in steps 4 and 5, we used the pressure measurements from our experiment, as well as both the actual and saturation water vapor pressures, to calculate the saturation and actual water vapor mixing ratios. For reference, actual water vapor mixing ratios greater than or equal to 12 to 14 grams per kilogram often indicate potential heavy rainfall, and ratios greater than or equal to 16 to 18 grams per kilogram often indicate high flood potential as well, if accompanied by atmospheric instability and lift. However, the actual weather outcome is also dependent on saturation water vapor mixing ratio as well as other atmospheric qualities. After recording the data we collected from the payload and performing the calculations described in the previous slide, we obtained the ranges of values shown on the left side of this slide. When comparing and plotting the data, we found that, as shown in the graph, the actual water vapor mixing ratio was always less than the saturation water vapor mixing ratio. This finding aligned with the weather on the day of the experiment, as there was no rain that day, thus demonstrating how a high-altitude balloon system similar to ours can collect reliable data for gauging precipitation potential and intensity, which is a vital part of predicting flooding.
Now moving on to phase 3 of our project, where we developed a ground-based system to further enhance our flood detection network.
The SAFE Sensors Alerting Flood Emergencies Arduino is the TASR Team sub-project created to predict flooding based on water level. Using an Arduino kit and programming, we were able to create a circuit to detect when the sensor comes in contact with water. It will activate a buzz and turn the LED light red. Here we can see the 3 phases to connect SAFE with the high-altitude air balloon and make it possible to predict floods. Phase 1 ends in a temporary, fully functioning alarm. Phase 2 ends when the system is permanent and solar-powered. Phase 3 is connecting the data from the high-altitude air balloon and SAFE to create safe directions for safety and evacuation similar to embedded roadside technology, but at a lower affordable price.
So our untethered launch had a few difficulties. During the launch itself, wind shears kept pushing the balloons back onto the roof from which we launched. We had to wait for a moment when the wind was calm enough to safely let our balloons go. But once they were up, our biggest issues just revolved around communication, with people forgetting to mute themselves on our calls, and some connectivity issues with the launch team, which was up on the roof. The biggest barrier that we faced was when our Yagi antenna stopped receiving signals from our payload, which meant that we lost our position information as to where the payload actually was. Thankfully, we had a backup, an AirTag, and the next day we were able to go out and retrieve our payload and data. Thermals occur when the sun heats patches of the ground unevenly, so air above some patches warms faster than above others, and rises quicker. As air rises, cold air is pushed down, creating updrafts and downdrafts. Wind shears, on the other hand, are when wind is just traveling along smoothly until it hits a surface obstacle like a tree or a house, and once it hits that obstacle, it starts swirling up, going in different directions. In our tethered launches especially, we saw the effect of thermals and wind shears by our balloon being knocked into different surface obstacles like a tree.
I came to SEAS looking to team up with like-minded individuals in engineering, and not only have I done that, but I also made good friends, learned new skills, and expanded upon my love for engineering to continue pursuing my dreams.
I came to SEAS to gain experience in applying my STEM knowledge, collaboration skills, and research skills in a real-world experiment. I am very grateful for all the support, resources, and encouragement that have made SEAS such an enriching and transformative experience.
I came to SEAS looking to solidify my desire to pursue an astronautical engineering career, and I have greatly furthered my passions due to this program. I am so grateful for meeting such an amazing community of dedicated individuals and the opportunities for growth that SEAS has provided me.
I came to SEAS looking for a community of ambitious, like-minded individuals, and I found all that and more. I'm incredibly grateful for the experience SEAS has provided me personally and professionally.
I came to SEAS mainly to explore my passion for aerospace and look at the different opportunities and pathways that were available to me. Through SEAS, I was able to meet some incredible mentors and other interns and I found more opportunities than I could have ever imagined.
Here at NASA SEAS, I've had the unmatched opportunity to surround myself with ambitious, dedicated, and like-minded students who share a lot of the same passions as me.
We want to give a huge thank you to the following people and facilities
for hosting our time here at SEAS and supporting our work.
But most of all, we would love to give a huge thank you to our
3 dedicated mentors, Ms. Melissa Poore, Mr. Chris Mukes, and Mr. Nick Pugh,
who went to infinity and beyond
to teach us, guide us, and inspire us.
3, 2, 1, TASR!
TASR over and out.
Thank you.
So we have several questions for our TASR team. If you would please unmute and turn on your cameras. If given more time, what other projects would your team explore?
Yeah, I can take this one. With our high altitude balloons, there was a lot of other things that unfortunately we didn't have time to implement. So not only with the high altitude balloon do we collect data in the air, but Alejandro worked on an Arduino system that could work on predicting floods from the ground. Alejandro, if you want to talk about that.
Yeah, so we created the Arduino project, which we're going to put on the side of a creek. So if we had more time, we'd probably actually get to build the prototype itself and like solder all the parts, put it together to test to see if it's actually going to work or not.
Great. What were some of the challenges that your team faced?
I would say definitely communication was one of the biggest issues, just because during the actual launch day, we had Meg and I on the roof of CSR. Emma and Alejandro were on the floor, and then Dishita and Michael were on the chase team, actually driving to retrieve the payload. So being able to coordinate when we were launching, when we were doing a cut down was difficult. Ultimately, we were able to do it successfully, but there were challenges there.
Adding on to what Bella said, one of our biggest challenges was actually recovering the payload after our final untethered launch. After we initiated the cut down, we lost communication with it about halfway as it fell to the ground. But luckily, we still had an AirTag on it. But AirTags only work if you have an Apple device in close proximity to it. And for a while, the AirTag was not getting signal, but luckily we were able to get some small patches of location data while people drove by or past the payload, and then the next day we were able to drive and find it.
I can speak a little bit more to that. For our chase team, we usually have 2 sensors that are going along with the balloon so that we can track where a balloon is falling. One of the main issues was the device that was in the chase team vehicle was not able to connect to our laptop, so that we weren't able to sync our data. So while the chase team was traveling to retrieve the payload, our ground team, which was me and Alejandro, we had to communicate like the exact coordinates of the balloon to them in real time, which kind of made it a little bit more difficult since they weren't able to track in their own device. So that did lead to a little bit of struggle with finding the payload. But as Meg mentioned, the AirTag was definitely super beneficial at the end.
So did your team use any coding tools or platforms to help you with your analysis?
Yeah, I can speak to this. We used Adafruit, which was basically a server where we were able to connect our laptop to all our different sensors, including the GPS, the humidity, temperature, and altitude sensors. What this allowed us to do was in real time see how the different values were fluctuating, and we could also very easily track where our balloon was going so that our chase team could then recover it. After our actual launch had happened, we were then able to convert all of the Adafruit data and then transfer it into an Excel sheet and create graphs that we then put into our presentation to depict how our balloon traveled and how that related to the temperature, humidity, and altitude.
So why did your team choose to study water vapor mixing ratio rather than humidity?
I can take this question. The reason is mostly that because the mixing ratio is a ratio of the mass of water vapor versus the mass of dry air, and humidity is more of a measure of like the volume of the water vapor instead of the volume of other things, then we found that it'd be more accurate per se to measure using the mixing ratio because it isn't as affected by temperature and pressure than the humidity usually is. And also the mixing, and for that same reason, mixing ratio is also used for other calculations in the real world of meteorology.
Well, congratulations to your team. Thank you. And our next presentation is from the Gravity Recovery and Climate Experiment team, led by Chirag Patel and Benjamin Kreichman, researchers at the Center for Space Research. So please join me in welcoming the GRACE team.
Hi everyone, my name is Tammy.
Hi, my name is Cindy Long.
Howdy, my name is Arnold Bute.
Hi, my name is Ryan Collins.
Hi, my name is Sam Goyle.
Hi, my name is Sanjay Bohil.
And we are the GRACE-FO team with the NASA STEM internship program. Our project focuses on analyzing data from the Gravity Recovery and Climate Experiment follow-on satellite, and we're really excited to share our research from our time at SEAS. For a quick background into our mission, the GRACE satellites were initially launched in collaboration with NASA and the German Aerospace Center in March 2002 to measure changes in the Earth's gravitational field. These satellites gave us critical knowledge of changes in Earth's water storage, and the satellites were in commission until 2017. And in 2018, GRACE-FO was introduced as a follow-on to the GRACE mission, continuing to monitor Earth's gravitational field data. Both missions gave us new pathways to gather data about a plethora of information, such as ice sheet loss and glacier loss, sea level rise, groundwater depletion, and many other insightful details that we've gathered from these incredible satellites. So, how do the GRACE satellites work? The identical satellites are constantly following each other in orbit, sending microwave and laser signals. The range of distance is around 220 kilometers, and changes in that distance are used to measure gravity variations. As one satellite approaches larger mass, it accelerates forward, increasing the distance between the two, which represents changes in Earth's gravity. As both satellites pass the area with stronger gravitational force, their range reverts back to normal. There are many crucial instruments on board the GRACE and GRACE-FO satellites, which help us track important data. To measure distance, the GRACE-FO satellites use GPS, microwave, and laser instruments. The Laser Ranging Interferometer instrument was a new addition aboard the GRACE-FO satellite as a way to test new technology to improve distance tracking. And while the microwave instrument had an accuracy level of 1 micron, or at the size of a blood cell, the new laser instrument has the potential to increase precision by 10 times. This allows the satellite to find gravitational variations at even smaller levels. To monitor time and position, the GRACE-FO satellites utilized high-precision GPS receivers to determine orbit, and star cameras are used to determine attitude. An accelerometer is used to differentiate gravitational forces and other acting forces that may cause changes in distance. To gather our data, range and range rate are used to calculate gravitational potential. From there, we can utilize the gravitational potential to calculate different quantities, including mass concentration blocks or Masscons. That's where we derive equivalent water thickness, or EWT. The objective of our project is to use Masscons from instrument data to visualize GRACE-FO data and mask various regions that experience significant mass changes. So, why are the GRACE satellites so important? Along with providing us with tons of incredible information about gravitational variations, knowledge gained from the satellites allow us to monitor and understand contributions to sea level rise. The greatest contributor is ice sheet and glacier melt, especially in areas like Greenland and Antarctica. Thermal expansion and land water shortage also plays a key role in sea level rise. And all of these factors are exacerbated by global warming.
And today I'm covering monthly gravity solutions for GRACE. So, to understand Earth's gravity field, you need to understand how these gravity solutions are computed. And currently, there's two methods to do so. The first is spherical harmonics. Essentially, what happens here is that you have a multidimensional global wave function, think sine and cosine, and you essentially layer them on top of each other until you get something that roughly resembles the Earth's gravitational field as you see above. However, there's some severe limitations with this method. First, there's significant leakage between regions, which means that if one thing changes in one region, it affects the other. That's because of the global characteristic of these functions. Second, it's pretty difficult to visualize these because you need to combine multiple functions together until you can find the actual gravity solution. And last, it requires significant post-processing for the users to use spherical harmonics. That brings us to the current state of the art, which are mass concentration blocks, or Masscons. These are essentially tiles spread out across the Earth's surface, about 1 degree latitude by 1 degree longitude. There's about 40,000 of these. And the reason these are so good is that they estimate the actual gravity within the region, and they make for much simpler visualizations with much less pre-processing. Thus, that is what we used for our approach.
One of the key challenges when working with global data like GRACE is understanding that latitude and longitude
aren't just a grid of uniform rectangles. As you can see on the left, the surface area covered by each cell changes with latitude. Boxes near the poles are much smaller than those at the equator. So, if we treat all grid cells equally, we introduce a major bias in our analysis. That's why we use grid area weighting, shown by the weighted average equation below, to make sure that each region contributes proportionally based on its actual surface area. We also apply a technique called masking, which is shown on the right. Masking means filtering the global dataset to only include the regions we care about, in this case, South America. And this allows us to isolate and analyze changes in mass or water storage over specific areas without interference from surrounding regions. When we talk about GRACE data, we often work with a measurement called liquid water equivalent, or LWE. LWE tells us how deep a layer of water would be if all the mass change in an area were converted into water and spread out evenly. It's a really useful way to translate mass shifts, which GRACE detects via gravity, into something more tangible like centimeters or millimeters of water. But sometimes we need to know the actual mass of water involved. That's where mass change comes in, and it's calculated using this equation at the bottom below, which makes converting from mass change to LWE or vice versa very simple to do.
All right, so now we have our regional projections. So first we have San Francisco. The top left graph compares range acceleration in nanometers per second squared measurements between the K-band ranging and laser ranging interferometer systems, which are on board the GRACE FO. So as we can see, the green line is more stable, not as many big extreme lines, which means that it's more accurate than the KBR. And then we see the satellite ground track that went over San Francisco. As you can see, it just went over one part of San Francisco, and it's only one pass of the satellite. And then we have our GRACE Masscon LWE time series, our change in mass over time. And we can see it's just a seasonal change. There's no big loss in water for San Francisco. Next, we have Greenland. The top left graph also shows the range acceleration, as I already talked about. The green line is more stable, so the LRI is more accurate. And we see the Masscon data for this one in the bottom left corner, just showing the change in mass in Greenland and the big losses around the edges in the dark blue. And we have the satellite ground track in the top right, which shows just the one pass that the satellite did over Greenland to collect this data. And then the time series reveals significant mass loss in Greenland's ice sheet over time, as shown in the declining trend in the graph. Not just seasonal, you can see how it goes down over time. It's concerning. And next we have Alaska. We can see the Masscon data, Masscon graph in the top left corner. Lots of dark blue there, which is not very good, which means we're losing lots of water mass in Alaska. And the top right, the LWE thickness anomaly, we can tell that the mass is declining throughout the years. It's not just a seasonal change, with the trend line showing a clear downward angle. And then we have the range acceleration graph, and then it shows the path that the satellite took over its one pass over Alaska.
GRACE satellites are able to detect changes in Earth's gravity field caused by large earthquakes that cause significant redistribution of mass. The Tohoku earthquake that struck Japan on March 11, 2011 had a magnitude 9.0 with the epicenter 80 miles east of Sendai, Miyagi Prefecture at a depth of 18.6 miles below the floor. On the right side of the epicenter, the LWE increased by around 100 centimeters, while the left side decreased by over 200 centimeters from 2009 to 2013. This anomaly is attributed to a sudden downward shift of the Philippine Sea slab, triggering a rapid descent of the Pacific slab. The Japan LWE graph highlights this event. A deviation from the trendline in LWE can be seen in 2011, showing a noticeable decrease. The Indian Ocean tsunami that occurred after an underwater earthquake of magnitude 9.1 struck off the coast of Sumatra in Indonesia on December 26, 2004. The Sumatra-Andaman earthquake caused a 5-meter vertical deformation near the Andaman microplate and Australian plate, causing large mass redistributions. The overall LWE thickness from November 2004 to January 2005 shows an increase of around 75 centimeters off the west coast and over a 100-centimeter decrease off the east coast. The Sumatra-Java LWE shows a slight decrease near the event of the earthquake, but since the mass is mostly over land, the anomalies in the oceans are not shown clearly.
So next we have our extremes in water mass Masscon trends. So this map on the right shows mass change trends from GRACE satellite data across the globe. Red areas indicate regions losing mass, such as melting glaciers or groundwater depletion, while blue areas show regions gaining mass, like increased snowfall or rainfall. The values are expressed in centimeters of liquid water equivalent per year. In the enhanced version of the map on the right, green highlights mark areas experiencing extreme trends, greater than 4 centimeters per year of a gain or loss. These regions stand out as undergoing especially rapid water storage changes, signaling potential environmental stress or dramatic shifts in hydrological patterns. This extreme shows Lake Victoria in Uganda, We can see Lake Victoria has had a significant gain in water mass due to factors such as rainfall and rivers draining into the lake. The water levels of most lakes and bodies of fresh water have fallen in recent times. However, Lake Victoria had previously been in a drought until recently when it started to come back from it. This zoomed-in map of Patagonia highlights a widespread loss of water mass over time, shown in the deep red tones. The strong negative trends are concentrated along the Andes, where glaciers are rapidly melting due to rising temperatures and changing precipitation patterns. This ongoing ice loss is a major contributor to the regional water decline and reflects the broader impacts of climate change on the cryosphere in southern South America. Here we can see the Caspian Sea, which has seen a drastic and devastating loss in water mass. The climate change has caused more evaporation and reduced river inflows in that area, which has led to such a significant loss in water mass. Here we can see the satellite imagery of the Caspian Sea, proving that our data is correct, as there's clearly a huge drop in the water level over a short period of time, as shown by the red line here. Overall, the GRACE Masscon data reveals significant regional differences in water mass trends, with areas like Patagonia showing alarming losses. These patterns emphasize the importance of continued satellite monitoring to track climate-driven changes in Earth's water systems and inform sustainable water resource management.
Sea level change refers to the change in the height of the world's oceans. Particularly with increased greenhouse gases, our warming atmosphere is causing ice to melt into our oceans, raising the sea level. These shifts can lead to worsening weather conditions like flooding, erosion, and habitat loss. This animation shows the LWE thickness anomaly over Antarctica and the points of maximum and minimum LWE thickness shown as triangles. At the beginning of this animation, the western and peninsula regions of Antarctica have a positive LWE thickness anomaly, while eastern Antarctica has a negative LWE thickness anomaly. By the end of this animation, however, these specific regions flipped, with the western and peninsula regions of Antarctica having a negative LWE thickness anomaly and eastern Antarctica having a positive LWE thickness. This flip in western Antarctica, the Antarctic Peninsula, and eastern Antarctica shows how mass change redistributes water to the oceans, directly driving sea level change. And this graph shows how Antarctica contributes to sea level rise, as we can see its overall decreasing trend in mass. These three graphs support the conclusions from the animation. They confirm the mass losses we see in western Antarctica and the peninsula with the downward sloping blue curve. These losses are somewhat offset by the gains in East Antarctica. This animation also shows the LWE thickness anomaly over Greenland and points of maximum and minimum LWE thickness anomaly. The beginning of the animation shows the glacier and ice sheet-filled coastal region of Greenland having a positive LWE thickness anomaly. By the end, however, the coastal region developed to have a negative LWE thickness anomaly. This flip shows how the mass loss in Greenland directly drives sea level change. This graph also supports the animation. It confirms the large mass loss we see, reaffirming Greenland as the largest contributor to global sea level rise. Overall, there are massive contributions from Antarctica and Greenland to sea level rise, which the graph on the left supports. As landmass LWE decreases due to melting glaciers and ice sheets, ocean LWE is increasing at an alarming rate in direct correlation. We should note that contributions to sea level are not the same around the world, as seen in the various red and blue regions on the right.
Now we will be talking about deep and statistical learning models. After conducting our initial analysis of GRACE's follow-on data and identifying key regions experiencing significant mass change, we decided to extend our research beyond retrospective analysis. Rather than simply describing past trends, we aim to predict future changes in terrestrial water storage. This shift allowed us to approach the data in a more forward-looking and impactful way, helping to address observational gaps and informing decision-making for water resource management. To do this, we implemented predictive modeling techniques using both LSTM neural networks and Meta's Prophet algorithm. So first, let's take a closer look at one of the models we used, Prophet. Prophet is an additive regression model. This means that it breaks down a time series into four main components: trend, seasonality, user-defined holidays or events, and random noise. It begins by decomposing the time series into its underlying trend, which can be modeled using either a piecewise linear or logistic growth function. Next, it captures seasonality using a Fourier series approach, which is great for handling the repeating patterns across different time intervals. The model also has the flexibility to incorporate custom events like holidays or known anomalies, allowing us to fine-tune the forecast for specific conditions. Finally, it adds an error term to account for the unexplained variance, and thus comes the name an additive regression model. So, why do we choose Prophet? In short, Prophet offered a reliable and interpretable way for us to project future changes in water mass, especially when working with noisy, irregular geophysical time series like those from GRACE follow-on. This animation shows global changes in liquid water equivalent from 2002 to 2025, as observed by the GRACE and GRACE follow-on satellite missions. Each frame represents a monthly snapshot of Earth's terrestrial water storage. Red regions indicate water loss, while blue regions indicate water gain, measured in centimeters of LWE. Over the course of 2 decades, we can clearly see significant drying trends across regions such as the Western United States, the Middle East, India, and parts of South America, while other areas like northern Canada and the Amazon show periodic water accumulation. From this animation, we can see that Greenland stands out with persistent deep red shading, indicating significant long-term mass loss due to ice melt. This trend is a clear signal of accelerating glacial retreat and its contribution to sea level rise. In Antarctica, we see a sharp contrast. West Antarctica constantly loses mass, especially near the Amundsen seacoast, while East Antarctica remains relatively stable, with some regions even showing slight gains. To expand on the real Masscon data from the GRACE satellites from the last slide, we used Meta's Prophet model to forecast what global LWE might look like in December 2028. This visualization represents our predicted distribution of terrestrial water storage, capturing expected increases and decreases across the globe. Regions in deep red are projected to experience further water mass loss, while areas in blue suggest potential gains, possibly due to seasonal variation or recharge. This prediction gives us a forward-looking view of how climate and human activities may shape water availability in the near future. We developed an interactive model that allows users to select any global location and visualize both historical and Prophet-predicted LWE's time series data for that region. This graph shows the observed and predicted LWE near southern Greenland, where significant ice loss is clearly captured and projected to continue through 2028 under current trends. The blue line represents observed data, and Prophet was able to closely follow this trend and use the underlying pattern to generate a reliable forecast as seen by the yellow line. This chart shows Prophet's mean absolute error across various forecast horizons. While error is highest in the short-term forecast, around 5 months, it quickly stabilizes and remains relatively low, indicating that Prophet is consistent and reliable even when predicting up to nearly 4 years into the future.
Now we're going to be covering a long short-term memory network, or LSTM, essentially a deep learning model to predict regional mass changes over time. Just as basics and some reframing, we use GRACE to tell how mass changes over time. That's the whole point. And so, in order to do that, we need to start with a time series. We take some Masscon data, we spread it out over different times from 2002 to 2025, and then we have that as an input. We then give that to a special neural network called a long short-term memory network, or LSTM. Long story short, this model is pretty good at learning from sequences, and so it can find relationships between different time steps that it can then use to predict an output. And so the way we train this model is that we have some vector X input, so let's say the last 3 months, T1, T2, T3. We give that to the model, and it gives us an output T4. The process by which it learns is called training, where it learns relationships between the inputs and outputs. And then we slide the window over and repeat the same steps for future time steps. Again, overlapping sequences until eventually our model has learned and is converged. So to evaluate the LSTM, we use something called mean absolute error, which is essentially just the error rate for our model. It was about 0.2201, which means about 78% of the time, our model is pretty accurate. So it's reasonable, but there's definitely room for improvement. Here you can see LSTM comparison to the Antarctic data, and it's clearly outlined here. It's pretty good, except for when there's drastic changes or sudden upticks, for example, between T equals 150 or T equals 215. Here's LSTM comparisons with Rio Grande data. Again, the model is pretty accurate when it comes to predictions against actual data as well, but there are some places that show that sudden shifts in our LSTM can definitely hurt predictive capabilities, like around T equals 225. And so, when comparing our models between statistical learning and LSTM, we had to understand that Prophet is very good at capturing linear signals, cause and effect, direct relationships. That's why it's more interpretable for us humans, but also has much lower accuracy. And overall, although it is good for getting quick, accurate analysis, it's subpar for multivariate forecasting or looking at multiple time series from multiple regions and learning some big truths from them. Compare that to an LSTM. It captures more nonlinear signals, but it is more black box for this reason. We don't know what signals it learns, but again, it's more accurate, and over time, it can look at much more different pieces of data and learn from them, which is why, again, it is a great model to go with, and overall, I would say the best model choice would be something that fuses the power of LSTMs when it comes to accuracy and nonlinear climate signals, along with the power of interpretability from profit.
The GRACE-C satellite is a continuity mission scheduled for 2028. While GRACE-FO had both K-band ranging and laser ranging, GRACE-C will only include laser ranging. We will continue to analyze LWE anomalies to monitor natural disasters such as droughts, floods, tsunamis, and more. We will also monitor sea level change, with a growing concern for increased water level during the 21st century, utilizing gravity fields for global water levels. To improve our deep and statistical learning models, we hope to improve the accuracy of the LSTM, as well as the interpretability of profit and spatial understanding. In the future, we are hoping to find a model with all three characteristics, such as transformers.
We had a blast at SEAS, and some of our top highlights included gaining valuable research and programming skills, as well as meeting and learning from different mentors and interns from across the nation. Beyond that, having the chance to explore NASA Johnson Space Center was also an incredible journey. Some challenges we faced during the program included working with new collaborative workspace, as well as differences in Python experience with different team members. Beyond that, we also spent quite a bit of time debugging code, but it's been an incredible journey nonetheless. I'm incredibly grateful to be a part of SEAS. Having the opportunity to create such special memories with our mentors and fellow interns is a gift I will forever cherish.
I just want to extend my thanks to everybody involved. First, my mentors. They taught me practicality. 2 lines of code that do something versus 40 that genuinely just don't. Then, I want to thank my amazing teammates because they taught me the lesson of working hard and partying even harder. And lastly, I want to thank the actual people who made this program possible because it's exposed me to all these careers in space that I didn't even think about, like designing Artemis and its landing on the moon with its 3 thrusters, or the robotics division trying to navigate Mars. It's made me interested in how humans will take over space, and it's something I genuinely want to contribute to now that I've seen what NASA is really like. So again, thank you to the program and everyone involved.
Through the NASA SEAS program, I've been able to engage with talented peers from across the country, brilliant mentors, and leading scientists. Additionally, the NASA SEAS GRACE program broadened my horizons and introduced me to a world of research I wouldn't have access otherwise, and for that I am deeply grateful to the program administrators for making this incredible experience possible. Thank you, NASA SEAS.
SEAS has deepened my passion for earth science and data analysis, inspiring me to pursue a career of aerospace engineering. It gave me the confidence to tackle real-world problems using coding and satellite data. It showed me how impactful science can be when paired with collaboration and curiosity. Thank you so much, NASA SEAS, for this incredible opportunity.
I had an incredible time at SEAS meeting our mentors, especially Ben and Chirag, as well as meeting my group members and interns from other groups, and this experience has definitely increased my interest in space research.
I want to thank SEAS for an amazing 2 weeks. Over these last 2 weeks, I have developed so much professionally and personally. Whether it's meeting new mentors and scientists at the Johnson Space Center, or even working in a professional scientific environment, I've learned so many valuable skills. Additionally, I met so many amazing people and learned new challenges and how to overcome them. I'm so thankful for SEAS for an amazing opportunity. Thank you.
Amazing grace, how sweet the sound.
So congratulations to the GRACE team. We do have a couple of questions. With GRACE-C launching in a few years, what would be the advantage to having 2 pairs of gravity satellites on orbit?
I think I'll take that question. So we were actually talking about this the other day, and the benefit of currently GRACE-FO, the current satellite in space, has already lived past its lifespan. But if it does continue into the future, when GRACE-C is launched in about 2028, that would mean that there's 2 different satellites that are orbiting around space, and it takes one satellite typically around 30 days or 1 month to give us a complete gravity solution. But if we have 2 different ones, we can possibly cut that time down to just 15 days for a gravity solution. As in, GRACE-FO could cover possibly the northern hemisphere of the Earth, Grace C could cover the southern hemisphere. And so we would have much faster gravity solutions to work with that are much more localized.
What were the key limitations of using GRACE FO data to access short-term events?
That's a great question. So if you remember the ground tracks that Ryan was showing, Grace only goes over a certain region about once every 30 days. So to look at something like a flood or an event that happens very quickly, it's really hard to use Grace to analyze that. But if we're looking at something like El Nino or La Nina, something that takes maybe 9 to 12 months, using Grace data is very valuable because we see that trend over a longer span.
Well, congratulations to the GRACE team. Our next presentation is research that was conducted from Hack the Globe teams led by Andrew Clark, Dr. Kevin Jakowski, Dr. Rosanne Lowe, and Sarah Mierzwiak from the Institute for Global Environmental Strategies and Globe Mission Earth. We will have 3 Hack the Globe teams presenting their research, followed by the Q&A. Team 1, identifying outliers in globe surface temperature protocols. Team 2 on drift, and Team 3 on their Mosaic research.
Hi everyone, I'm Vin.
I'm Sanvi.
And today we'll be discussing our project, Identifying Outliers in the Globe Surface Temperature Protocol. We'll start off by introducing the Globe Surface Temperature Protocol and the Globe database. Next up, we'll introduce techniques used to detect anomalies and outliers in the database. We'll then show our analyzation of the outliers found, and finally we'll envision next steps for Globe and our dataset. So what exactly is Globe? Well, the Globe program is a science and education program that focuses on advancing Earth system science through data collection and analysis by citizen scientists. The GLOBE program's primary goal is to advance Earth system science and its applications. We specifically worked with the GLOBE Surface Temperature Protocol.
So what was our review process? First, we examined ground temperature readings submitted through the GLOBE program, and we noticed some extremely high temperature readings from 60 to 72 degrees Celsius. Our aim was to pinpoint entries that might have been a simple unit error. For example, taken as Fahrenheit and accidentally entered as Celsius.
Some of our coding strategies included utilizing a Parquet file, which helps compress large CSV files that otherwise might not have been able to be opened. We also converted the Parquet file into a data frame using the Pandas Python library. We also used matplotlib to plot outliers, coordinates, and heat maps. And finally, we also projected onto maps with GeoPandas. Here are our findings and results.
When we examined our temperature data, we were able to identify readings that fell outside the expected temperature and location ranges. We compared each of these ground readings against a climate reanalysis model called ERA5 and satellite data from Landsat 8 and 9 if available. When we investigated our clumps of data, we adjusted the tolerances based on surface type and time of day. Then, we classified each entry as a likely accurate or unit mix-up.
In terms of location data, we noticed that there are lots of erroneous locations attached to certain data points, including impossible locations that were outside the bounds of latitude and longitude. In addition, we found that lots of the data was clumped up in few locations. So we decided to investigate deeper on whether these points were created by the same user or organization, and it turns out that they were. We also found that site coordinates didn't always equal submission coordinates, as you can see on the linear graphs on the right, and that led to some issues regarding reliability, which is why we introduced interpretable flagging. We created a Pandas data frame to create Boolean interpretable flagging, and we marked when temperature or location data was likely to be an outlier. Multiple of these flags could stack, which indicates that the data is less reliable. And so that can be helpful to researchers who are trying to filter through the data for reliability's sake.
So what is the importance of our research? We hope that it'll improve the overall reliability of GLOBE data for researchers and educators. We also want to be able to offer constructive feedback to volunteers, including student participants. Our next steps are to plan to build automated checks for real-time error detection. And we also want to expand review rules to cover more surface conditions and times of day.
We want to expand the scope of our review of coordinate data, and we want to share our findings with the GLOBE community to support ongoing data quality efforts.
Some of the highlights of our internship include top features like map projection plots, identifying both temperature and location outliers, and Boolean interpretable flagging. Some of our biggest challenges included figuring out what data is reliable or not, analyzing the data through graphing, and also some of the data was hard to visualize. I absolutely loved working on the Hack the Globe project, and it was great to be able to build up my data science and earth science skills. All of my mentors and teammates were awesome, and I'm so glad to have had this opportunity.
Participating in Hack the Globe was such a rewarding experience. It pushed me to think critically about the environment and how technology can help us understand it better. Collaborating with my team and learning from inspiring mentors made the experience even more valuable.
We'd like to share special appreciation to NASA, the NASA STEM Internship Program, and mentors from GLOBE, IGES, the University of Toledo, and City University of New York for sponsoring and providing guidance and mentorship throughout this research project.
And lastly, we want to thank you, the viewers, for listening to our presentation.
Thank you.
Hello, we are the Dimensionality Reduction sub-team as part of the Hack the Globe team for the 2025 SEAS term. My name is Advait Vinod Kumar.
My name is Marlon Wong.
My name is Daksh Mamnani.
And our project is called Drift ST, Dimensionality Reduction and Inference for Field-Based Surface Temperature. We worked with the data from the Globe Surface Temperature Protocol to explore how dimensionality reduction could help uncover outliers and improve data analysis.
Before starting the project, it is important to understand the data that we are working with. To simplify, GLOBE is an international program that collects environmental data from students and scientists around the world. It gives us access to real-world data sets such as the surface temperature records that we used.
Our dataset came from the Surface Temperature Protocol, where students measure surface temperature using infrared thermometer. Each measurement includes metadata like date, time, instrument type, site latitude and longitude, and more. While the data had lots of information, it was messy, containing inconsistencies, missing values, and potential measurement errors.
This drove us to form a research question that addressed the problem. Which dimensionality reduction method best reveals structure in the surface temperature data and supports outlier detection? Dimensionality reduction is a technique to simplify large, complex datasets by projecting high-dimensional data into a lower number of dimensions while preserving as much meaningful structure as possible. It helps us make large datasets more understandable and interpretable. By finding the best method, we can uncover patterns and identify anomalies.
Before we can apply dimensionality reduction, we need to understand the structure of the data. So we start off with exploratory data analysis using tools like wide data profiling, which gave us a detailed overview of missing values and data types. Then we ran histograms, box plots, and kernel density plots to visualize distributions. Pairwise plots helped us see relationships between numeric variables like surface temperature and elevation. Through this, we were able to remove columns with over 50% missing values, dropping null values, and adding useful metadata like season and country through quick reverse geocoding.
Then we applied the three most common dimensionality reduction techniques: PCA, UMAP, and TSNE. PCA was the starting point, which is basically a linear method that reduces the number of variables retaining the most variance. We then used UMAP and TSNE to capture more nonlinear relationships, giving us different views of the data structure. We also made a PCA locus heat map to see which numerical features influence each component the most.
So, we needed a way to quantitatively evaluate which method performed best, and that's where we applied k-means clustering to each of the methods. We used three clustering metrics: silhouette score, Kolinsky-Herabass index, and the Davies-Bolden index. Across all three metrics, and as seen from the graphs, PCA outperformed UMAP and TSNE with a silhouette score of 0.45, a Kolinsky-Herabass index of 7779, and a Davies-Bolden score of 0.83. PCA was also found to have a very low reconstruction error of 0.035011, meaning it was able to compress the dataset to 12 dimensions while retaining almost all of the structure and relationships between variables.
We found that PCA best reveals structure in the surface temperature data, and so we moved forward using PCA as a basis for our outlier detection. We combined three unsupervised methods: isolation force, dbScan, and Gaussian mixture models to flag unusual data points. From the graph, we can see a total of 93 outlier points denoted by the points shaded in red. However, we did not have enough time to interpret these outlier points and possibly find any correlations between any variables.
This brings us to some of the challenges we had, which were time. We often spent a lot of effort exploring different methods and techniques that didn't always lead to useful results, which limited the time we had to analyze and interpret our complex findings. If we had more time, we would analyze the outliers more deeply, explore patterns more closely, and work towards integrating our findings with the work of other subteams.
Our results clearly showed that PCA provided the most well-separated and interpretable structure. Given its strong performance, low reconstruction error, and high speed, we recommend using PCA as the default dimensionality reduction method. For cases where local relationships matter more, a hybrid approach combining PCA with UMAP could be more useful in the future.
Thank you to Andrew, Brianna, Pramila, Ian, Dr. R, Sarah, and Dr. C for making this experience possible. Much appreciation to the Hack the Globe team for their guidance and collaboration on the project. We've learned so much and are extremely grateful for this opportunity.
Getting hands-on experience while working alongside geospatial scientists on real-world environmental data through SEAS helped deepen my understanding.
SEAS made me appreciate the depth and creativity involved in data science.
Early in this internship, I was surprised by just how many directions our project could take with the vast dataset. But exploring those paths sparked a real passion for data wrangling and research in the field as a whole.
Thank you once again to NASA SEAS for making this opportunity possible.
And finally, our references.
Hello everybody, my name is Daryl Tang, and today I'm joined with my team members Neil Kinsara and Jordan Tran. Today, we will be discussing Mosaic, metadata optimization and statistical anomaly detection using unsupervised clustering for geospatial temperature data. Our mission was to enhance the reliability of citizen-collected temperature data by identifying anomalies in a way that's both accurate and explainable. We wanted to make sure future researchers can trust this data, not just because it has passed a statistical test, but because the system clearly shows why a point is flagged. This dataset comes from the GLOBE program, a global citizen science initiative that's been collecting environmental data for over 30 years. It includes air and surface temperature, soil, moisture, and more. Because the data is collected by students and volunteers, it's incredibly rich, but it's also very noisy and inconsistent. The main challenge is that this kind of data often lacks precision and consistency. For example, you might see 40 degrees Celsius in the middle of winter with no context on location or time. Our objectives were to clean the data, add helpful metadata, apply clustering algorithms to detect anomalies, and most importantly, assign interpretable flags that explain when and why a data point might be unreliable. So what is metadata? Essentially, metadata is data about data. It gives raw numbers meaning. We added fields like country, continent, month, season, and biome using reverse geocoding and timestamps. This allowed us to contextualize each observation, making it easier to spot values that didn't align with their environment.
Okay, hi, my name is Jordan Tran, and our methodology consisted of 4 primary steps. We were given the surface temperature protocol from the GLOBE dataset and worked on profiling the data to learn more about how the dataset is structured. Then we added further data through metadata augmentation. Then we normalized the data, which could be used for flagging models, and then finally clustered the data and implemented an interpretable flagging system, which could detect outliers in the data and provide concrete reasons for the flags. For the metadata augmentation portion of our project, we ended up adding 7 new columns of metadata to the dataset. These columns were generated to improve research that would be done upon this dataset. For any machine learning models using GLOBE, these columns would add further training data and overall improves the accessibility of data for future researchers. The figures on the right are what could be analyzed from just the metadata, which shows a comparison of average global surface temperatures through different biomes, as well as by month comparing India to the US.
We applied 3 unsupervised models. Gaussian mixture models, or GMM, gave us soft cluster assignments and gave us scores for each point, letting us flag points with low confidence scores. DBScan identified sparse or isolated readings, which is especially useful for detecting outliers in remote areas, and isolation forced flag points that consistently stood apart from the others. We combined the 3 of these models rather than relying on one, and we made an ensemble scoring system to detect anomalies. After clustering, each point was checked against multiple flag types. Logical flags, like hot temperatures at really high elevations or latitude that didn't fit within the range. Statistical flags based on z-scores and Mahalanobis distance, and clustering-based flags from low model confidence. Every flag included a reason, so researchers can trace why a point was flagged when doing their research. The final dataset includes these flags and added metadata: country, biomes, continent, season, and more. This lets researchers filter anomalies based on context, for example, finding outliers only in winter. Metadata clarified ambiguous cases. It helped us separate natural extremes, like desert heat, from likely errors, like super warm winters in cold regions. This made our clustering results far more interpretable and helpful. By combining metadata and unsupervised models, we created a scalable and explainable system for anomaly detection. PCA visualizations helped verify that low confidence points helped form clear and separate clusters. This approach improves the reliability of the GLOBE dataset for further Earth science research.
Across our team, we believe that the true highlights of this program have been overall great team sessions and having a productive working environment. We had meetings every day for 2 weeks, and it was helpful having constant guidance for our mentors every day, who helped us through our daily problems and our project at a high level. The globe dataset was also incredibly comprehensive, and it was great to be able to work with almost 20 years of surface temperature data, which was gathered by citizen scientists around the world. We also grew our data science knowledge, and our mentors provided us with different ways we could attempt to solve this mission. Our big problems were balancing our work with other life activities other than the SEAS program. Our team is split up into 2 different time zones, so it was hard to overlap schedules. And while our methodology should be able to be extrapolated to other protocols, we only ever looked at the surface temperature protocol for globe. Overall, my personal highs for this internship was being able to grow my data science skills and being able to work with a large group of like-minded peers and amazing mentors who did a great job of guiding us through our projects. They made this internship a lot of fun and never really restricted us, allowing us to explore the topics that we were interested in.
For me, I really enjoyed working with a group of people that had a shared interest in programming. However, I feel like the time frame of the project made it a little difficult to complete on time.
One of the best parts of SEAS was working with real NASA data and building something that could actually support climate research. It challenged me to think beyond school projects and gave me clarity that I want to pursue, data science and AI. SEAS made that feel real and achievable.
Thank you to NASA and SEAS for putting on this program. Thank you to the mentors who have helped us with this project. And thank you to the Globe team for providing the data and the project initiative. Thanks to all the citizen scientists who collected data around the world to make this project possible. And finally, thank you for being here to listen to our presentation. It really means a lot to us.
So excellent information from all 3 teams. So we're going to start with team number 1. We have a question about what challenges did you face with new programs and technology?
Yeah, so initially our approach was to try and compare our data from the GLOBE dataset to Landsat data, but we quickly realized that would be an issue because of the Landsat only passing over the same point every 16 days. So that's why we pivoted to using ERA5 as a climate reanalysis model in order to try to get more reliable and accurate data predictions.
In addition, we also saw that multiple organizations and users had entered large clumps of erroneous data that was all centered at inaccurate latitudes and longitudes. And so that was also a challenge that we faced with this globe technology.
Team number 2, what are the main goals of reducing dimensionality?
For us, reducing dimensionality is mainly to make the vast data set of the surface temperatures more understandable. As we got it, the data set had a lot of missing columns, areas which needed further information, and it was pretty messy. So with the reduction techniques, we were able to make it more concise.
Team number 3, did you notice any patterns to the missing data, like regions or time frames?
Yeah, so in some of the places, we had a bit of missing data, or like the data wasn't super consistent. For example, like in urban areas or at like a university with large numbers of students or more people, we usually have like better data availability. However, in like more remote regions or like low infrastructure areas, there's not as much data. And for time frame, it was pretty consistent along the time frame.
I would also like to add on to that, because our program reverse geocodes using the coordinates that are provided from the data set. That because people might misinput data points, there may be some inconsistencies where we may misidentify like a place that's a country, even though a country does not exist wherever that data point is.
So team number 1, how did the team validate or test reliability of the data?
Yeah, so we introduced interpretable flagging methods just like the other 2 teams in Hack the Globe. And so we mainly did that through augmenting our data set by adding multiple Boolean-based columns, which could flag for inaccurate location, unlikely temperature, and we could flag each of these. And if they compounded, researchers can choose how much they want, how reliable they want their data set to be to exclude or include certain data.
And team number 2, what is the spatial or temporal distribution of the surface temperature data? Are these seasonal or regional patterns taken into account?
Yeah, so I can take this question. So usually the surface temperature data is taken by students around the globe, but it can be uneven, like some countries and regions have more like submissions than others. And regarding seasonal and regional patterns, we had our metadata team add features like season and country through reverse geocoding, which helped us understand the data more as a whole.
And the last question for team number 3, are there new features that can be created in Globe data based on your research?
Yeah, so for our research, since we worked on doing metadata, all the data that was generated relies on the current inputs that are like provided through the Globe data set. So whenever people are inputting something like their latitude and longitude, we can use that information to find a lot of different information that future researchers can use. So country, season, the type of climate and biome that they're in. That can be automatically added into any Globe data set.
Excellent. Congratulations on doing a good job. Our next team is the Airship team led by Dr. Darcy Snowden, who is an associate professor of physics at Central Washington University with a research focus in planetary science, particularly the study of Titan. The project assistant for the Airship team is Sherelle Webb. Please join me in welcoming the Airship team and their research on developing a Titan airship.
Hey everyone, we're the 2025 Airship Project team, and thank you for tuning in to our presentation.
Hey, I'm Swayam.
I'm Rebecca.
I'm Amarachi.
I'm Gene. I'm Oliver.
I'm Michael.
I'm James.
And I'm Adi. And over the past few weeks at SEAS, we've been working on a project that challenged us to think beyond Earth by designing an airship for Saturn's largest moon, Titan. However, in order to understand our solution, we must first understand our purpose.
Titan has caught the eye of scientists for nearly 400 years, but it wasn't until after the Cassini-Huygens mission that scientists discovered Titan was the only place besides Earth known to have clouds, rain, lakes, and seas of compounds like methane and ethane. This means that there's a potential for life on Titan, which could lie in the subsurface ocean or in the hydrocarbon liquid on the surface. Since then, scientists and engineers at Johns Hopkins APL have solidified our next mission to Titan, Dragonfly. Set to launch in 2028, Dragonfly is a rotorcraft that can travel aerially to a broader range of locations, allowing for more surface research on Titan as opposed to a traditional rover. Yet, long-term atmospheric data obtained from airships will provide crucial context for interpreting future Dragonfly data from the near surface. As Dr. Sarah Horst said, Titan is fundamentally different because the atmosphere and the surface are incredibly closely tied together.
High-altitude balloon platforms, like our prototype, can access infrared and ultraviolet wavelengths that ground instruments can't. From this, we can study absorption bands that can indicate molecule presences like water and carbon dioxide, crucial for identifying hydrated species, minerals, ices, and volatile organic compounds. Furthermore, Titan is especially well suited for airship-based exploration. Its atmosphere is about 1.5 times denser than Earth's, making it the most practical body in the solar system to conduct buoyant flight. Unlike rotors or aircraft, which require constant propulsion, airships can fly without using continuous energy. With Titan's atmosphere obstructing most solar energy, an airship model is especially beneficial as it allows for more power to be delegated to data collection and transmission.
With our project, we aim to design an airship to study environmental conditions analogous to Titan by collecting atmosphere data here on Earth. We did that by using temperature and pressure sensors, gas sensors, and a spectrometer for reflection spectroscopy. Using these sensors, we could conduct research that would complement the surface-focused goals of missions like Dragonfly by providing atmospheric context.
This calculation determines the maximum liftable mass for our airship in Earth's gravity. To calculate the budget, we start by finding the volume of the balloon, which is 0.44 cubic meters. Next, we plug in the values of Earth's standard air density and gravitational acceleration into the buoyant force equation and find a total force of 5.3 newtons. Finally, dividing that buoyant force by gravity gives us the maximum mass allowance of about half a kilogram. Because Titan has a much denser atmosphere and weaker gravity, it changes the mass budget to about 2.5 kilograms, about 4.5 times larger than the mass budget on Earth. Here we've calculated our propulsion force. On Earth, we have a thrust coefficient of 0.15, a propeller diameter of 7.5 centimeters, and a spin rate of about 883 revolutions per second. Next, with the thrust force equation, we calculate how much force the propellers can generate in each environment. Since we have two propellers, our results will be doubled. When calculated, the Earth-based propulsion force comes out to about 9 newtons, but Titan's denser atmosphere boosts that to over 40 newtons, showing significantly higher efficiency.
After making calculations for our design constraints, we set a list of engineering requirements to fulfill with our gondola design, such as the payload must weigh between 0.4 and 0.6 kilograms, and the balloon must lose less than 10% of its helium per day, and accordingly must maintain structural integrity in holding a stable flight for 10 minutes. This was accomplished by designing a novel O-ring clasp for the balloon seal, which achieved a helium loss of 5% per day.
We split our design into 3 focus categories: propulsion and control, gondola attachment, and sensor optimization. For control, we intended to minimize the number of propellers used in order to simplify wiring. At first, the propeller was put in the front of the gondola, with the 2 thrust propellers in the back. After catting the initial design, the vectoring motor was moved to the back with the other 2 propellers for aesthetics and increased torque. A stepper motor controls the orientation of the vectoring motor, allowing variable control over pitch and yaw.
However, when testing the pitch up and down control abilities, the airship largely translated vertically instead of rotating, due to the low torque relative to the airship's rotational inertia. While unintended, this feature was beneficial, as it allowed for more accurate movement. Yawing was also diminished, with the gondola simply translating left or right instead of actually rotating. For gondola attachment to the balloon, we initially considered a carriage structure, which would distribute the weight evenly across the balloon. However, due to weight and printing limitations, we settled upon using external strings. In our first flight, we attached these 3 strings to 6 separate hooks, yet after testing, these hooks lacked the integrity to support the airship. Thus, in our final iteration, we decided to attach strings to clips, which would attach to the side of our modified propeller arm.
Our fully customized gondola design involved designing an aerodynamic yet sturdy structure that could integrate all of the electrical components. A simple boat design worked well for this. Screw holes were placed throughout the base for sensor mounts. 2 arms were placed to the sides of the gondola to optimize airflow to the propellers, ensuring maximum propulsion, and a recess was added to the back of the gondola to attach the stepper motor. Finally, we created a friction. One main constraint for the gondola design was mounting electronic components at clear vantage points, especially for external sensors. To remedy this, we created custom sensor mounts. For example, the spectrometer and external camera are mounted under the gondola to face the moon's surface. Our final design has a sleek and aerodynamic look. The arms were remade to increase propeller thrust and improve balancing. This was done by adding a bottleneck for a more stable connection to the ropes. To allow the lid to be easily removed and installed, 2 holes were added at the top for easy access. Ultimately, the final gondola weighs 0.47 kilograms, which fulfills our engineering requirement. To better understand the airship's performance and control characteristics on Earth and Titan, we created a computational fluid dynamics simulation. In our Earth model, we observed air hitting the front of the airship and slowing down, causing stagnation. As it traverses the side surfaces, the flow speeds up. However, towards the aft, we observed uncontrolled flow separation, creating uneven eddy vortices. In certain conditions, this can lead to unexpected drag and control loss. However, because the airship flies at low speeds and the helium provides strong enough inertial dampening, this behavior isn't expected to cause major issues in ground testing. Also, these vortices dissipate quickly in the model, so they shouldn't be of too much concern.
Next, we cloned the same simulation, yet modified the fluid we'd be using. Taking data from the Cassini-Huygens mission, we obtained air density, viscosity, specific heat, and compressibility values to input into the CFD model. This allowed us to model fluid flow if our airship was in fact on Titan. When the simulation was solved, it had a significantly higher Reynolds number, indicating greater turbulent flow overall. We observed this especially at the aft, where separated flow fails to restabilize, revealing stronger and longer lasting eddy currents when compared to Earth. This creates a chaotic wake that could disrupt flight. To address this, future prototype and mission designs will require effective control surfaces to help manage and reduce this uncontrolled flow separation.
Here are our electronics and wiring components. The main controller is an Adafruit Feather Sense. It acts as a central microcontroller, communicating with multiple sensors, including an integrated sensor for temperature and pressure changes. For movement, the system uses 3 cordless brush motors. 2 work in parallel to move the ship forward and backward, while the third is linked to a bipolar stepper motor, which handles rotation. All motors are controlled using the Adafruit stepper plus DC motor feather wing, which acts as the motor driver for both brush and stepper motors. Power comes from a 3.7-volt lithium battery, regulated for the feather. A 5-volt power boost charger handles motor battery charging. Additional sensors include the air quality sensor and the Adafruit spectrometer for light and color analysis. A sand-cell mini camera is used for visual capture, and an Adafruit multiplexer expands sensor connectivity. In our initial prototype, our airship contained a micro SD card to store all collected gas, spectral, and imaging data from sensors. However, due to card malfunctions, we instead collected the data directly through download. We made a fritzing schematic to map out the electronic and wiring design. This served as a baseline to recreate the diagram in real life and place the shown electronics inside of our gondola. To finalize our airship, we used a new Adafruit feather and feather wing and soldered header pins to connect. We also replaced our motors and resoldered their wires to stabilize the connection. A multiplexer was also added to connect the gas sensor. During development, we continually ran into conflicts with multiple sensors and electrical components requiring the same transmission channel on the featherboard. This was resolved by adding a multiplexer so that multiple sensors could connect to the same channel.
We also encountered difficulty with the stepper motor not making full rotations. We found that more torque was needed to rotate the stepper motor 90 degrees in both directions. To initialize the airship software, we set up a connection between the featherboard and the motors and initialized the onboard and external sensors. We used the Bluefruit Connect app to control our airship, which changed the motor throttle and stepper rotation using the button type and whether it was pressed or released. The directional buttons on the left control the back motor and the stepper motor, while the numbered buttons on the right control the motors on the side. Both the motor and sensor data were transmitted in real time as small packets over Bluetooth using NUS protocol to the Bluefruit Connect app. The sensor data was later exported as a CSV file for data analysis.
This is a video of our initial airship test. We noticed that once forward motion has been established by the propellers, the airship continues to drift without a large decrease in speed, even after the motors have been turned off. However, we also noticed that the forward motion wasn't very stable, and there wasn't sufficient control of the airship's movement, as it tended to slowly drift and turn over time. In this video, we observed the airship's drift matching our CFD model. The turbulent flow destabilizes the airship, causing chaotic flight visible in the uncontrolled lateral drift. Our airship was equipped with scientific instruments to simulate advanced sensors used in Titan missions. We chose to find comparisons of our prototype sensors to more advanced mission technology. Instruments like the fiber optic gyroscope, known for high-precision orientation detection, and Huygens atmospheric structure instrument, collected detailed information about our pressure, temperature, and acceleration during descent. The mixed gas sensor on our airship mirrors the gas chromatograph mass spectrometer on Huygens, which identified nitrogen, methane, and isotopic ratios critically to understanding Titan's atmospheric history. Our spectrometer and external camera are also analogous to the visible and infrared mapping spectrometer on Cassini, which revealed surface composition and helped identify features like lakes, dunes, and ice.
Titan's atmosphere is made up of about 95% nitrogen and 5% methane. Even though the sun's radiation should be breaking down methane over time, the atmosphere remains questionably dense, suggesting the presence of a methane cycle, possibly due to surface features like cryovolcanoes, erupting water, and methane. On the left is Titan's temperature profile showing well-defined atmospheric layers like Earth, but much more extended. At different altitudes, sunlight can trigger complex chemical reactions with carbon, hydrogen, nitrogen, and oxygen forming organic molecules. These molecules can recombine into heavier hydrocarbons, which either join Titan's haze layers or fall to the surface, creating dunes and lakes. As mentioned earlier, spectrometers were widely used in the Cassini missions. The top images highlight important features captured from the missions, such as lakes, diverse terrains, and an image of the Silk crater, which displays exposed water ice. The spectral graphs below correspond to these features. The right graph reveals how methane lake depth affects reflectance, with deeper regions reflecting less light, allowing scientists to estimate lake bathymetry. The center graph displays strong indicators for different compounds, including water ice at 2.7 microns, and the left graph compares bright and dark regions on Titan, showing clear differences in absorption from 1 to 3 microns. likely due to reflective ice-rich areas versus darker light-absorbing dunes. If conducted on an airship, we can obtain readings with greater definition and clarity than existing data, allowing for a much more detailed understanding of Titan's chemical composition.
After iterating on our proof-of-concept airship design and researching it, we developed a hypothetical airship mission to Titan. Our main objective is to utilize the unique benefits of an airship model to fill in the scientific knowledge gaps of Titan. In this mission, the airship will enter at a 40-degree latitude angle, at an Earth-facing point for ideal communication. It would make a west-to-east pass according to Titan's eastward jet stream, while gradually traveling across wind currents toward Titan's north pole. We will time the airship's entry to Titan's winter season since it provides the ideal north-south winds to allow the airship to reach the North Pole. During the first 5 months of our 10-month-long mission, the airship will circle Titan at an altitude of 10 kilometers in the troposphere. During this phase, it will use reflection spectroscopy to bounce light off Titan's clouds, collect temporal data, and capture high-resolution images of the surface and frozen lakes. Afterward, it will release a ballast and rise to the stratosphere, around 50 kilometers up, for another 5-month-long revolution. Here, the airship's focus shifts to atmospheric chemistry, characterizing Titan's hydrocarbon cycle and classifying upper atmosphere chemical compounds. Meridional wind oscillations, or north-south wind gusts, that occur during Titan's winter will help the airship cover more of Titan's surface. On our hypothetical mission, our airship's instruments aim to provide unique insights into Titan's surface and atmosphere that build on observations from previous missions and research questions. We would need to consider our airship's limited storage capabilities when flying on the outer planets and allow time to transmit data incrementally to minimize the risk of losing data in a malfunction or failure. Thus, for our mission profile, we varied the data collection periods of different instruments and sensors.
Our first instrument is called SCAN, which stands for Spectrometer Camera Atmospheric Notation. The spectrometer would work in tandem with the camera to collect spectral data from a variety of terrains. When the camera senses a new type of terrain, it would begin taking higher resolution images, and the spectrometer would transmit 5 readings, each about 0.2 seconds apart. This would be beneficial for observing molecules like methane, nitrogen gas, and water volatiles. Our second instrument is called GAS-O, which stands for Gathering Atmospheric Sensing and Observations, and is composed of a gas sensor and an air intake system. For this instrument, we have 2 main objectives. The first objective is to map Titan's atmospheric chemical composition. We would quantify organic molecules such as C3H2, which have been detected in previous missions and are unique to Titan's atmosphere. Using this data, we aim to characterize Titan's hydrocarbon cycle. The second objective is to investigate gas distribution and variability across Titan by collecting atmospheric profile data every 20 seconds and looking for gas pockets or distribution anomalies similar to the Antarctic ozone hole on Earth. Also, we would monitor Titan's wind profiles by tracking how the airship drifts.
Finally, let's discuss our future research goals. First, as mentioned earlier, our current CFD models from Titan show significantly uncontrolled flow separation, which can impact stability and maneuverability on Titan. Adding active flow control surfaces like fins on a prototype will help manage separation-induced turbulence, improving overall flight performance for a future Titan mission. Second, instead of using a single inflated envelope, separate internal gas cells, or ballonets, will allow us to test an inflation mechanism of the airship as it arrives on Titan and provide greater structural integrity to withstand Titan's harsh cold and storms. The diagram above illustrates the ballonet layout and support structure we've been considering. Third, a simulated physics model of our airship operating under Titan-like conditions would enable us to test material behavior, stress distributions, and allow optimization of control algorithms well before building further physical prototypes. Such a model will allow us to better map and test an Earth-based prototype for future Titan use case. Fourth, due to Titan's approximately 1.4-hour communications delay, remote piloting is severely impractical. To address this, we plan to test a proportionally integral derivative, or PID controller, in the future to test autonomous piloting on an airship. This system will use real-time sensor feedback to autonomously adjust motor outputs, enabling self-correcting flight without human input.
Our main highlight of NASA SEAS was the opportunities that we got outside of the project. We were given the opportunity to work on the Z-Cube, construct the ISS research proposal, converse with astronaut Dan Tanney, and learn more about flights in microgravity. These many opportunities illuminated the different career or research paths that we all could take. SEAS, however, did not come without its challenges, as every intern had to adjust to a new environment while navigating newfound skills. Within our project, the High Altitude Balloon Project, we found it strenuous to analyze research about Titan to connect to a future mission. With the airship itself, we had issues wiring our sensors to our multiplexer while optimizing battery usage. These challenges, though, made us work harder and tested our critical and collaborative skills. C's pushed us to adapt and thrive in a fast-paced environment, and ultimately to come out stronger.
My time at NASA STEM taught me that there are so many different ways to contribute to space research. I met an astronaut, a biologist leading a NASA lab, a flight director, and many like-minded peers with a variety of interests. I'm so grateful to STEM for helping me further my interest in space science and engineering.
Working alongside a team of passionate high schoolers who brought unique strengths to the table made every challenge feel like a shared opportunity to grow. Through late-night problem solving, learning from our mistakes, and supporting each other, I not only gained valuable experience, but lasting friendships.
My time working in such a collaborative and dynamic team at SEAS showed me that the value of a future career or education in engineering isn't defined by what is built per se, but by the people who it's built with. It was such a pleasure to be on this team, and it's certainly defined how I view a successful career.
At NASA SEAS, I learned how our diverse skills can come together to create something none of us could do alone, building an airship in 2 weeks. I not only furthered my interest in engineering and research, but also made lasting friendships and connections.
At NASA STEM, working alongside motivated peers showed me the importance of dedication. Their drive inspired me to give my best in CAD and strengthened my passion for mechanical engineering.
At SEAS, I was exposed to many opportunities in the STEM field. Being able to work with a group of such intellectual students allowed me to realize my potential within this field. I'm grateful for my experience at SEAS, and I plan to continue pushing myself in future environments I surround myself in.
NASA STEM showed me the power of a focused team as we successfully built an airship, CAD, wiring, and programming included in under 2 weeks. It also sparked my passion for combining electrical engineering with programming to create innovative solutions.
Through SEAS, I gained a broad perspective on the careers at NASA and met incredible peers and mentors who inspired and challenged me to continue pursuing aerospace engineering and also to have fun.
Thank you for watching!
Great research. So we do have several questions for the team. The first question is, what factors influence the boat-shaped design of the gondola?
I'll take that one. So for the gondola, we settled on a simple boat-shaped design. It was cheap, easy to print, and very easy to CAD. And it also allowed for a lot of space for internal electronic components. We also added skis on the bottom of the gondola to protect the internal electronic components in case of an unexpected landing.
Were there any weather conditions unique to Titan that you had to factor in when designing the high-altitude balloon?
I can take this one. What's especially nice about Titan's weather conditions is that it has a dense atmosphere, which makes it an ideal place for an airship to fly. For our tangible, like proof of concept airship design, that was more for Earth. For example, we wouldn't actually use a latex balloon on Titan. However, in our mission profile and sort of research side of our project, we definitely took weather conditions and wind profiles in mind when designing our mission profile. For example, we researched where we would make entry into Titan's atmosphere based on the direction of the winds in the troposphere and stratosphere so that the north-south winds would drift the airship to the North Pole.
So was the payload designed with mass constraints in mind? And how did the team balance structural strength and weight minimization?
Yeah, great question. Our mass constraint was around 0.5 kilogram for our model airship to remain neutrally buoyant. While creating the CAD and thinking about what sensors to include, the weight was always on our minds. To balance our strength and weight of the gondola, we found that out of PLA, 2-millimeter walls for the whole of the gondola was stiff enough for our design and was light enough to fit within our design constraints.
What were the biggest design challenges when fitting all the electronics and sensors into the gondola?
That's also a good question.
I'll take this one.
Good.
So basically, the biggest design challenges was making everything be able to fit in such a small space and being able to keep the wires organized and make sure that our sensors were placed where they're supposed to be and all the wires were placed in the correct input so that they would collect accurate and good data without getting in the way of each other.
Yeah, I think there were like challenges with the airship not being wide enough or tall enough. So we had to think about like the height of the height of the lid and like the width of the airship in a way that both like allowed for space but also didn't take up too much weight.
So what improvements would the team make for a future flight to ensure better stability, sensor accuracy, or altitude reach?
Okay, so I'll take this one as well. So for our future flight, basically our team would mainly improve stability by being able to adjust our weight distribution so that our airship can actually balance and using just better wind resistant materials. And to like increase our sensor accuracy, we want to add like installation or something that will basically prevent our sensors from being affected by external factors so that they can solely conduct accurate data. And to reach a higher altitude, we would mainly aim on either using a bigger balloon and adding more helium or just finding a way to make our materials lighter so that it doesn't weigh down our balloon too much.
Well, congratulations to your team. Excellent research. So our next presentations are from the Earth System Explorers team, led by a team of scientists, including Dr. Lowe, Cassie Sofing, Andrew Clark, Peter Nelson, and Erica Podest. We will have each team present, followed by Q&A. Our first team and their research is on predictive modeling of flash floods.
Hi, my name is Shelby Taylor. I am from Morro Bay, California, and I am part of Working Group 1. Our team name is SHIELD, which stands for Soil and Hydrology Intelligence for Emerging Land Cover Disruptions. Our project is about predictive modeling of flash floods, investigating hydrology and land cover dynamics through remote sensing data. To come up with this project, we actually combined two of our proposals, one on soil properties and one on flood risk. This project is important to us because flash floods pose significant risk to infrastructure and human safety. In Texas and New Jersey, ongoing floods have caused an unprecedented loss of life and damage to affected communities. Monitoring topographic, hydrologic, and soil data to understand repetitive trends during flood events can help to minimize damage in the future. Our method to do this, we will analyze areas of interest focusing on hydrology, topography/elevation, runoff, land cover, soil properties, and other factors that could lead to flash floods and river overflows. Some of the data we've used includes the land cover observations we compiled through the Globe Observer and EarthMap.
Hi, my name is Kushi Patel. Growing up in Sugar Land, Texas, I've seen firsthand the impacts of flooding events, particularly during hurricanes such as Hurricane Harvey and Hurricane Beryl. Deciding to investigate what particularly causes an area to be flood-prone, I chose to first take a look at this 3-kilometer grid pasted to the left. Below that, I've analyzed the same grid but using different layers on EarthMap Online. Firstly, at the very far left, I've analyzed surface water runoff. Next is different soil types. Next to that is surface water occurrence, with bright reds representing an increase. And lastly, the slope of the area I live in, with paler colors representing a more steep slope. My team and I hope that analyzing these factors can help us gain a better understanding of what causes an area to flood more easily, or what mitigation efforts we can take to prevent an area from experiencing as much damage as it may from a flood event. Thank you.
Hi, I'm Ati Prajarji. I live in Edison, a town located in central Jersey, which has seen numerous flooding events in recent years. My region is flood prone, and recently we have experienced multiple extreme weather events involving flash flooding and storms. In an effort to figure out what makes my region so flood prone, I started by analyzing my AOI, or area of interest, using various layers from EarthMap Online. In the bottom right corner, you can see my 3x3 kilometer AOI in EarthMap Online without any layers applied. On the far left, the first layer I chose to analyze was the layer for yearly runoff. Runoff is usually highly correlated with flood risk, with flash floods being major sources of high runoff. However, the light purple and white coloring represented relatively low levels of runoff. Runoff alone cannot explain the flood risk in my area. Next, I analyzed soil types, theorizing that maybe the soil types in my area had higher clay content, leading to slow drainage of water from high rainfall events. But soil type didn't quite explain it either. The dominant soil type in my AOI was loam, which is a relatively balanced soil with minimal drainage issues. In this slide, we can see some pictures of the recent flooding in my area, which gave me a hint as to why this was happening. If you look closely, you can see that in both pictures, the flooding is concentrated around roads. In other words, impervious, non-porous surfaces, which which would prevent natural draining by blocking water from seeping through. This led me to analyze the history of urbanization in my AOI. In this slide, you can see a graph of land use categories over time in my AOI, with red representing urban development and green representing natural forests. The graph shows a clear trend from 1995 to 2020 of increasing urbanization and decreasing natural coverage, leading to a loss of drainage opportunities and increasing flood risk over time. Finally, the last piece of the puzzle lies in analyzing precipitation patterns. In this graph of monthly aggregate precipitation from 1981 to the present, I found high seasonal variability in monthly precipitation. Although yearly precipitation is not particularly high in my AOI centered in North Edison, monthly aggregates get as high as 150 to 200 millimeters per month almost every year in late summer due to hurricane season, leading to a consistent summer flooding risk in coastal regions or regions of New Jersey near rivers, like mine. This investigation into my AOI really emphasized the importance of considering every variable in a situation as complex as flood risk, an ideal which our SHIELD project adheres to.
Hey everyone, my name is Arun Venichetti and I'm from Monroe, New Jersey. In recent years, NJ has experienced increasing rainfall and precipitation, leading to constant flash flood warnings and accidents on our highways. Branching off our experience analyzing land cover in our Adopt a Pixel project, I analyzed my same AOIs using different EarthMap datasets related to precipitation, runoff, as well as the land elevation and slopes. On the top row, you can see my AOI's data for precipitation, but it's worth noting the lack of variability because in the grand scheme of things, a 3 km by 3 km area is not very large. But next to that, you can also see the historical data from millimeters of rainfall, both monthly averages over the years, as well as average rainfall since the 1980s. You can see that the average rainfall peaks in the summer months, July being over 110 millimeters. And in the bottom left, I've included snapshots of surface water changes, red representing an increase. To the right of that is my AOI's elevation and slopes visualized, the different colors representing different slopes and valleys. Our team, SHIELD, hopes EarthMap's visualization and data can help us answer what makes an area flood prone and what we can do to make these areas better prepared for disasters.
Hi, I'm Kumudar Srinivas, and the area of interest for my case study was Dublin, California. Dublin is a rapidly growing city in the East Bay area with minimal flood risk and a very limited history of flooding. Using the hydrology layer on Earth maps, I found that there was approximately 100 millimeters of runoff per year in Dublin, which is on the lower end of the spectrum. The soil texture filter revealed something very interesting. Although Dublin isn't a flood-prone region, it has a large amount of clay loam soil, which typically implies higher runoff amounts and consequently a higher flood risk. This stood out as a discrepancy until I examined the city's precipitation levels. The linear fit of the annual aggregation chart showed a decreasing trend, and the highest amount of monthly average rainfall was only about 87 millimeters. Therefore, the minimal rainfall accounts for the reduced runoff, despite the soil type discrepancy. Discovering such patterns and trends in hydrology, land cover, and topography is essential to predicting flood risk and alleviating future destruction.
Hi, I'm Satvik Kopu from Suwannee, Georgia, a region not typically prone to flooding. To understand why, I analyzed the local hydrology, soil texture, and precipitation. Using EarthMap datasets, I found out that Suwannee experiences peak surface runoff from January to March, with a maximum of 28.42 millimeters in February. But the overall runoff remains moderate, which is around 290 millimeters per year. Soil data revealed a transition from loam at the surface to clay loam at deeper depths, which slows water infiltration. This layered soil profile, combined with moderate rainfall and higher elevation, reduces flood risk despite occasionally high runoff. Additionally, Suwannee has a minor risk of flooding over the next 30 years, according to the 2024 Suwannee, Georgia Flood Map and Climate Risk Report. ERA5 land precipitation confirms this, showing that rainfall peaks in winter months like January and March, while drier months in the fall help balance the wet season. Together, these factors support long-term climate resilience and effective flood mitigation.
Hi, I'm Pallavi Nair from Allen, Texas, a region notably unaffected by floods or flash floods. To understand why, I analyzed hydrology, soil texture, and slope. Firstly, the runoff is very minimal, with a majority facing around 100 millimeters of runoff. Interestingly, the dominant soil types, clay and silty clay, have high water retention, which would usually increase flood risk. So, while soil texture raises questions, the minimal runoff combats this anomaly. Additionally, the slope map shows that most of Allen has a flat to gently sloped terrain, which helps reduce rapid water flow and pooling. Additionally, recent climate reports confirm that Allen faces only a minor flood risk over the next 30 years across residential, commercial, and infrastructure sectors. Together, these factors suggest that Allen's topography plays a critical role in mitigating long-term flood vulnerability.
Here is a table from my poster that combines my own ground observations with remote sensing data and image chips. Each row represents data from one of 37 points in our 3-kilometer area of interest grid. Comparing our own globe observer pictures with different remote sensing layers and graphs allows us to discover patterns, trends, and inconsistencies within our areas of interest.
Hi, my name is Saad Ali, and I'm from Tyler, Texas. One key focus of our project has been the integration of AI and machine learning and enhancing flash flood prediction using remote sensing data. We specifically plan to model the key hydrologic processes of rainfall to runoff transformation, rapid floodplain inundation, and flood routing to assess factors that contribute to flash flooding. To do this, we're processing satellite-derived inputs like Sentinel land cover, daymet precipitation, and SMAP soil data within Quantum GIS software to delineate catchments, extract hydrologic and topographic features, and analyze land cover dynamics. We're also working with HEC-RAWs, where hydraulic simulations can help us map inundation extents, giving us insight into the potential risks of flooding caused by land cover, weather patterns, and soil properties. These models will be validated against discharge hydrographs and ground observations. By fusing physical modeling with machine learning, we aim to develop a hybrid predictive system that can adapt to changing land cover and climate trends, improving both lead time and spatial accuracy of flood forecasts. Our end goal is to deliver a scalable, AI-enhanced flood risk platform to support operational decision-making in emergency response and long-term hydrologic planning. This approach enables more effective, data-driven flood risk management, especially in areas with limited ground observations or rapidly changing land use. Thank you.
Hello, my name is Hector Galvan, and this is our project timeline. Basically, just a sequence of steps we're going to follow in the months leading up to AGU and the annual meeting. So our first step, which is already mostly accomplished, was gathering data for our own AOIs, or areas of interest, relating to our project theme, such as soil properties, elevation, runoff, among others. Our second step will be to expand our AOIs to other areas that have recently suffered flood events and are more flood prone, such as Kerrville, Texas, and Plainfield, New Jersey. Our step number 3 is artificial intelligence. Here, the team plans to develop an AI that can predict high-risk flood zones by using our past data collection and meteorological forecasts. For our step 4, a web-based platform, we want to develop a website in the format of an interactive map to showcase our AI's predictions and send notifications or warnings of possible flood events. We also want to allow for citizen science entries, including pictures and soil samplings, which could allow us to ground truth and validate the data that we're using to train our AI. In the future, we want to make this website public so that everyone can benefit from the project. Finally, our 5th step, though still in the brainstorming process, we do want to have a physical component to this project, and ideally we want it to be easily deployable, potentially be used by citizen scientists, and of course provide the invaluable ground truth data that we need to train our AI and to validate the data sets that we're using.
Hi, I'm Arush Roy Chaudhary. One of our biggest challenges during our data collection process was technical, losing data and images on the Globe Observer app, and it forced us to redo fieldwork or work with incomplete data, slowing down our progress. Socially, one of our biggest challenges was dealing with awkward moments and having to explain to homeowners why we were standing in places such as the middle of the road and having to take directional pictures that included their and their neighbors' properties. Through all of this, we learned valuable group skills like teamwork and communication, especially working across different time zones, schedules, and commitments as a group of students across the country. And we also learned other skills such as problem solving and other technical skills. Here are some personal reflections from our team members. Here is a representation of our brainstorming process, timeline, methodology, and future plans, all put together. Thank you to our mentors, Dr. Rusty Lowe, for your guidance and support throughout this program, Dr. Peter Nelson, for always being enthusiastic about our questions, Cassie for always making sure that we submit our forms on time, Dr. Andrew Clark and Dr. Erica Podest for your insightful feedback during our meetings, and our peer mentor, James Irvin, for sharing his valuable SEAS experience throughout our research project. On behalf of the whole team, we'd also like to thank the SEAS staff, Selena Miller and Margaret Baggio, for organizing this incredible program. Lastly, thank you to all our partners at UT Austin's Center for Space Research, NASA, and the Earth Science Education Collaborative for making this opportunity possible.
So we want to invite you to please turn on your cameras and unmute your mics. We have several questions for your team. If given more time, how would the team improve the flood prediction model real-time monitoring, finer resolution, or integration with emergency response systems?
Right, so I'll take this one. So if we had more time, the team would want to include further databases and ground truth data, and basically data from our physical component that's still in the brainstorming phase. And once our AI is finished, we want to incorporate it, like as said in the timeline, with a web platform that provides real-time predictions, and maybe turn it into an app with notifications that could notify people before these flood events. And I don't know if Saad, would you want to add more?
Yes, sorry. So we plan to, as NASA adds more data sets to their satellite collection, we plan to add real-time databases to our web platform. So that's all I wanted to add.
Based on your findings, oops, sorry.
Sorry.
So based on your findings, what changes would you like to see implemented as urbanization continues to reduce flood risk?
Yeah, I can take this one. So we'd like to see cities use more permeable infrastructure like green roofs and permeable pavements to reduce runoff. Protecting natural soils and vegetation is also important since compact soils increase flood risk. And finally, tools like a predictive model, which we'll be developing in the future, could also help cities make data-driven decisions to prepare for flood events.
And also to expand on that, we've seen a complicated relationship between urbanization and flood risk. The highest risk is caused when urbanization results in the loss of natural drainage areas like marshes and swamps, and lower risk when the pre-existing natural environment was not a natural drainage area. So urbanization's effects have to be studied with historical context, which emphasizes the need for long-term data sets.
The next question is, what role did elevation or slope play in your team's flood modeling?
Yeah, I can take this one. So while analyzing land cover and soil properties do tell us about like water retention, examining topography, which is elevation and slope, it actually tells us about how the water is moving on the land. So more flood-prone areas tend to have steeper slopes and lower elevation, which means it tends to collect more runoff, which would imply a higher flood risk. And we plan to use digital elevation models, which tell us about elevation and slope to simulate how rainfall would actually move across the land while we're building this predictive model. And Kushi, do you want to add more to that?
Yeah, so as we analyzed the topography of our different local regions, we did see unexpected discrepancies in the relationship between slope and elevation and flood risk. So we hope to investigate this further as we create a more holistic picture of the factors that create flood-prone areas, because we did realize that the existing relationships aren't always perfectly seen when we're analyzing our data.
So the next question is, what were difficulties you had while collecting points from your AOI?
So I'll take this one. And some difficulties that we had while collecting points from our AOI were technical issues with the Globe app, which was most likely due to the mass influx of updates coming from other Earth system explorers. And we also had problems uploading images, and so we experienced a loss of images while uploading to Globe Observer. And lastly, we were unable to take photos of forested areas and private property and also non-accessible areas.
Yeah, and to add on to this, specifically in my experience, I was unable to reach points that were in gated communities or golf courses, and many other people in Earth Systems Explorers had similar experiences. So based on where you lived, whether it was very urban or rural. People had different positive and negative experiences throughout the course of the project, which is something we wanted to highlight.
Did the team incorporate rainfall intensity or precipitation duration in their predictive model? And if so, what data set was used?
Yeah, hi. So I can actually take that one. So we used the EarthMap dataset and Giovanni, which is used to analyze precipitation rates and geophysical parameters in remote sensing. So one thing specifically we did, at least for EarthMap, was we analyzed hydrology and specifically its runoff. And we also analyzed overall precipitation rates in certain AOIs and comparing these precipitation rates in flood and non-prone areas to analyze those statistical differences. Saad, you want to continue?
Yeah. So we use the DayMat data in combination with other gridded precipitation data sets from the National Weather Service to create rainfall runoff models. So rainfall intensity is also a weather factor that we plan to investigate further for its role in flash flooding using the NOAA precipitation frequency data sets.
Congratulations to your team. Excellent research. So please join me in welcoming our next Earth System Explorer team, Protection Pioneers.
Hello and welcome to the 2025 NASA SEAS Earth Systems Explorers Working Group 2 project. We are the Protection Pioneers.
For our project, we decided on a research question and hypothesis that better help guide us and serve as the foundation for our scientific research. Our research question was, what are the land cover trends and environmental quality changes over time when comparing protected and unprotected areas across different locations? As you can see in the graph below, the environment is something more and more citizens are becoming passionate and involved in, making our research question extremely relevant to today's society. Our hypothesis is that protected areas would show significant improvements or at least less volatility in ecosystem health when analyzing the area over a period of time and comparing the protected area to similar unprotected areas. As we delve deeper into research in the coming months, we hope to be able to answer this hypothesis.
Why does our question matter? Well, we often assume that protected areas are ecologically better than unprotected ones, but that might not always be the case. Some protected zones remain unmanaged as conditions decline, while some unprotected areas are actively restored through landscaping or green infrastructure. As a land use shift, it's important to ask, does protection status actually lead to better environmental outcomes over time? This question has resonated with us especially, as our team lives across suburbs, coasts, forests, in both protected and unprotected areas. For example, one of us lives near the SpaceX launch site in South Texas, where a wildlife refuge is being polluted by private infrastructure. These surroundings not only shaped our interest in this project, but also provided meaningful case examples.
This is the methodology slide for our team. It's going to show you how we used EarthMap to collect data and how we used it to compare protected and unprotected areas. Step 1 is to upload your AOI GeoJSON to EarthMap, which is like a grid of the points you want to look at specifically. The second step is to apply the World Database on Protected Areas, the WPA layer, to EarthMap and search for the closest area to you that is protected, which would be in bright or light red. The third step is to look at the similarities and differences in land cover data by location and time, which you can do by looking at all of the EarthMap layers that is offered. For example, we have ESR land, dynamic world, world cover, and meta/WRI canopy in this example. But there are so many more examples on EarthMap that you could use to collect data. We use EarthMap for our comparisons between tree canopy, world cover, dynamic world, and ESRI, which can show distinct differences between unprotected and protected areas that we're going to be focusing on later in the slides.
The next part of our project is the aggregation poster. Feel free to scan the link and follow along. The data on our aggregation poster is a synthesis of the findings from each of our individual AOI points. The aggregation poster allows us to observe land cover at a more national scale, as it features land cover from every location pinned all over a US map, and it allows us to make recommendations applicable to a larger community. This is our aggregation poster. The 3km 1 meter tree canopy meta, dynamic world 10 meter, ESRI 10 meter, and world cover 10 meter from our AOIs that are represented highlight a rise in built-up land and a decline in green spaces, despite having slight variations in canopy sensitivity. As a result of this data, we are able to use this information to identify constants in land cover trends, which will help our project. Some of these constants include vegetation loss, urban expansion, and more. And this allows us to make more accurate comparisons of environmental quality changes over time.
To help answer our question, we used 4 different resources to compare and understand land cover data. First, we used the Globe Observer app to physically record our own observations throughout our set area of interest. This gave us a concrete understanding of specific locations, preparing us with an accurate starting point and base of comparison. After this, we used EarthMap, a resource that provides a variety of satellite data through different filters. Here, we uploaded our AOI and were able to test the accuracy of different points in comparison to our globe data. We used tree canopy meta, world cover, dynamic world, and ESRI for initial comparisons, and later used an overlapping filter to observe protected land. To see change over time, we used the Landsat Time Series Explorer, which shows land cover changes between 1984 and 2025. To check the accuracy manually, we use Collect Earth Online. This resource prepares a grid of dots that allows us to visually determine certain types of land cover, ensuring a direct classification. Ultimately, through a variety of resources, we were able to observe the accuracy of different satellite classifications, especially between protected and unprotected areas.
This is the preliminary research we did for our project. Since most of our team is located in suburban areas, we want to record any similarities or trends we found throughout our data that relate to ecosystem health. Trends that can be seen as shown in the notable EarthMap statistics is that there's an increase in built-up area, shown in red, there's a decrease in forest coverage, there's a large decrease in water availability, and there's an increase in temperature that can be seen nationwide. Another thing to note is that the population analytics on EarthMap showed that populations were increasing in mostly all of our areas. Ecosystem health can be affected by all of these trends and factors, but there are so many more examples other than the ones I listed, so it's also important to know about these other changes, starting with urbanization and deforestation, severe weather events and temperature rises, global warming, and water quality. On the bottom of this slide, I have 4 screenshots from EarthMap. You might say it doesn't seem like there's a lot of change between the images, but you have to keep in mind that these developments have been in progress for decades. In these images, you can see some patches of green land that are now red, signifying the land is being used for buildings or impervious surfaces. These analytics about ecosystem health and urban development will be seen in the following slides.
This is my area of interest point 7. It is a great example of how we are going to use the different resources to analyze points from our posters. The image on the top left is from EarthMap with the World Database of Protected Areas, or WDPA, layer on. That is how we will be identifying protected areas for our research question. The string of photos along the bottom are also from the EarthMap, but with other layers on, with the exception of the graph on the far left. That graph is the Landsat Time Series graph, and that has NBR, or normalized burn ratio, on the y-axis and time on the x. It essentially shows vegetation health over time. The image to its right is the 1 meter tree canopy meta layer from EarthMap, and it shows the tree height with warmer colors representing taller trees. It clearly shows the line between the protected and unprotected areas as defined by the WDPA layer. The next image is the world cover 10 meter, which is very similar to the dynamic world 10 meter and ESRI 10 meter. In all 3 layers, red represents a built-up area and green represents a forested area. All 3 layers also include that clear line between protected and unprotected areas. Above the dynamic world layer are 2 photos I took on the location via Globe Observer. Looking at these photos, one can clearly see the tree line of the protected area. Last but not least, to the right of the globe photos is the Collect Earth online screenshot. Each member of our team went through and manually labeled the land cover of 100 points within each of our 37 AOI points. This process confirmed the stark tree line yet again. The way these layers agree with each other and show similar patterns supports their reliability. This reliability gives us confidence in using EarthMap to assess points like this to answer our research question.
Here's some data from an unprotected residential area. As you can see, the tree canopy layer and the wall cover layer accurately depict the trees and the vegetation that is found from the Collect Earth Online high-resolution image, as you can see here. But on the other hand, the dynamic world and the ESRI layers completely fail to account for this, and they say that the entire area is full of buildings and impervious surfaces. This shows some slight inconsistencies in an unprotected area between different satellites. This image here is from the NDVI MODIS dataset, and as you can see from this image, the protected areas marked in red have a greater vegetation health than those in unprotected areas. And this is mainly could be due to the fact of a relatively less human activity in these protected areas. Here is a protected area depicted in red with a map with no layers. So as you can see in this image, the protected areas have geometric and evident boundaries, allowing for satellites to much more easily and accurately plot the land cover. And this is evident in the world cover, dynamic world, and ESRI layers, as they all collaborate with each other and accurately depict the land cover in this area. Next, we will talk about the challenges we face, our future plans that we have, as well as reflect on our seas experience.
But not everything was as smooth sailing as it seems. During the duration of our project and gathering research and data, our team came across many challenges and problems that made things a little difficult for us. A notable problem was the issue of many team members' globe pictures deleting easily from the database. This made accessing land cover data really difficult and resulted in many of us having to redo pictures and land cover observations, which eventually delayed our overall progress and increased our workload. Another issue that we came across was that facing data inconsistencies within our AOI on the Earth map was really common. Satellite imagery and globe observer data did not always align, and in some cases the land cover classifications provided by EarthMap differed from what we had observed and recorded. This made it pretty challenging to analyze patterns accurately.
Looking ahead, we hope to execute our methodology, carry out further data analysis, and find patterns from that analysis. By following our methodology, we hope to have an answer to a research question in the following weeks. By having each team member contribute a significant amount of data analysis, we hope to have a pattern within our findings that leads to a highly defensible claim. Additionally, being an Earth system explorer has provided us with many tools to be successful citizen scientists. While completing the internship, we were able to get many certifications in Python, data ethics, and open science, as well as use many databases like the Globe Observer app, Appears, and EarthMap. All of this has allowed us to work towards publishing our first research paper within the internship. As each of our group members reflected on their experience as NASA SEAS interns, one thing was clear. We've all grown our confidence as scientists and researchers within these past few weeks. SEAS has inspired us all to become scientists, engineers, or researchers in our future career. A huge thank you to everyone who made this possible, including the research members of this team, our mentors, as well as a big thanks to NASA, CSR, and SEAS. Thank you.
So I invite everyone on the Protection Pioneers group to please turn on their cameras and unmute their mics. We have several questions that have been posed. How did you choose what things that your team wanted to collect data on?
So I'll take that one. Since most of our team was located in suburban areas, we wanted to record any similarities or trends we found throughout our first sets of data that can also relate to ecosystem health and protected areas. We had to focus on things that could apply to both suburban and protected areas so that we could accurately compare them. So we focused on statistics like temperature, land cover, vegetation, and tree cover, which were statistics that had enough data that we could accurately predict future conditions for. For example, the amount of fires an area had or the emissions in an area weren't really predictable statistics in relation to our research question, even if they do have dramatic effects on ecosystems.
So if you were to continue this project, what new data or region would you want to explore next?
I can take this one. Looking ahead, we would probably include an area that has a national park in it. So think something in Montana like Glacier or in California like the Redwoods. Something that obviously has an iconic American national park to it. So that could be an area that we would look to expand to in the future. And we could also look at things data-wise like biodiversity, the amount of animals or endangered species present in a protected area, as well as plant biodiversity and plants that are important, like trees or shrubs or things like that.
And what classification algorithm, supervised or unsupervised, was used to analyze land cover types in Google Earth Engine?
I can take this one. So we actually already used classified land cover data sets like the dynamic world, the Esri land cover, or the world dynamic. And these are already like data sets that are highly reliable and were consistent globally. And it just made them more ideal for comparing protected and unprotected areas over time.
How did the team compare land change rates inside versus outside of protected areas?
Yeah, so basically there was already a lot of land cover data sets that were classified that we could already use. And like an example, like the ones we showed in the slide, like the NDVI change, which tells you how quickly the vegetation is either growing or degrading. And we can kind of just use these kinds of vegetation indexes to help us benchmark whether or not the land cover is changing.
Great. What years or time intervals were selected to detect land cover change, and how were those intervals chosen?
I can go ahead and take this one. So, from the Google Earth Engine and the other Earth map layers, it was given to us between 1984 all the way to 2025, but we mainly focused on the last 5 to 10 years to show like how this protected and unprotected areas change over time.
And how did you compare your own land cover observations with remote sensing data?
I can take this one. To compare our own pictures and observations, we mostly used it just to confirm that the layers on things like Earth map were realistic. I know there are some members of our team that had been to the locations and said there's like a new development here or something like that, and that would prove that maybe a certain point or two on Earth map were inaccurate.
And how did the team define the boundary for buffer zones around protected areas, and how were they incorporated into your analysis?
I can take that one. So we followed pretty much the definitions of the WDPA layer. So whatever was defined as protected, we said that's protected land. Whatever was defined as a buffer zone, that's what we defined as a buffer zone. Could you repeat the second part of that question, please?
It just disappeared, so I apologize.
No worries.
How did you, not only did you select the buffer zone, but how did you incorporate that into your research?
We incorporated that by considering, hey, this might be like our intermediate zone of the differences between our protected and unprotected areas. So we're obviously like how Penelope had a very, very clear line between protected and unprotected. A buffer zone really couldn't be incorporated to our research in that setting, but in other settings like mine or somewhere maybe in a national park, that buffer zone could kind of be that middle ground or that gray area of saying, hey, we have really tall trees, medium length trees in this buffer zone, and then short trees outside of that.
Well, you've done an excellent job with your research. Congratulations to your team. So please help me welcome our group team number 3 for the Earth System Explorers and conducting their research.
Hi, my name is Imran Shamrao, and we are with the Earth System Explorers program, and we are Working Group 3. Our research question is, how do different durations of urbanization affect plant dynamics? We define urbanization as the introduction of impervious surfaces and buildings. We came up with this question after noticing that each of us live in either an urban area or a suburban area, but each area has had their urban infrastructure for different amounts of time, leading us to question what impact this has on the surrounding plant life.
And throughout our project, we plan to use MRLC NLCD Viewer and Google Earth Engine apps combined with Landsat satellite data to track the progression and rate of urbanization in our area of interest points. Throughout our project, we hope to answer how the speed and duration of development affect the biodiversity changes we observe, how we can use the different satellite data to classify plant life ecosystems, which plant life ecosystems are most affected by urbanization, and are there design elements of suburban development that can be tailored to support wildlife?
In order to gather data, we each created our own AOI grids that consisted of 36 evenly spaced points and one center point, totaling to 37. These served as the basis for the rest of our observations. The entire grid was 9 square kilometers, and each point was given in a 100 square meter bounding box for simpler data collection. We used Globe Observer, which compiled hundreds of photos utilizing the Globe Observer application of our AOI points and their bounding boxes. We took up, down, north, east, south, and west photos for each point, or as close as possible if inaccessible, but those will not appear in our datasets for the purpose of accuracy. We also analyzed each of the photos' land cover profiles using MUC, or Modified UNESCO Classification.
In addition to these ground photos, we also used EarthMap datasets, or satellite datasets that have been projected onto maps. We compiled screenshots of this graph satellite data from 3 different satellites. These satellites are WorldView 4 and Sentinel-1 and 2. And the names of these datasets are the Meta 1-meter tree canopy, 10-meter world cover, 10-meter dynamic world, and 10-meter ESRI. In addition to this, we also used the Landsat time series data, in which we plugged our AOI grid and points into an app made with the Google Earth Engine, which gave us maps and graphs with layers given by the Landsat satellites, starting all the way back in 1984. Lastly, we also used the Collect Earth Online software. This software provides analysis for land cover using aerial photos, which is extremely helpful in cases where we were unable to get to them on the ground.
Hi, everybody. My name is Claire Tagalog. I live in Portland, Oregon, which is my area of interest. Each of us are presenting a poster containing data that represents the full 9-kilometer area, as well as a closer look at each of our 37 data points. In this data table on the right, you can see our pictures from the field, as well as data from the outside sources we mentioned on the last slide. Along the top is the Landsat data, which shows the color reflected by land cover in my area of interest over the last 40 years, or starting in 1984. Also included on this poster are our collection methods, result and discussion summaries, conclusion, and some references. This is a more detailed look at my Landsat data for the whole area of interest over the last 40 years. If we compare the first and last 4 years, we can see the green in the bottom left corner has been more intense in the past, but there's much more green overall at present. This increase in greenery across the city is likely due to the use of residential trees, which are used for shade in the city. This slide shows 2 points that I found interesting. The first point is in a parking lot, as you can see from my ground photos, and the consistency in the year-to-year pattern of the latter part of the graph shows that there is less healthy vegetation in the last 20 or so years. The second point is on a tree-lined road in a residential area. We can see that the most reflected color at this point is green, and the graph is much more scattered year to year, which indicates a more healthy vegetation.
Hi, my name is Jayanna Newsom. I'm a rising senior from West Bloomfield, Michigan, and this poster shows my case study of Detroit. From this Landsat imaging, we can see that Detroit has always been a very urban area, but throughout time, it has grown more green with time. This is because of the organizations and communities that have encouraged more green spaces in Detroit in order to better the environment there. As we can see from these three sets of data, there's multiple instances of shrubbery and grasslands throughout all of Detroit, no matter where you are.
Hi, my name is Adi Mamageshran, and I'm a rising junior in Sandy, Utah, which is a mostly suburban area. In this slide, I show you the Landsat progression images of my centroid coordinate from 1984 to 2025. Over the last 40 years, there is a slow but steady increase in impervious surfaces, and we can see a more noticeable difference if you compare the 2025 image to the oldest 1984 image. So almost all 37 of my AOI locations were integrated inside a neighborhood. The main difference between the locations is the start time, duration, and rate of urban sprawl. For example, my centroid location, which is the first row, is a recently built housing complex, while the other sample points have been fully developed for years. AOI analysis through Dynamic World and ESRI showcased majority built area in all 37 interest points. And AOI analysis through Earth Online, Globe Observer, Tree Canopy, and World Cover confirm high concentration of impervious surfaces in recent years, but they also reveal high vegetation integrated within the suburban neighborhoods, which is not seen in the Dynamic World or the ESRI analysis. In the Landsat graph on the top right, that plots NBR over time, we can see that the green light is constantly reflected, and as urbanization has increased in recent years, there's a steady decrease in NBR.
Hello, my name is Sophie Hoomer, and I'm a rising senior in San Diego, California. This is my research poster that focuses on 37 locations. My area is predominantly suburban with many impervious surfaces and scattered patches of managed green space. This shows the Landsat imagery from 1984 to 2025, focused on my sensor coordinate. The changes do look subtle in my area, but when looking closely, we could see a shift from a more natural vegetation tones in the earlier years to a spread of grays and browns in the recent years. This means that urbanization has happened gradually, but consistently. These are three specific points from my grid. The first point is a suburban neighborhood. In the world cover and dynamic world layers, it's classified as red, meaning that it's been developed. The meta tree canopy shows just a small patch of trees, likely being backyard or street trees. The second point is a golf course. World cover shows yellow, which is grassland, and dynamic world shows green, which is vegetation. The meta tree canopy shows a much larger canopy patch for this point. The third point is a grocery store parking lot. All data sets mark it as red, showing intense urbanization. And the meta tree data show that almost there are no tree coverage at all. These three examples show that areas developed more intensively or rapidly tend to have minimal biodiversity, while areas with intentional green design are better able to retain vegetation.
Hi, my name is Charles Quinn. I live in Burnsville, New Jersey, and this is my research poster. Burnsville is a town dominated by urban activity, but is also home to lots of vegetation, especially in an abundance of tree canopy. Here are my Landsat data chips. These show how Burnsville has developed since 1984. Burnsville remains relatively the same, reflecting lots of bright green light from the tree canopy and surrounding vegetation. There are a few outliers, however. The majority of these are years where the ground reflected less bright green light and more dark green light. We hypothesized that this was the result of longer winters in which vegetation did not start reflecting light until later on in the year. 1986, however, serves as a year of mass urbanization, as Burnsville's main shopping plaza was constructed. While this briefly impeded vegetation, it came back the next year and continued to grow stronger from there. The 3 points I chose reflect Burnsville's balance of greenery and urban areas. My first point depicts a home and backyard, which serves for urban activity, but also promotes a great ecosystem for local vegetation, as seen in the Landsat time series, where higher, more scattered points represent healthier vegetation. The second image demonstrates a private forest, hence the lack of ground observations. Looking at the other 6 sources, it becomes clear that this area is home to lots of thriving vegetation, as all satellite data and Collect Earth Online data agree that the area is covered in vegetation. The Collect Earth Online, far right, exemplifies this even further, as almost every single point is labeled green, representing that it is covered in vegetation. Lastly, the shopping plaza from 1986 represents how it is possible for an area to support urban development in addition to greenery. Looking at the sources, it is clear that there's a lack of vegetation directly in the plaza, as all the satellites and Collect Earth Online data agree it is full of impervious surfaces and buildings. However, the ground images demonstrate that there is lots of vegetation surrounding the urban area, which is extremely relevant in 3 out of the 4 cardinal directions, proving that it can be possible for an area to contain urban features without impeding on surrounding ecosystems.
This is my poster, a 2025 case study of Dublin, California. Here, you can see satellite images of Dublin, California in different time periods. In 1984, notice how the city is almost all grasslands with little to no extra vegetation like trees. In 2025, you can see how with suburban development came lots of diverse vegetation like trees, shrubs, and bushes. This shows how urban and suburban development isn't just impervious and can, in fact, increase the biodiversity of plant life in an area. I chose 3 points from my area of interest grid that I thought best represented our research question. The first is of an underdeveloped area with grasslands and barely any trees. This representation of Dublin before the development shows how sparse it is. The second is of a park with lots of trees next to a road and parking lot. This park shows how with development of urban amenities like parks comes the diverse vegetation of different types of trees and shrubs for the shade and landscaping. The same is true for my third point, which shows a parking lot with lots of trees for shade. The area is made up of all asphalt, but with the parking lot also came the planting of different kinds of trees for shade. Overall, this shows how Dublin, California was converted from originally grasslands to a suburban city with diverse vegetation.
Hi, my name is Arva Wasti, and my case study was on Frisco, Texas. So this is a closer look at my Landsat data. So as we can see, I picked 5 points spread out over 10 years to gradually show the urban development that took place here. And we can see that earlier there was basically none, and in the end, it's a lot different. There's urban development everywhere, and the amount of grass is a lot less. So I picked these three different points to kind of reflect on different areas. And so the first one is just an empty field that is next to a road. And I feel like this is probably going to be urbanized in the future. And this is probably how the area looked before the urbanization took place. The second point is just a natural area near a residential road, which actually it's basically like a creek. And then the third point is a natural area near a road, which is also similar to the first point, probably going to be used for urbanization, except this one has trees as well.
Hello, my name is Boone Macon. I'm a rising junior and I live in Austin, Texas, and here's my current poster. On this slide, you can see different Landsat images for my area for over 40 years with 5-year intervals. You can see that the urban areas have been here for long extended time and are limiting the ability for vegetation to grow. It is also important to note that there is vegetation in the area over time, but the urbanness is limiting the ability for that vegetation to thrive as much as it could. Here you can see 4 different sets of images. If you look at the first image and the second image for the globe observer images, you can see that the vegetation is able to live through being conserved in park areas and suburban yards. And then in the last 2 photos for globe images, you can see that vegetation isn't as prominent due to there being a large amount of urban area where those photos were taken.
Hello, my name is Vineeth Aram, and I'm a rising junior from Leander, Texas. So first, I want to talk about the Landsat time series data for Leander. So if we first look at the bottom left, we see the 1984 image chip. What you see here is that there's barely any urban infrastructure present. There's mainly green area and barren ground. But the first signs of rapid urbanization takes place in 2003, where the first major highway is built in that area. And now in 2025, it's evident that urbanization has occurred in a large amount of the area, with several neighborhoods and many shopping complexes. But one thing that's different between 1984 and 2025, other than urbanization, is that there's also denser greenery in several areas, which is seen by the reflected green. Where in 1984, there's more brown or darker colors compared to 2025, where a lot of the area other than the urbanized part is mainly a light or dark green, which shows that there's more prominent trees and plant life growing there. Next up is the three areas I want to highlight. First up is the Greenbelt area, which shows reduced urbanization. While other areas are being heavily urbanized in Leander, there's also places which are being retained as greenbelts, meaning that no buildings or neighborhoods as such can be built on top of that area to retain the greenery and trees in that certain location. Next up is the urbanized area in new neighborhoods built in the last 4 months. Here, the satellite data shows that it's mainly impervious structures due to only roads and buildings being in that area. The last part is urbanized parts with trees near the neighborhood on park trails. Essentially, what I was trying to show is that while there's also heavy urbanization, there's also trees and plant life being added in conjunction. And this is clear through the ESRI picture, which shows almost half impervious structures and half green trees and plant life. So that goes back to our hypothesis or claim, which is showing that while urbanization is also increasing, we're also seeing an increase in plant life, which was also present in other locations.
This internship taught us all a lot about citizen science and remote sensing. We all agree the case study poster was the most time-consuming, but the most rewarding in the end. We also found the guest speaker events within ESE to be very interesting, teaching us valuable information about the field. Lastly, just becoming a citizen scientist and contributing greatly to the community made us proud we were making an impact and helping NASA in a big way.
This project was not easy to complete, though. One aspect that made it especially challenging was trying to balance schoolwork with internship work. While the work was fun and exciting, it was sometimes difficult to accomplish, especially with an already full course load. Luckily, however, we were able to make it work and complete it all successfully. Another challenge was creating a plan to take pictures of our AOI grids, which was very time-consuming. Lastly, and probably the most daunting challenge, was sitting through long Zoom calls trying to stay awake and finish a project.
I'm grateful for the NASA STEM internship for making a career in space exploration accessible and guiding me on how I can use NASA resources to help our planet. I'm excited to bring back what I've learned to my high school through my space club Space Monkeys in Utah, and thank you for providing such an incredible opportunity where I get to work with like-minded, passionate individuals like my teammates and mentors.
My time as a NASA STEM intern gave me hands-on experience with rewards, research tools, and introduced me to the exciting field of remote sensing. It broadened my understanding of NASA's diverse missions and how science can be used to address challenges on Earth. This experience has inspired me to explore new pathways in science and technology I hadn't considered before.
SEAS has taught me valuable research skills I would have never learned outside of the classroom, in addition to giving me information about new tools that I can use beyond my time with SEAS. I've also gone to make many new friends who I hope to stay in touch with and do science with after the internship.
SEAS has introduced me to a very interesting area of NASA that I didn't even know existed before the internship. I learned a lot about the remote sensing field and may even consider it as a career path when I apply to college. I also enjoyed the guest speaker events, and my personal favorite being about light pollution. I'm very grateful for the opportunity to make new friends and learn so much.
For me, SEAS has shown that there's another side to NASA related to purely just earth science, which is almost arguably just as important as those addressing purely space. And now going on to my career and education path, I might follow that too.
My time as a SEAS intern has provided me with an invaluable experience that broadened my understanding of remote sensing and improved my teamwork skills. I'm very thankful for this opportunity.
My time as a SEAS intern has given me a lot of hands-on experience, things I need to improve on, and excitement for the future that's ahead of me.
Working on this impactful project has inspired me to find new ways to use my existing skills in creativity and problem solving, and working with my incredible peers has inspired me to work harder.
Finally is our acknowledgements. We want to thank everyone who's helped us gather our data, present it here, and set us up for more success in the future. And we want to give a special thanks to Dr. Cassie Sofing, Dr. Rusty Lowe, Dr. Peter Nelson, Dr. Brianna Lind, Dr. Erica Podest, Mr. Andrew Clark, Mr. Hugo Butler, and the entire C staff. And thank you to all our viewers.
So we invite everyone from Working Group 3 to please unmute your mic and turn on your videos. We have several questions for the team. The first question is, does federally protected land create outliers or exceptions to the findings about impacts on vegetation?
I think I got this one. Our main research question, just to reiterate, was how land cover in certain areas has changed over time with urban development. So in the case of federally protected lands, since those lands can't really have urban development because they're protected, those really do lie as an outlier, because with a federally protected land next to a non-federally protected land, you may have a lot of urban development right next to a forest. So just taking that into account and knowing that's federally protected land can help us distinguish those areas from our own research so that we can properly identify why there is a bunch of buildings in one area right next to a giant forest with a diverse ecosystem.
So how did you balance spatial, spectral, temporal, and radiometric resolutions effectively in order to gain a better understanding of your data?
So I can take this one. So looking at spatial data, we used Worldview 10 meters and Sentinel data to look at spatial detail when identifying our features in like tree canopies or impervious surfaces. And coming to spectral data, we also use Sentinel and Landsat, which provided several different bands to calculate indices, such as like NDVI or other monitoring indexes to show vegetation health. And for temporal data, we used the Landsat's long historical record, which we showed with our image chips like 1984 to 2025, which showed us the changes in tracking over time.
Why is land cover so important for understanding climate and ecosystems?
I can take this one. So the type of land cover directly impacts what plant species can thrive, the health of those species, and then it also affects the organisms that rely on those plants. So for example, in Sandy, Utah, I saw an increase in impervious surface in the land led to a decrease in the reflected green light and NBR, which is normalized burn ration. So that typically correlates to a decrease in vegetation health. And so we'd also typically see a decrease in NDVI or normalized difference vegetation index. And so through this project, while we're identifying relationships between the types of land covers and what's happening to the plant species and the density and the health of the vegetation, it can allow us to use these relationships to predict in the future how the different land cover will impact the types of plants we're seeing and then therefore their ecosystems. So that's how it's helpful to help us understand those ecosystems.
What was one challenge your team faced when working with large spatial data sets?
I can take this question. Well, one problem I know many people faced is that working with a large space, a lot of the times we would end up in areas that were private property or homes of people. And in order to take photos, we would either have to ask or wouldn't be able to take photos. So that was probably one of the hardest things.
I can add on to that as well. I think that one of the biggest challenges is we wanted to have like a very evenly spaced grid, but oftentimes because of those private property restrictions or other reasons you might not be able to take a photo, for example, like dense vegetation, you can't get close to the point that you really want to get to. That can make your data there be outside of the range that we really want it to be in like an evenly spaced grid. So that can also just end up reducing your amount of available data for your area of interest.
I'd also like to, go
ahead.
I'd also like to add on to that. With the large spatial data set on the satellite side, I think with so much data coming in, you're always going to get errors with different resolutions. So using our poster, we had a bunch of data from a bunch of different satellites. And by comparing each data set to each other and our land cover photos, we could really identify what were errors and what was actually there so that we can have a whole picture of what was truly there and different errors. So the challenge that it faced were basically there could be errors with different satellite images, But by comparing and discussing with our team, we could come up with a big picture that we thought was correct.
How did your team differentiate between vegetation loss due to local urbanization versus regional climate-induced stressors like drought or heat waves?
The way that we kind of differentiated between long-term impacts as a result of urbanization versus short-term impacts from weather anomalies would definitely be looking at all those Landsat data chips back to back to back. On my slide, I discussed how there are some years where you see almost very little green light reflected, but then the next 5, there's a ton of bright green light. So if you only look at 2 or 3, you're not going to see a lot of change, or you'll see a ton of change. But once you look at, the 45 we did choose to look at, that's where you can see where the underlying patterns are, where the anomalies are. And then looking at the different colors in those anomalies, you can tell which are the result of droughts or climate and which are the results of human interaction.
It's also interesting to note that the Earth System Explorers are still meeting for another 3 weeks, so their research isn't finished. So I want to say congratulations to your team and excellent job. The success of SEAS is determined not only by the commitment and research conducted by student interns, but also by their mentors and our project assistants. To our NASA subject matter experts and project assistants, your passion for youth development, STEM learning, and NASA missions and opportunities is to be applauded. A special thanks to the SEAS project assistants, project associates, Earth System Explorers, peer mentors, and also our SEAS mentor, a SEAS alumni mentor, Aaron Kingsland, who helped to score and guide the Python coding class. I know that SEAS interns appreciate your guidance and advice as they conducted their research. So I want to thank each of you for joining us for day 1 of the NASA SEAS Science Symposium. Please join us again tomorrow at 11 o'clock Central Time as we continue to share the research from NASA STEM Enhancement in Earth and Space Science high school interns.